What up, what up? My name is Mr. Parrish, and I'm presenting to you a video series called Back to Basics, in which I tell you how to do math problems, and at the end of the video, you're going to get hundreds on all your quizzes and tests in math. It's as simple as that. So this video goes over solving one-step equations. This is what one-step equations look like. Your job is to solve. You have to get one of these variables, whether it's A all the way to the left or Z in the middle or Q that looks like all the way to the right. Our job is to get that variable all by itself, completely all by itself. Now, this is what we do. I'm going to do this problem, the first one all the way to the left in red. Start it out in red. I'll probably switch colors as I move along. My job is to get A all by itself. Is A all by itself on one side of the equation or the equal sign? No, it's not. What's in the way? Well, that -6 is floating around in the way. How do I get something gone if it's in the way? See, again, I need to get that letter all by itself on the same side as the equal sign, but it's not. So how do I get rid of a -6? Well, if I owe $6, -6, how do I not owe it? Well, I get $6, +$6. So what I do is I add 6 to both sides. Some people like to build this thing right here, the line. I'll do that once, and then I probably will never do it again. But what I did is I added 6 to both sides. The -6 and the +6 cancel each other out because, again, if I owe $6, but I get $6, I'm good to go, I'm done. A drops down all by itself on the left side. On the right side, I have 13 plus 6, which is 19. And so I ask myself, is A all by itself on the left side now? It sure is. A is all by itself, and on the right side is 19, and I'm donezo. Donezo. My job is to get the letter all by itself. So let's take a look at the middle problem. I have Z, that's my letter, that's my variable. Is Z all by itself on the right side of the equal sign? No, it's not. What's in the way? Well, this -8 is in the way. Okay, Z is not all by itself because that -8 is in the way. So how do I get rid of a -8? The same way I got rid of the -6 over here. I did the opposite of -8 and I added 8 to both sides. I'm not drawing that line because I don't like that line. -8, +8 cancel each other out because they become 0. -8 plus 8 is 0. In the other problem, we just said, oh, I owe $8 and I get $8 or $6. And now I'm back to good. On the left side, I have -3. I owe $3. Now I get $8. So after I pay off the $3, I have $5 left over. And on the right side, I have Z. I like to make my Z's fancy because then it'll look like a 2. Also, I have Z on the right. I don't like writing out my answer as 5 equals Z, although I am done, and if I wanted to circle my answer, technically I'm not wrong. But if someone asks your name, you're not going to say, oh, Mr. Parrish is my name. You're going to say, my name is Mr. Parrish. So if someone says, what's Z? You're not going to say 5 is Z. You're going to say Z is 5. Again, 5 is Z is an acceptable answer. But I just don't like it. Sorry, I don't like it. Let's move my face over there. And let's take a look at this Q problem. Ugh, fractions. Nobody likes fractions. Look at the denominators. What do you notice immediately? They're not the same. So I wonder if that's going to be a problem. Also, what do I notice immediately? Q. Is Q all by itself? No. What's in the way? +2/3. What do I do when I have a +2/3 in the way? A +2/3 in the way? I subtract 2/3. -2/3. See what I did? I crossed those out. Now what I have is I have 1/2 -2/3. Can I subtract fractions when the denominators are different? I'll answer that for you. No. So I have to make the denominator on both of them 6. So what do? So let me rewrite this out. I have to do 1/2 minus 2/3. I'm just rewriting it out. If you had scrap paper, you would run to scrap paper and rewrite it on scrap paper, but I don't have scrap paper because I don't use a computer. So what am I going to do? I have to get these denominators to become 6. How do I do that? Let's multiply u by 3, and let's multiply u by 3, and let's multiply u by 2, and let's multiply u by 2. When I do that, 3 times 1 is 3. 3 times 2 is 6. Whoopsie daisies. Minus 2 times 2 is 4. 3 times 2 is 6. Can I combine them now? I sure can. What do I get after I combine them? 3 minus 4 is -1. And 6, remember, when you add or subtract fractions with the same denominator, you keep the denominator. So my answer is -6. So let me clean all of this up. Bye. The answer was -6. What's 1/2 minus 2/3? -1/6, of course, equals Q. Is that the way I like writing it out? No, I like my variable on the left. Remember? Q equals -1/6. Dunzo. Not fun at all. Not fun at all. Well, for me, it was fun. Pew! All right, let's take a look at the left one. Is H all by itself on the left? No. What's in the way? 3's in the way. How is 3 in the way of H being alone? 3 is being multiplied to H. So in order to get H all by itself, I have to do the opposite of multiply, which is divide. So I'm going to divide both sides by 3. H equals 15 divided by 3, which is 5. Is H all by itself now? Yeah, so I'm done. Look at that. Easy. Is P all by itself here? No. What's in the way? -6. How is -6 in the way? It's being multiplied to P. So how do I get rid of it? Divide it. The opposite of multiply is divide. The opposite of multiply is divide. So we divide -6 from both sides. P equals, let me think. A positive divided by a negative is a negative, and 48 divided by 6 is 8. So my answer is -8. Is P all by itself now? So I'm done. Is N all by itself in this third problem? No. What's in the way? Divided by 2. So how do I get rid of divided by 2? Multiply both sides by 2. So I like to wrap everything in parentheses. 2 times divided by 2 is just crosses out, goes away. N's all by itself on the left now. -7 times +2, let me think. A negative times a positive is a negative, and 7 times 2 is 14. So N equals -14. And if you're wondering, like, how do you know you did this right, sir? You showing all this math stuff, and I don't know if I did it right. It's easy. Take a look at this green one. The green one, we had that answer of 5. So 3 times H? No. 3 times 5. I just found out that H is 5. So is 3 times 5 15? Sure is, which means I did it right. Wait. Is G all by itself? No. What's in the way? 3/4. How is 3/4 in the way? It's being multiplied. How do I get rid of being multiplied to G? I divide, of course. But a very, very, very important phrase that you need to know is, yeah, sure, you can divide by a fraction. But instead of dividing a fraction, multiply the reciprocal. 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 See, normally I divide here, but I don't want to divide a fraction. I'd rather multiply the reciprocal. So I have 4/3 to be multiplied. How did I get 4/3? A reciprocal is when you take a fraction and flip it. Flip it real good. So 3/4 turned into 4/3. That crosses out now, and g is all by itself. How do I multiply a whole number like that to a fraction? Well, let me rewrite it out. I'm just going to rewrite it out. I'm rewriting the right side out. But instead of calling it -12, I'm going to call it -12/1. You can turn any number into a fraction by putting it over 1. So I have -12/1 times 4/3. And when you multiply fractions, you multiply straight across the top, straight across the numerator, and straight across the denominator, which is the bottom. So if I multiply straight across the top, I have -12 times 4, which is 48. And I have 1 times 3, which is 3. Now see if you can simplify. Can you do 48 divided by 3? Sure. 48 divided by 3 is 16. So g is actually equal to -16. Not easy. Not easy. This is the same exact type of problem, just uglier because of the negatives and, whatever. Is that all by itself? No. What's in the way? -4/9. How is -4/9 in the way? It's being multiplied. How do you get rid of being multiplied? You divide. But instead of dividing a fraction, multiply the reciprocal. Instead of dividing a fraction, multiply the reciprocal. The reciprocal of -4/9 is -9/4 because all you do is flip it upside down. -9/4. Those of you who are wondering what those dinging sounds are, my phone blowing up. I don't know what that means. In this problem on the left, we had -12. And then we turn -12 over to 1 so we can multiply fractions. Over here I have -3. So why can't I just make it -3/1? You can. -3/1 times -9/4. Let me see. A negative times a negative is a positive. So my answer is going to be positive. 3 times 9 is 27. 1 times 4 is 4. Can you do 27 divided by 4? No. What does that mean? I'm done. Dunzo. So those are one-step equations, okay? Some people like calling them simple equations, but some of these are not simple. They just call it simple because it's one step, okay? That should do it. Bye. Well, hello, kids. We are going to start a new series called Back to Basics, in which I go over problems. Just take my sweet old time doing it to make sure we understand everything that we need to do. Today's focus is on solving two-step equations. So here we go. My goal is to get M, that guy, all by itself. Is it all by itself? No. In fact, I have two things in the way. I have an over 9, a divided by 9 in the way, and I have a -1 in the way. So if you're wondering which do I get rid of first, I have to get rid of the 9 and I have to get rid of the -1. Which one should I get rid of first? If your job is to isolate a variable, if your job is to get the letter all by itself, what you need to do is see what you have attached. If you have something attached to the letter, like in this case, I have 9 literally attached to M, or if you see something that's floating around, like in this case, -1 is floating around, always get rid of the thing floating around first. -1 is not attached to the M. It's floating around on the same side. So I have to do the opposite of -1 and do that to both sides. The opposite of -1 is +1. And then you can cross that out. Why do you cross out the -1 +1? Because they just cancel each other out. If I owe $1 but I get $1, I'm back to where I started. So they just cross each other out. Now we rewrite what we have. M over 9 did not change, so I'm going to bring down M divided by 9. On the right side, I have negative 2 plus 1. Negative 2 plus 1 is negative 1. Is M all by itself now? No. What's in the way still? Over 9. Over 9 means divided by 9. How do I get rid of divided by 9? The opposite of divided by 9, which is times 9. So I'm going to multiply 9 to both sides. So I'm going to wrap everything in parentheses and times 9 to both sides. 9 divided by 9 cancels itself out because 9 over 9 is 1. So you basically have 1m, which is what we have on the left, an m. On the right side, I have negative 1 times 9, which is negative 9. Is m all by itself now? Yes, it is. Circle your answer. M equals negative 9. So again, my job is to get m all by itself. It's called isolating the variable. Now that m is all by itself, I'm good. So if you have something attached and something floating around, get rid of the guy that's floating around first. M again. So I have something attached, which is negative 4, and I have something floating around, which is positive 5. I have to isolate m. Which one should I get rid of first? The thing that's floating around. What's floating around? Positive 5. How do I get rid of positive 5? Minus 5, which is negative 5. Subtract 5. Do that to both sides. Now I write down what's left over. Negative 15 minus 5 is negative 20. Negative 4m comes along for the ride. Okay? And these guys cancel each other out because if I have $5 but I lose $5, I have nothing. Okay. Is m all by itself now? No. What's in the way? Negative 4. How is negative 4 attached to m? It's being multiplied to m. So how do I get rid of a negative 4 that's being multiplied to m? Do the opposite, which is divide. Divide both sides by negative 4. Divide both sides by negative 4. And the negative 4 over negative 4 cancels each other out because they just turn into 1. A number over itself turns into 1, so I have 1m on the right side. Negative 20 divided by negative 4 is positive 5. So I have positive 5 on the left, and I have m on the right. Is m all by itself yet? Yes, it is. But I don't like having my variable on the right side. Some people don't mind, but if 5 is m, I'm just going to write out m is 5. Same thing. And m is all by itself. I'm in a rocking chair right now. That's why the light's going up and down. It's not a ghost. It's like I'm riding a roller coaster. Oh no! Oh! All right. Let's do a few more. Another two-step equation. Is n all by itself? No. What's in the way? 8. Anything else? Positive 7. Those are both in the way. 8 is attached to n. Positive 7's floating around. Which one should I get rid of first? The guy that's floating around. So the guy that's floating around is positive 7 plus 7. How do I get rid of plus 7? Subtract 7, the opposite. So I'm going to subtract 7 from both sides. 7, take away 7, turns into nothing. Goes away. Bring down what's left. I'm going to bring down the 8n, bring down the equals, and 31 minus 7 is 24. Is n all by itself? No. What's in the way? 8. How is 8 in the way? Well, it's being multiplied to n. So how do I get rid of something that's being multiplied to my variable? The opposite of multiplication, which is division. So I'm going to divide everything by 8. Divide by 8. Divide by 8. 8 over 8 crosses out because it becomes 1. And on the left I have 1n, which is what I want. And 24 divided by 8 is 3. I have to think about that for a second there. Is n all by itself now? Yeah. So that's my answer. Okay. One more. 6 equals a divided by 4 plus 2 is a all by itself. No. What's in the way? Divided by 4. What else is in the way? Plus 2. Which one should I get rid of first? The divided by 4 or the plus 2? Get rid of the plus 2 because it's just floating around on the same side as a. So what's the opposite of plus 2? Minus 2, of course. What's the opposite of plus 2? Minus 2, of course. And whatever you do to the right, you have to do to the left. 2 minus 2 cancel out because it becomes nothing. On the left side, 6 minus 2 is 4. On the right side, these are gone now, and I have a over 4. Is a all by itself? No. What's in the way? Over 4. What does over 4 mean? Oh, that means divided by 4. So I have to get rid of divided by 4. How do I get rid of divided by 4? The opposite of divided by 4, which is multiply both sides by 4. So I'm going to wrap these guys in parentheses to show that I'm multiplying. If you're an old-fashioned person and you just want to say times 4 times 4, there's nothing wrong with that as long as you know what you're doing. But I'm a new-fashioned person. Look at me with the hipster glasses and the backwards cap. I'm going to multiply both sides by 4. I'm going to multiply both sides by 4, cross you out. Okay, 4 divided by 4 crosses out because it becomes just 1. And I have 1a on the right. 4 times 4 on the left is 16. Now 16 equals a, but that's like saying, like, Nick is my name. Well, yes, Nick is my name, but I really should say my name is Nick, which it is. Nick Parrish, that is. And that should do it. We did 4 problems. We slowed it down a little bit. Watch again if you need to feel more comfortable. But that's it. Back to basics. Bye. Oh, I'll be right back. Back to basics. It's the video name. And today we're going to discuss multi-step equations. In a previous video, we talked about two-step equations. And usually the two-step equation started out with add a number or subtract a number from both sides. And then we ended up multiplying a number or dividing a number from both sides. Well, now, that was just 2 steps. Now we're going to have multiple steps. So what do I do with problems that involve a little bit more? I have to think more clearly. All right, so we're starting right out with something that is a little different than usual. I have 6a on the left, and I have positive plus 5a right next to it. If I have 6 apples sitting next to 5 apples, it would be much better if I had a pen. If I had 6 apples and I was just adding 5 apples right next to it, don't I just have 11 apples? Sure do. So if you see 2 things that you can combine on the same side of the equal sign, combine them. 6a plus 5a is 11a. Because if I had 6 apples and I'm going to add 5 more apples, I'm going to have 11 apples. How about them apples? Nothing changes on the other side, though. It's still going to be equals negative 11. And now I'm going to figure out what I do next. Okay, is a all by itself? No. What's in the way? A positive 11 is being multiplied to a. That's the only thing that's in the way. So how do I get rid of the multiplying 11? Divide 11. Divide 11 from both sides. Divide 11 from both sides. Pew, pew. A is going to equal negative 1. Is a all by itself? Yeah. Nice. So this one started out by combining like terms on the left side. Okay, if you have like terms on the same side of an equal sign, combine them. And that's what I did. I wonder if the same thing's going to happen again. On the left side, I have a 4x, I have a 6, and a 3. So it's like I have four xylophones in a room, and next to the four xylophones, I have $6 laying next to $3. Well, if they're in the same side, can I just combine them? The answer is yes. Yes, I can. So I have 4x. The xylophones haven't changed. Okay. And I have $6 next to $3. Well, I just have $9. And now it's a regular two-step equation. So it seems like with multiple step equations, if I have the opportunity to combine like terms on the same side, do that first, and then maybe it turns into a two-step equation, or in this case, yeah, it is a two-step equation. The last case, it was just a one-step equation. Is x all by itself? No. What's in the way? 4 is being multiplied to x, and 9 is being added. So which one should I get rid of first, the 4 times or the plus 9? Always get rid of the one that's floating around first, and 9 is floating around. So we do the opposite of positive 9, which is minus 9. 9 minus 9 cancels each other out. And I just rewrite what I have now. 4x comes along for the ride. You're gone. Equals is equals. And 17 minus 9 is 8. Is x all by itself? No. What's in the way? 4. How is 4 in the way? It's being multiplied to x. How do I get rid of something that's being multiplied to x? Divide it. Divide everything by 4. Divide everything by 4. 4 over 4 becomes 1. So what I have on the left side is 1x. Just have an x. And 8 divided by 4 is 2. Is x all by itself now? Sure is. And x equals 2. Okay. If I have a number multiplied to a parentheses, and inside the parentheses, I have a bunch of things going on. And in this case, I have 3x minus 6. That's called distributive property. And the way you do distributive property is you take the number that's being multiplied to your parentheses and multiply it to everything inside the parentheses. So 3 groups of 3 x's is going to be 9 x's. 3 times 3 is 9. And x comes along for the ride. So it's as if I have 3 bags. And in each bag, I have 3 x's. So if I dump all those x's out somewhere on the floor, if I dump that bag of 3 x's, that bag of 3 x's, and that bag of 3 x's, I'm going to dump out 9 x's in total. So why not just multiply the two numbers and attach the letter? That's what I did. If I have negative $6 in each bag, which doesn't make a whole lot of sense, but if I have negative $6 and I dump negative $6 and negative $6 and negative $6, I have 3 groups of negative 6. In other words, 3 times negative 6 is negative 18. So I have minus 18. The left side didn't change. So I have 18 equals 9x minus 18. So in the first two things, the first two problems that I had to do, I had to combine like terms first. This time I had to do distributive property first. And now I have a two-step equation. What do I mean two-step equation? Well, is x all by itself? No. What's in the way? 9. And what else is in the way? Negative 18. So that's 2 steps that I have to do to get rid of the problem and get rid of everything else. So I have multiply 9 and I have minus 18. Which one should I get rid of first? The one that's floating around, minus 18. So let's add 18, the opposite of minus 18. Add 18 to both sides. Cross it out, cross it out. 18 and 18 make 36. And 36 equals 9x. And you're gone because if I'm down $18 but I get $18, I'm back to nothing. Is x all by itself? No. What's in the way? 9. 9 what? 9 plus 9, 9 times x. So how do I get rid of 9 times? Divide 9. Divide 9 from everything. 9 over 9 becomes 1, so I have 1x on the right. And 36 divided by 9 is 4. 4 is x. Well, that's great. But I don't like my variable on the right side to finish the problem, so I'm going to flip it. Flip it real good. X equals 4. There you have it. So the first two problems I had to combine like terms, and this one I had to do distributed property. Ugh, this is a mess, but that's all right. Let's get back to basics and take our time with it. I have distributed property. How do I know I have distributed property? Well, I have a -8, and no, not an 8, a -8 attached to a parentheses, and inside the parentheses I have 1 plus 7n. So the first thing that we're going to do is distributed property. You take -8 and multiply it to each term inside the parentheses. -8 times 1 is -8. -8 times positive 7n is going to be -8 times positive 7, which is -56, and then n comes along for the ride. Multiply the numbers, keep the variable. Did I do anything with -5n? No, so let's just drop that down, -5n. Did I do anything with equals? No. Did I do anything with -8? No. On the left side, I have a -5n, and I also have a -56n. They're on the same side of the equal sign. And when you have two variables on the same side of the equal sign, you can combine like terms. So the way you combine like terms is you add the coefficients, add the numbers in front. -5 plus -56 becomes -61, and n comes along for the ride. Did I touch -8? Nope. Did I touch equals? Nope. Did I touch -8? Nope. Interesting. I have a -8 on the left and a -8 on the right. I wonder if anything's going to happen. Is n all by itself? No. What's in the way? -61. Anything else? -8. -8 is floating around, so I'm going to get rid of the guy that's floating around first. +8 plus 8. If -8 plus 8 goes away, then shouldn't -8 plus 8 also go away? Yes. Yes, it should. Bring down the -61n. You're gone. You're nothing. And that's going to equal nothing. Well, what do I make that look like? If it's nothing, then you have to have 0 on the other side. Is that all by itself now? No. What's in the way? -61. How is -61 in the way? Well, it's being multiplied. So let's divide -61 from both sides. 0 divided by any number is 0. So my answer is 0. All that for nothing. Literally. Because 0 is nothing. And n starts with, or n is the first letter and nothing. Forget it. All right. Please tell me, oh, I have a few more? Well, like I said before, if I have distributive property to start the problem out, that's what I should do. How do I know I have distributive property? Well, I have 8 times a parentheses, and inside the parentheses, I have a bunch of stuff going on. So I'm going to do 8 times 4k, which is going to be 32k. If I have 8 times -4, I have -32. Drop down the equal sign. -5k minus 32. Now, we haven't run into this problem yet today. I have a k on the left, but instead of the other k also on the left on the same side, it's on opposite sides. So what I have to do is balance out this equation. I have a k on the left and a k on the right. When you have a variable on the left side of the equal sign and a variable on the right side of the equal sign, it's best to eliminate the smallest variable first. Now, I could get rid of 32k if I wanted to, but I'm going to eliminate the -5k on the right. How do I get rid of a negative 5k that's just floating around on the right? Do the opposite of negative 5k, which is add 5k. So if I'm going to add 5k on the right side, I have to do it on the left side. Now, what's the purpose of adding 5k to both sides? Why can't we just combine? Well, we can't combine because they're on opposite sides. So I have to move this guy over here. So if I have negative 5k plus 5k, they cross out. Okay, if I owe someone 5 kangaroos and I get 5 kangaroos, I have to give that person all my kangaroos and I have no more kangaroos. But that person on the other side has 37 whopping kangaroos. Lucky him. Unless you hate kangaroos, then unlucky him. What drops down? Negative 32 equals, you're gone, negative 32. Similarly, like the last problem, I have a negative 32 on the left and I have a negative 32 on the right. They're the same exact thing. So on the left side, I have a two-step equation. If your two-step equation is 37 times k minus 32, then you have to get rid of the guy that's floating around first. The guy that's floating around is negative 32, so I'm going to add 32 to both sides. Add 32 to both sides. If negative 32 plus 32 crosses out, then negative 32 plus 32 also has to cross out. And similarly to what I had last time, I have 37k equals 0. If you go away and you go away and I'm left with nothing, then I'm going to have nothing on the other side, which is 0. Is k all by itself? No, no, no. What's in the way? Times 37. How do I get rid of the times 37? Divide 37. And like I said in the last problem, 0 divided by anything is 0. So what's k going to equal? 0. And there she is. Tricky. But it follows the same rules as every problem so far, except this one had two variables on different sides of the equal sign. Will that happen again? It sure looks like it. So I have negative 11 on the left, minus 5a also on the left. I can't do anything there. On the right side, I have 6 times parentheses 5a plus 4. Well, that's distributive property. So 6 groups of 5a's is going to be 30a. Multiply the numbers, keep the variable. And 6 times positive 4 is going to be plus 24. It's like if I go home and I have 6 bags. And in each bag, I have 5 apples and $4, and I dump everything. If I dump 5 apples and $4, 5 apples and $4 all on the couch, I'm going to have 30 apples and $24. Don't ask me what store I went to when I'm buying apples and dollars. I'm pretty sure there's an apple and dollar store somewhere. What I just did is I wrote out the left side. And now I have an a on the left side of the equal sign and an a on the right side of the equal sign. I have variables on different sides of the equal sign, so I can't combine them. So what I should do is get rid of the smallest variable first. What's the smallest of the two variables? Negative 5a. How do I get rid of negative 5a on the left? The opposite of negative 5a, which is positive 5a. So I'm adding 5 apples to each side. That way, the negative goes away. So what drops down? Negative 11. You're gone. Equals 35 apples plus 24. And now I have a two-step equation. Is a all by itself on the right side? No. What's in the way? 35 times. What else is in the way? Plus 24. Which one should I get rid of? The times or the plus? The plus. Always get rid of the guy that's floating around first. What's the opposite of plus 24? Minus 24, of course. Minus 24. Negative 11 minus 24 is negative 35. That's going to equal 35a. Is a all by itself? No. What's in the way? 35. How is 35 in the way? It's being multiplied. How do I get rid of something that's being multiplied? Divide. So I'm going to divide both sides by 35. Divide both sides by 35. And what I get is positive 35 being divided from negative 35 is going to be negative 1 equals A. But you know I don't like that. Negative 1 equals A could also be written as, and I'll write it over here, A equals negative 1. Okay? Drink it in. It's a tough problem. But I believe we have one more. And it might be considered the toughest problem that we've done so far. Maybe. We'll see. I don't know. Look at the left side. Distributed property. Let's do it. Negative 5 times 4x is negative 20x. Negative 5 times negative 2 is positive 10. Equals is equal. Now on the right side, I have distributed property again. Weird. Negative 2 times positive 3 is negative 6. And negative 2 times positive 6x is going to be negative 12x. So I have an x on the left. I have an x on the right. As I know from the last couple problems, if I have an x on the left and an x on the right, I should get rid of the smallest x first. It doesn't mean I don't have to do it that way, but I like doing it that way because it makes things positive. What's the smallest of these two x's? Negative 20 seems to be smaller than negative 12. So I'm going to do the opposite of negative 20x, which is plus 20x. And I'm going to do that to both sides, plus 20x. Negative 20x, positive 20x cancels each other out. What do I bring down? The positive 10 equals negative 6 minus 12x. I'm recording a video. Can I finish recording the video? Okay, bye. Love you. Mwah. Give me 5 minutes. Give me 5 minutes, okay? Love you. Kids. All right. So let's rewind a little bit. What did I do? Negative 20x, positive 20x went away. 10 just drops down. Equals just drops down. Minus 6 just drops down. I have 20x and negative 12x, which becomes positive 8x. That was a close one. See, distractions, but now I have a two-step equation. Is x all by itself? No. What's in the way? Negative 6. Anything else? 8. Which one should I get rid of first, the negative 6 or the 8? The negative 6, because it's just floating around. How do I get rid of a negative 6 that's just floating around? Add 6, of course. Add 6, of course. Cross you out. What's 10 plus 6? 16. What drops down on the right side? 8x. Is 8x all by itself? No. What's in the way? Or is x all by itself? No. What's in the way? 8. How do I get rid of 8? Divide 8. Divide 8. And on the left side, you have 2. So let me write that over here where I have a little bit more space. On the left side, you have 2. On the right side, you have x. I hate the way that looks. I'm going to flip it around. X equals 2. So we did a bunch of problems here. We did quite a few problems that involve multi-steps to solve. So if you're not sure, rewind this, watch a few more. But this was solving multiple step equations, a lot of distributed property, a lot of combining like terms, and a lot of variables on both sides of the equal sign. Okay, so that should do it. If you have kids and you decide that you're going to record a video, lock the door. Bye. What up? Mixture problems is what we're going over today. These are the types of problems that you see that are word problems, and it's like you go to the store and you buy trail mix and it's 25% M&Ms, and your bae brings home trail mix that's 10% M&Ms, but you want 15% M&Ms. How much of each should you mix together to give you that sweet percentage you want? That's what we're dealing with. These are the problems that are like, you have acid and it has this much solution. Basically, you have a certain amount and you want to add a certain amount to get a certain amount. Okay? Freddie is joining me today. As you can see, he's got a nice, handsome haircut because it's summer right now on the day of this recording, and today it felt like over 100 degrees, so a guy needs to feel good. Which is why I shave my head, because of the weather. Speaking of weather, whether or not we know how to do these problems. Sorry, Freddie, for getting cut off. Like your hair was. What we're going to do is we're going to have information. A lot of the information that we're going to be given is known. So again, you're going to be given something like, we have 25% of this stuff, and we want to mix like 18% of this stuff so we can get 20% of that stuff. And what we do is we set up a table that looks like this. We have rate in one column, we have the amount in the other column, and we have what I call the product, which means you multiply guys together. So, you know, if you know the rate, what did I say, 25%? I don't know, certain stuff, we'll say A. The product of that is 25% of A. Now, we always take our rate and we turn it into a decimal, so 25% is 0.25A. If we don't, what did I say, 18%? So 18% of, let's just actually say that we know the amount of the second one, and let's just say it's 15 pounds, just for funsies. We would write out 0.18, because that's 18% as a rate, times 15. You can probably hear my dog in the background. You hear that annoying dog? And what did I say? We wanted 20%, so we want 20. And this is what I know. I know that if I'm going to mix A amount plus 15, my amount is going to be A plus 15. So I will write out 0.20 or 0.2 parentheses A plus 15. This is confusing, not confusing, this is a pain in the butt. We're going to do 4 of these, so hopefully it will be less of a pain in the butt. What you do is you take this product, you add to that product and equal that product. So the equation that we're going to give ourselves is 0.25A, and I'll use x from here on out, plus 0.18 times 15 equals 0.20 or 0.2A plus 15, and then we just solve a really terrible looking problem. But basically the general idea is, if we have, like, you know, mixture number 1, or if we have group number 1 and group number 2, we write out our rate right here. We write out how much we're given, whether we know it or not, and then we multiply those two to get this column. Whatever our mix number 2 was, we write out the rate right there, whether it's percent or price. We write out the amount and we multiply those together. Then we take what we hope to get. So in this case, I said, I hope we get a 20% mixture. We write out 20. I know what my amount is. If I'm adding A and 15, it's going to be A plus 15. And my product is going to be 0.2 times A plus 15. We write it out. We say the first one plus the second one equals the third one. That's our equation, bada bing. So let's do 4 of them, okay? Again, this is a not fun topic, a very difficult topic if you want my opinion. You know, these are the types of things where if you were like, Mr. Parrish, what are your least favorite things to teach in Algebra 1? There you go. Hate these. But we got to do them. We got to do them. What if you become a scientist and you need to do stuff like that? All right. So I have mixture number 1, 5 fluid ounces, 2% alcohol solution. I'm going to put that in red. It's mixed with 11 fluid ounces, 66% alcohol solution. Find the concentration of the new mixture. The concentration is the percentage. Okay? So, what I have in mix number 1, in mix red, I have 5 fluid ounces, so in my amount, I'm going to put 5. I have 2% alcohol right there. And I have to find out the product. So I have 0.02 times 5 because I multiplied those numbers together, and there you have it. Okay, 0.02 times 5. That's mixture red. Mixture green is 11 fluid ounces, so that's my amount. 66% alcohol solution, so 66%. And I'm going to multiply out 0.66 times 11. That's my product. Okay. My rate is, I don't know. I'm trying to find the rate. My total amount of new mixture is, well, I knew that I added 5 of some stuff and 11 of other stuff, so that's going to be 16. And so x times 16 is 16x. Now, what I do to set up an equation is I add that guy, red, I add it to green, and it equals out 16x. So 0.02 times 5 plus the green 0.66 times 11 equals 16x. The x is going to give me the rate. Okay, the rate of my total final mixture. 0.02 times 5, I think, is 0.1. 0.02 times 5.
The answer is 0.1.
0.66 times 11. I have zero idea. 0.66 times 11.
It's 7.26.
And that's going to equal 16x. And then you just solve this equation. Okay? 0.1 plus 7.26 is 7.36. And that's going to equal 16x. Is x all by itself? No, we have to divide 16 from both sides. Divide 16 from both sides. 7.36 divided by 16.
It's 0.46.
So 0.46 is my rate, which means I want to turn that into a percent. So 0.46 is 46 out of 100, so my final answer is 46%. All right. Told you it was a lot of fun. I don't know why my dog's freaking out. It's 8:18 here on a Sunday evening at my house. Oh, I know. My kids are eating popcorn upstairs, so she's going berserk. Let's do it again. We have 16 pounds of brand M cinnamon. So what I didn't do with the last one is I didn't label it. So I'll call you brand M cinnamon. Was made, the whole thing is brand M cinnamon. All right, brand M. McCormick's. 16 pounds of brand M cinnamon was made by combining 12 pounds of Indonesian cinnamon, which costs $19 per pound, with 4 pounds of Thai cinnamon, which costs $11 per pound. Find the cost per pound of the mixture. This one's actually a little bit friendlier than the last one. All right, so we have the Indonesian cinnamon. We'll make you red. We have the Thai cinnamon. We'll make you blue. And we'll start filling things out. Indonesian cinnamon is, we got 12 pounds of it, and it's $19. So we've got $19 of the Indonesian cinnamon, and there's 12 pounds of it. So I've got $19 times 12 pounds. All right. I've got the Thai cinnamon, which is 4 pounds of that, $11 a pop, which is 11 times 4. That's math I can handle. Find the cost, so I don't know the price, the cost, so I'll call you X. It is 16 pounds, and that's obvious because this adds up to 16, and it also tells us that it's 16 pounds at the very beginning. That's why I said this problem's slightly easier than the last one. And so when I multiply those two guys together, I get X times 16, or 16X. Was the last one 16X? Oh, jumping the gun. Yeah, look at that. Not very creative. So I take 19 times 12, add that up to 11 times 4 to get 16x. So I have 19 times 12, which I don't know what that is. I'm going to add that to 11 times 4, which I do know what that is, and that equals 18x. 19 times 12.
It's 228.
I'm going to add that to 11 times 4, which is 44. Add that, not equal it. Shame on me. And that's going to equal 16x. 228 plus 44 is 272.
The answer is 272.
That's going to equal 16x. Is x all by itself? No. Divide both sides by 16. Divide everything by 16. Bada bing. 272 divided by 16.
The answer is 17.
17 is equal to x. What was x? The price of brand M. So $17. Baby. Oh. And that makes sense. Dollars and cents. Because I added a lot of the $19 stuff to a little of the $11 stuff, so it's going to be more on the pricey side, not near as expensive as the $19 stuff. How many milligrams of a metal containing 45% nickel must be combined with 6 milligrams of pure nickel, which is 100%, to form an alloy containing 78% nickel? All right. So I've got nickel number 1. I've got nickel number 2. And I need the alloy. Okay. How many milligrams of 45% nickel? So I don't know that. I have no clue. Must be combined with 6 milligrams, so I know you're 6, of pure nickel, which is a hundo. To get 78% alloy. Now this mixture is x plus 6, because I don't know how much of the first, I do know how much of the second, so I get x plus 6 for my alloy, because you just combine them. So we've got 0.45x right now. We've got 100, which is 1, 6, and that's going to equal 0.78x plus 6. So I'm going to add that guy to 6 and have it equal 0.78x plus 6. So 0.45x plus 100% of 6 is 6 equals 0.78x in parentheses plus 6. First thing I should do is distribute a property on the right side. So the left side has not changed, not yet. 0.78x 0.78 times 6.
The answer is 4.68.
I always like subtracting the smaller number when I have two variables or one variable on each side. So I'm going to subtract 0.45x from both sides minus 0.45x cross u out. And that's going to be 6 equals 0.33x plus 4.68. I'm going to subtract 4.68 from 6, so minus 4.68 because I'm subtracting the number floating around from both sides. 6 minus 4.68 is 1.32, and that equals 0.33x. Is x all by itself? No. Divide both sides by 0.33, divide both sides by 0.33. 1.32 divided by 0.33.
The answer is 4.
Oh, wow. Perfect. So 4 equals x. So what was x? X was the amount of nickel. So how many milligrams of metal containing 45% nickel? 4 milligrams of that metal. What do you think, buddy? Pretty intense, huh? Pretty intense. Pretty intense. This is a good guy. He's a good friend. By the way, today is August 8th, which is National Cat Day. I celebrate you, Freddie. Mwah. Just love a cat. Love cats. Love me some cats. All right. Brand X sells 21-ounce bags of mixed nuts that contain... Hey, mixed nuts. That's the name of a SpongeBob episode. Brand X sells 21-ounce bags of mixed nuts that contain 29% peanuts. To make their product, they combine brand A, blah, 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 and brand B, blah, blah, blah. So X is what I want. A is here, B is there. X sells 21-ounce bags that is 29% peanuts. I put 0.29 instead of the percent because why not? All right. To make their product, they combine brand A, which is 35%, so 0.35. We don't know how much. And brand B, which contains 25%. All right. How much of each? All right. So we don't know how much is A. Here's the thing. We don't know how much B is either as far as my amount. The last thing I want to do is introduce a new variable because then I won't be able to solve it. Now, when I learn how to do these with systems of equations, that's a different story. But right now, I don't know how to solve this with two variables. So I'm not going to say that you're X because I don't know what you are, and you're Y because I don't know what you are. What I do know is the whole thing's supposed to be 21 pounds. Pounds, ounces, 21 ounces. And I already added X, which means the rest is going to be 21 minus X. So if X was 10 pounds or ounces, and you're like, well, I added 10 ounces, how much do I have to add of this stuff? You would say, well, 21 minus 10 is 11. But we don't know that this is 10. So we're going to just say X. So 21 minus X, which means your 0.35X, your 0.25 parentheses 21 minus X, and your 0.29 times 21. Lots of stuff that I don't know off the top of my head. But what I do know is I add U to U and have it equal U. Or as Soldier Boy would say, U. Bam, 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 writing out equations. All right, so now I'm writing the guy out. That's in third column. Plus 0.25 times the quantity 21 minus x equals 0.29 times 21. 9 plus 10. Your 0.35x. I'm pretty sure 0.25 times 21 is 5.5. No, 5.25. 0.25 times 21.
It's 5.25.
Minus 0.25x is going to equal, I have no clue what that is. 0.29 times 21.
That would be 6.09.
Okay. Forgot my x there. That would have been catastrophic. Catastrophic. Let's combine like terms. If I have 0.35x and I'm taking away 0.25x, that's just 0.1x. Plus 5.25 equals 6.09. I'm going to subtract 5.25 from both sides. 0.1x equals 6.09 minus 5.25.
It's 0.84.
0.84 divided by 0.1.
It's 8.4.
All right, so what am I supposed to do? I'm supposed to... How much of each do they need to use? So I need to find out how much of A. Well, X is how much of A. So A is ounces, 8.4 ounces. B, the amount B is 21 minus 8.4. 21 minus 8.4.
The answer is 12.6.
Yuck! But now I know how to mix nuts together. Chocolate? Did he say chocolate? SpongeBob episode called Mixed Nuts. That's all I've got. Tuffy. Watch this 15 times for your own good. As for me and my cat, I wish you adieu. And together we're going to say bye. Oh, are you looking at my back? Well, that's appropriate because we're about to get back to basics. So today we're going to talk about rewriting equations. Now, normally we'd look at a problem like this and be like, you can't solve for y, sir. There's two letters there. One's a y and one's an x. How are you going to get y all by itself when there's an x floating around? Easy. You just keep x attached to 5 and pretend it's like a party hat or something. See, if that x wasn't there, pretend this whole time that we're doing this, pretend that x is a 0. And so pretend that this is 2y plus 50. Just pretend. 50. X's are now zeros. Equals 6. You would look at that and say, well, is y all by itself? No, because 50 is in the way, and because 2 is in the way. Well, that's not a 50. It's a 5x. It's a 5 with a party hat attached. It's a 5 with an ear piercing. It's a 5 with glasses. So what are we going to do? Let's just get rid of 5 and x all at the same time. So we're going to subtract 5x from both sides. So I have 6 and a negative x, 5x on the right side. Can I combine the 6 and the 5x? No. No, I can't. Why? Because one has an x and the other one doesn't. So I'm going to write out what I have. 2y, that's now gone, equals, and this is the way I'm going to write it. Negative 5x positive plus 6. I always like putting my x first, just like in my dating history. I'm being humorous. I'm being humorous. Is y all by itself? No. What's in the way? 2. How do I get rid of that 2? Divide that 2. Divide it from everything. Divide it from the 5 and the 6. Rule of thumb is when you do this, simplify what you can, but keep it improper. Okay, and if you're like, I don't understand why we have to do that. Why did we have to put the negative 5x first? Why can't I make that a negative 2.5 or negative 2.5? Why do I have to listen to you? Trust me, you're going to learn something called slope-intercept form, and you're going to want to get used to putting things in this way. So if you can keep it as, or if you could simplify it, but keep it as an improper fraction if you can. Negative 5 over 2 is negative 5 over 2. Is it pretty? No, but someone's going to love it. X comes along for the ride. 6 over 2 is actually 3. How nice. And now y is all by itself. Since y is all by itself, I've officially solved for y. So this wouldn't be too different if instead of subtracting 5x, I subtracted 50. And then instead of dividing 2, I'd still divide 2. It's just now I have that x there, and so I have 2 things on the one side instead of 1, and I have to divide 2 things by 2 instead of the 1. The rules don't change that much. They're just a little more inconvenient. Now this problem is actually a whole lot nicer. I have to solve for b. My formula is a equals bh. Is b all by itself? No. What's in the way? H. How is h in the way? It's being multiplied. How do I get rid of it? Divide both sides by h. So I'm going to divide both sides by h, and h over h cancels out. Now b is all by itself. Does the a and the h on the left side combine? No, because a and h are different. In fact, one means area, the other means height, and you can't combine area and height. So I have a over h and leave it like that. And you're going to have some teachers, me being one of them, who does not like your final answer to have the variable on the right side, and they might ask you to switch the variable to the left side. And I'm going to do that right now. B equals a over h. Now b is all by itself, and I'm done. Very similar problem. Simple interest formula is I equals PRT. Principal times rate times time. If I wanted to get P all by itself and solve for the principal, like if I was doing, what interest means is how much extra money you get, like on a loan or pretty much just a loan. How much extra money you get or how much extra money you have to pay for. And if I wanted to solve for how much money I put in, that would be solving for P. Now, I'm going to rewrite the equation. I equals PRT. Is P all by itself? No. What's in the way? R and T. What are R and T currently doing? Multiplying to P. So why not just divide both of them at the same time? Well, I can. So that's what I'll do. R crosses out. T crosses out. On the left side, I have an I and an R and a T. Do any of them combine? No, because interest is not the same as rate, which is not the same as time. So I have I over R times T, and P is now all by itself. Mean, picky, crazy teacher with the backwards hat says, I don't like P on the right. Move it to the left. And the answer stays the same, but it looks a whole lot prettier. So the first problem we did, the solve for y, was a pretty tough problem. The second two were not so bad. Let's end with a bad, ugly, terrible problem. Now this is about as ugly as you're going to see it in 8th grade or 9th grade math. I have to get h all by itself. That h. And I have all this other stuff in the way. So S equals 2 pi r squared plus 2 pi r h. I believe that's the surface area of a cylinder. I believe. I have to get h all by itself. Is h all by itself? No. What's in the way? Well, this whole chunk is floating around. So what we always do is get rid of the guy that's floating around first. If that means I get rid of the entire guy, then I'm going to get rid of the entire guy. So I'm going to subtract 2 pi r squared from both sides, minus 2 pi r squared. Cross that out. Okay. Does s and minus 2 pi r squared combine? No, because s is surface and pi is pi and r squared is r squared. It's its own thing. So we write out s minus 2 pi r squared on the left. What do I have left over on the right? 2 pi r h. My job is to solve for h. Okay? And I'm going to do this the same way that I did that first problem. Not all teachers are going to do it this way, but I like to get everything as simplified and as clean as possible. So let me move my face up there because I might need the room. Is h all by itself? No. What's in the way? 2 and pi and r. How are 2 and pi and r in the way? 2 and pi and r are being multiplied to h. So I have to divide everything by 2 and pi and r, which means I have to divide u by 2 and pi and r, and divide u by 2 and pi and r. Now this is what I'm about to do is pretty advanced. So if you want to leave your answer like this, I guess that's okay. But watch what I'm about to do. See how the 2 is over the 2 and we cross it out? Why can't you do that over there? And see how the pi is over pi and we cross it out? Why can't you do that over there? This is where you have to be careful. I have an r over an r and you cross that out. I have 2 r's over 1 r. So I can cross out 1 r and be left with just an r there. And some of you might look at that and be like, yeah, I don't know about that. And that's okay. If you're just starting out 8th grade math, you don't have to think this deeply into it. But I'm a math teacher, this is what I do. So why don't I clean all of this mess up? And while I clean all of this mess up, I'm going to put h all by itself on the left. So here's h all by itself on the left. I have s over 2 pi r. So s over 2 pi r minus r. There you have it. So that last problem was brutal. Impossible? No, nothing's impossible if you just believe in yourself. Bye. Back to basics. The missing length of a right triangle. How would I do that? Pythagorean Theorem. If I ever have to find the missing length of a right triangle, I do what's called the Pythagorean Theorem, which states the following. A squared plus b squared equals c squared, where c has to always be my longest side, my hypotenuse, and a could be any of the legs, and b could be any of the legs. So looking at my picture, c is already c, so I'll call you a and I'll call you b. It doesn't matter which one's a or b as long as the longest side is c. That's a rhyme. So I got 21 squared, I got 20 squared, and I got c squared. We're going to use Siri a lot today, or at least I'll use Siri. Let's see if I have good connection in my classroom. I'm in my classroom right now, which is like a lead wall because there's like no signal. 21 squared, I think it's 441. I know you're 400.
21 raised to the second power is 441.
Told you. Now, 21 squared was 441. 20 squared is 400 because 2 squared is 4, so 20 squared is 4 with 2 zeros attached to it. Is C all by itself? No, but I have 441 and 400 being added right next to each other, so why don't we add them up? Makes sense to me. That's going to equal C squared. Is C all by itself? No. What's in the way? Squared. How do I get rid of the squared? Square rooted, of course. What's the square root of 841?
The square root of 841 is 29.
Oh, on the dot. So my number is 29. My unit is kilometers. So that means my answer is 29 kilometers, which makes sense. If 29 is supposed to be longer than 20 and 21, and 29 is supposed to be a shortcut, that seems to make sense. The numbers match up. The numbers match up. Find the missing length of the triangle. Okay, well, it's a right triangle, so I'm going to write out a squared plus b squared equals c squared. Doesn't matter which one's a or b as long as the longest side is c. So you have to be c, and I'll call you a because you're already called b. Well, this one's going to be slightly different. Not hard, but different. A is 9 squared. B is b. And c is 15 squared. Just plugging them in. 9 times 9 is 81, plus b squared equals 225, 125. No, 225. I was right. Should have gone with my gut. Is b all by itself? No. What's in the way? 81. Anything else? Squared. So which one should I get rid of first? The 81. Minus 81, minus 81, cross you out. B squared equals 225 minus 81, which is going to be 146. No, it's not. It's 144. I looked at that and I knew something wasn't right. Again, I should have gone with my gut. And when my gut says something, you gotta go with it. Is b all by itself? No. What's in the way? Squared. How do I get rid of this squared? Square root it. Let's go. Hey, let's go. B equals 12. 12 what? 12 or millimeters. Which makes sense. I mean, according to the picture, it looks like it's going to be bigger than 9, smaller than 15, so is 12. Yeah. Let's do more. See how many mistakes I can make for this one. Well, this is plastered on top of a coordinate plane. And it's a right triangle yet again, because these guys are parallel. So I'll write out a squared plus b squared equals c squared. Doesn't matter which one's a or b as long as the longest side is c. The longest side is already c, so I'll call you a and I'll call you b. So a, according to what I wrote out, is going to be 8 squared. B, according to what I wrote out, is going to be 6 squared. And C is C. 8 squared is 64. 6 squared is 36. C squared is C squared. 64 plus 36. 100. Yum. Is C all by itself? No. What's in the way? Squared. How do I get rid of squared? Square root it. Square root. Square root. Cross you out. C equals 10. 10 what? Boxes. Units. Squares. Doesn't matter. If I don't have a word, I don't need to write out a word. You can say the word units, and you'll still be right. Don't you worry. Don't you worry your pretty little heads off. Oh my gosh, what is this? It looks like a block of cheese that's pink without edibility. I don't even know if that's a word. Well, if you're X, I don't know how I'm going to find you, but you're going to be the same as that. Oh, I see what I'm supposed to do. It gives me a 3D shape, and I'm supposed to use the information that I have and find the missing side by pretending it's all a triangle and it's all connected. That makes sense. a squared plus b squared equals c squared. It doesn't matter which one is a or b as long as the longest side is c. So I'll call x c, I'll call 14a, and I'll call 48b. So I have 14 squared plus 48 squared equals x squared. 14 squared is 196. What's 48 squared?
48 raised to the second power is 2,304.
Look at that. I know something magical is going to happen just by looking at those numbers. Well, look at the two numbers on the left. They're being added to each other, so just add them. No way. Equals x squared. Is x all by itself? No. What's in the way? Squared. How do I get rid of the squared? Square root it. You know, the square root of 25 is 5. So the square root of 25 hundreds is like 5. Square root of 100 is 10. Just put a 0 there. Let me see. Inches. And we'll throw the x over here. X equals 50 inches. Okay. Find the missing length of the triangle. Oh, I have a dot here and a dot here. And it tells me that I need to find the missing length. So that's going to be C because it's going to be the longest side. I'll call you A and I'll call you B. A bunch of problems on coordinate planes. I wonder if that's going to be like a topic. I don't know. A squared, hot topic, plus B squared equals C squared. Hot topics. It doesn't matter which one A or B is as long as the longest side is C. So I called A 8 because they rhyme. I called B 6 because they don't. And C is C. There's no name or no letter for C. 8 squared is 64. 6 squared is 36. 64 plus 36 is 100. Is C all by itself? No. What's in the way? Squared. What do you do? Square root. And we did a problem just like this already, 10. Now, I'm not going to put C equals. Why? Because I'm just being asked to find the missing length of the triangle. So if someone's like, hey, how far did you walk to school? You're not going to be like, C equals 10. You're going to say 10 blocks. Well, in my case, I'm going to say 10 units because it gave me the word units, and I'm very picky and I'm very peculiar. Okay. So I was able to use that information to find that dotted line, which happened to be on a coordinate plane. Oh, look, a line on the coordinate plane. Well, I'm no genius, but it looks to me that if I'm going to compare that to the last problem, and I had to find a line on the coordinate plane, I was able to take like other lines and pretend that those are the sides of a triangle. And I had that here also. So why don't I just do that again? Why don't I just turn this guy right here into a triangle? And then I'm going to literally, and you're not going to be able to see me do it, but I'm literally going to go from one of the points and go 1 block, 2 blocks, 3 blocks. So I'll do that in a different color so you actually see what I do. It's like when we do the slope, when we count up and over. It's the same thing. I have 1 block, 2 block, 3 block, 4 block, 5 block, 6 block, 7 block, 8 block, 9 block, 10 block. And then this is going to be 1, 2, 3, 4, 5, 6. So what I don't know is C. So I have A squared plus B squared equals C squared. Computer's very laggy all of a sudden. I'll call you A because why not? It doesn't matter which one's A or B as long as the longest side is C. So A is 6, 6 squared. B is 10, 10 squared. C is, I don't know, 36 plus a hundo is going to equal C squared. Right next to each other, I have 36 plus 100, so let's add them. Is C all by itself? No. What's in the way? Squared. How do I get rid of squared? square root it. I don't know what the square root of 136 is, but I know it's less than 12. What's the square root of 136?
Just a sec. Here are the last 100 games for the Rangers.
What's the square root of 136?
The square root of 136 is approximately 11.6619.
So we'll say 11.7, because 2 6s in a row makes me uncomfortable. Okay, units. The only thing that I care about is the number, because I don't have to call it C if I don't want to. So if I'm asked to find the distance between 2 points, you can turn it into a triangle. There's another method called the distance formula, but I hate it. Mr. Richard owns an orchard that has a rectangular fence. The orchard is 36 yards long, as you can see from the picture, and 18 yards wide, as you can see from the picture. If he walks across the diagonal length of the orchard, how much distance would he cover? Okay, well, I need to find the diagonal. And if I know you're 36, and I know if this is 18, you're going to be 18, I have to find the longest side of a right triangle. Pythagorean Theorem. I have a squared plus b squared equals c squared. If I call u a and u b, I'll have 36 squared plus 18 squared equals c squared. What's 36 squared?
36 raised to the second power is 1,296.
What's 18 to the second power?
Just a sec. Working on that.
344?
18 raised to the second power is 324.
What's 1,002? Let's try that again. What's 1,296 plus 324?
That would be 1,620.
Is C all by itself? No. What's in the way? Oh, you know what's going to happen. Just square root everything. What's the square root of 1,620? Please be nice. Please be nice.
The square root of 1,620 is approximately 40.2492.
What did it say? 40.24. So we'll put 40.2 yards. He would walk 40.2 yards. Lots of Pythagorean Theorem. Still got more. Is the triangle a right triangle? Well, if I have right triangles, I always deal with a squared, b squared, and c squared. So what I need to do is I need to label these triangles C, A, and B. Doesn't matter which one you label C or A or B as long as the longest side is C. I have a squared plus b squared equals c squared. A is 36. B is 27. I'm just going to do a little bit of math and see what happens. Okay? What's 36 squared?
36 raised to the second power is 1,296.
I think I did that one before. I don't know. What's 27 squared?
27 raised to the second power is 729.
Okay. What's 45 squared?
45 raised to the second power is 2,025.
Two numbers over there being added together. What's 1,296 plus 729?
It's 2025.
This adds up to 2025. So this is what we have to do. If I ask you if something is a right triangle or not, you call the longest side C and you call the other two sides A and B. Doesn't matter as long as the longest side is C. You do the math, and if the left side checks out with the right side, it's a yes. So looking at that triangle, you would have to be C, and you can be A, and you can be B. So A squared plus B squared equals C squared. I called A 8, so 8 squared. I called B 15 squared equals, I called C 17 squared. 8 squared is 64. 15 squared is 225. What's 17 squared?
17 raised to the second power is 289.
64 plus 245 is 289. And 289 equals 289. Is this a right triangle? Yeesh. 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 Long problem. Oh, where's my pictures? Where'd they go? Where'd they go? Easy. You'll have to be C because you're the longest. I'll call you A and I'll call you B. A squared plus B squared equals C squared. 14 squared plus 19 squared equals 23 squared. What's 19 squared? I know you're 196.
19 raised to the second power is 361.
What's 23 squared?
23 raised to the second power is 529.
196 plus 361 is going to be 557 equals 590, 29. Is this a right triangle? No, they are not. Fractions. Ugh, I hate fractions. Oh, I know what I'll do. Turn them into decimals. 9/10 is 9/10. 1 1/5 is 1.2. 1 1/2 is 1.5. That's supposed to be a 5. And yet it's not. Let me erase it. I'll call you A. I'll call you B. I'll call you C. A squared plus B squared equals C squared. If 9 squared is 81, then 0.9 squared is 0.81. If 12 squared is 144, then 1.2 squared is 1.44. And if 15 squared is 225, then 1.5 is 2.25. 81 plus 144 is 225. So 81 cents plus $1.44 is 225 cents, or 225. And look at that. It's a yesh. That's a bingo. Good movie. Not allowed to say the title of a movie because it's a curse word. Well, that's a lot of Pythagorean Theorem. You should be well equipped. Bye. Well, another day and another back to basics video that's going to make me like $1 or $2 total. Yeah, we'll see. Today we're going to talk about inequalities and how to deal with them, what they are, how to solve them. Well, what's an inequality, you ask? Well, an inequality is exactly what it sounds like. It means not equal. Now, I think a lot of people, when they think not equal, they might be thinking this symbol right there, and they're not too far from. I mean, that means is not equal to, but there's 4 other symbols that have to do with inequality, and they live right there. Let me that. First things first, we have less than or is less than. For example, 2 is less than 3. Simple. or we have greater than or is greater than. For example, 3 is greater than 2. Simple. Now, there are the other ones that kind of piggyback off of the previous ones that we did, and that's the less than or equal to, or the greater than or equal to, and that adds like a little I don't know, pizzazz, if you will, to the guys that we're dealing with. For example, I could take that 2 is less than 3, draw a little line underneath it, make it 2 is less than or equal to 3, and it's still a true statement. 2 is less than or equal to 3. You know what else? 3 is less than or equal to 3, because the word or gives it another possible option. Similarly, greater than or equal to, I could say the phrase 4 is greater than or equal to -1, and that is a true statement. Okay, that is a true statement. So how are we going to use this little number line down here? Haven't seen one of those in a while. How are we going to use that number line down there to solve or graph what an inequality is? What are we dealing with when we have inequalities in algebra? I'll give you an equation, or rather an inequality, and I'll give you a variable like x, and we might end up saying something like x is less than 3. What that means is x, our variable, could be any number smaller than 3, like 0, like 1, like 2, like 2.5, like 2.9, so on and so forth. So we make ourselves a number line, I don't know, -2, -1, 0, 1, 2, 3, 4, 5, 6, and we go to 3 and we put a nice little circle there. Now notice, this looks awful. Notice that I didn't fill my circle in. Because by saying is less than 3, I'm saying it's got to be smaller than 3, but not equal to. Okay. So since it's not equal to, I'm not going to fill in the circle for 3, because by filling in the circle for 3, that means I'm including 3, and I'm not including 3. What I am including are all the numbers smaller than 3. So I'm putting a nice, big, fat, terrible, ugly looking arrow pointing to the left of it. So all these numbers are here, over here, -1 and -2 and 0. All of those guys are factual in the fact that it is smaller than 3. So that's what an inequality looks like when it's graphed. So we'll do more. Otherwise, I could just sit here all day and talk about all the wonderful inequalities that we could graph. But let's just solve some first. How do you solve them? Well, you solve an inequality just like you solve a regular equation, but with 2 rules. If you multiply or divide by a negative number, you have to flip the sign. So as you can see right here, we have -3x is less than 12. How do I get x all by itself if I'm going to solve this like a regular equation? Well, I'm going to divide both sides by a -3. However, when you divide or multiply by a negative, you flip the sign. So x is now greater than -4. Wow. Amazing. Amazing. X is greater than -4. Now, I always like to put my variables on the left side. It's not necessary, but when I graph inequalities, if my variable's on the left side, the inequality symbol acts as an arrow. So if I were to take that guy and graph it, if this is a number line, and if I were to say that's -4, I would put a circle right at -4 and see how that it looks like an arrow pointing to the right. Well, I'll make that an arrow pointing to the right, and bada bing. That's why I like my variable to the left. So see how this guy is a variable not on the left? Well, if I want it on the left, you flip everything. Flip it all. Flip it real good. So if 9 is smaller than x, that must mean that x is bigger than 9. Well, that makes sense. If 9 is smaller than x, then x is bigger than 9. We flipped it all. We flipped it real good. So let's do a few. Let's solve a couple of these guys. We've got a two-stepper. My favorite type of dance. Is x all by itself? No. What do I have in the way? I have -4 being attached to x. I have 16 just floating around. If I am going to solve for x and get x all by itself, I'm going to always get rid of the guy that's floating around first. So I'm going to subtract 16. Uh-oh, a minus symbol. Does that mean flip the sign? Nope. Because you only flip the sign when you multiply or divide by a negative. So I have -4x. That drops down on the left side. The less than symbol is still less than. 24 minus 16 is 8. Is x all by itself? No. I have -4 being attached to x multiplied. So I'm going to divide both sides by a -4. I'm going to divide both sides by a -4. And since I divided both sides by -4, I'm going to flip the side. That's right. X is now greater than -2. So let's put -2 right there smack dab on the bottom, which means you're -1, which means you're 0, which means you're 1, which means you're -3, which means you're -4. I'm using this new pen. So if you're wondering, what's with all that clicking? It's the pen. And I'm starting to realize it's not that great. It's good, not great. Put a circle at -2. Why don't I fill in that circle? Because I'm not including -2. See how my variable's on the left? That arrow is pointing to the right. So if my possible solutions are everything greater than -2, then I'm going to say this graph represents all the possible solutions for the inequality given. My x values could be anything greater than -2, like 0 or a billion way over here. Okay? When you solve an inequality, you're trying to find all the possible solutions that match that inequality's answer. And in this case, the possible numbers that make this original statement true are anything bigger, but not including -2. Let's do another. This is fun. This is fun. I thought I clicked the button, and I must not have clicked the button. Oh, okay, good. Oh, I got scared there. Solve and graph. We've got 2 j's on the right side. So let's combine like terms right away. Combine like terms. I have 3 j's take away 5 j's. So that becomes -2 j's plus 15 on the right. 8 was on the left, and less than or equal to is just there. I'm going to solve this like a regular two-step equation. -2 is attached to j. 15 is floating around, so I'm going to subtract 15 from both sides first. Yes, I will. 8 minus 15 is -7. Is less than or equal to -2j. Is j all by itself? No. What is in the way? Well, -2 is being multiplied to j, so I have to divide both sides by -2. Hot dog, divide by a negative. Well, that means I take that less than or equal to sign and make it greater than or equal to. -7 over -2 is now positive. That becomes 3.5. So I'll make this 3.5, or you could just write out 3.5, or you can write it out as 7 over 2. Your call. J is now alone on the right. Now, I don't like my variable on the right side. So if I want to move my J to the left, I have to flip everything. 3.5 is bigger than J? Well, j is then smaller than 3.5. It's allowed to be equal to as well. Let's not forget that. Ooh, a half. Oh, that steams me. So I'm going to put a 3 right there. I'm going to put a 4 right there, and then all the others can just follow suit. Mr. Parrish, does it matter where you put your numbers on a number line? No. Just make sure that everything that you do can fit on the number line. So 3.5, last time I checked, is in the middle of 3 and 4. So I'll put a nice little circle there. And you know what? Not only is it less than, but it's also equal to, which means I get to fill that circle in. That's right. If it's or equal to, you fill the circle in. If the circle's filled in, it counts. Remember piecewise functions from 8th grade? Same thing. J is smaller than 3.5, so my possible solutions that make this original thing true are going to be everything smaller than 3.5. So I'm going to draw that graph right there. Right there. So my answer is J is less than or equal to 3.5. My graph is an arrow pointing to the left of 3.5 and including 3.5. Awesome. Feeling good? It's going to be a long video because I think I have 2 left, not 1. That's right. So let's fly through this. Let's mindlessly fly through it, shall we? I got distributed property. 2 times 4 is 8. 2 times 2x is 4x. That's going to be less than or equal to 6 plus 3x. Goodness gracious, variables on both sides of the inequality symbol. I guess we should handle that the same way we would an equation. Yes! I always like getting rid of the smaller one. So I'm going to subtract 3x from both sides because I can. That crosses out. Tappity, 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 says the new pen. X plus, 8. Look at me getting ahead of myself. 8 plus x is less than or equal to 6. Is x all by itself? No. What's in the way? Just an 8. So I'm going to subtract just that 8. And 6 minus 8 is negative 2. So x becomes everything smaller than or equal to negative 2. That's my answer. Now my graph, I'll put a negative 2 right there, which means you're negative 1, which means you're 0, which means you're 1, which means you're negative 3, which means you're negative 4, which means you're negative. All these negatives. If x is less than or equal to negative 2, I'm going to put a circle at negative 2. So there it is. If it's equal to, I'm going to fill that circle in. And I care about everything to the left, to the left, to the left, to the left. Cupid shuffle done. That's it. If you're wondering what that sound was, that was my ankle cracking because I am old. One more though. I think one more and then we can finally call it a day. Thank heavens. Distribute again? I can handle this. I have a master's degree in math. Nothing happens on the left, but on the right we get 4-H. What is this, a club for horses and farmyard animals? I'll skip 14. On the left, so on the right side, we end up with 2 times 2H is 4H. 2 times 7 is 14. And on the left side, we get 5 plus... Oh, this is so weird. I didn't think this was going to happen. 4H again. 4H on the left. 4H on the right. They just cancel each other out. So I'm going to subtract 4H from both sides. Minus 4H. Minus 4H. Goodbye, goodbye. And 5 is greater than or equal to 14. Now, wait a minute. I remember from equations that when my variables disappear, I have one of 2 options. And if my answer that I'm left with makes sense, it's infinite solutions. But the answer that I'm left with here, 5 is greater than or equal to 14. 5 is greater than 14? No. Equal to 14? No. This is not a true statement. It's fake. It's not a true statement. Which means my solution is there is no solution. You're telling me that there's no possible number that I can plug into this original inequality and get an answer? No. So what's my graph going to look like? Nothing. Because there's no solution. So if there's no solution, I can't have a graph that represents my solutions. It's blank. So just like equations, if my inequality gives me a false statement after my variables disappear, it's a no solution. If the tables were turned and this was 5 is less than or equal to 14, that would be an infinite solution. But that didn't happen. Now, did it? No. Well, that was a doozy. That one felt like a half an hour. It was fun, though. It was fun. It was a lot of fun. All right. Catch you on the flippity flip. Like and subscribe. Comment and stuff. I don't know. It doesn't ever work. Bye! What up, what up? Mr. Parrish here. No face in this video. I'm trying something new on my iPad to see if it works, see if it's any better quality, and I don't know. Maybe every now and then I'll just put pictures of my face reacting to things, or I'll figure something out. But today's Back to Basics video is going to be focused on compound inequalities. Compound inequalities. You know what compound means. Compound means two things in one, like a compound word, butterfly. Well, a compound inequality is you have two inequalities essentially taking up one problem, like this guy right there. Now, we have two types of compound inequalities. We have an and we have an or. We're going to start out with doing or. Now, what an or compound inequality means is I give you two situations, one or the other. In this case, we have x is less than 3 or x is greater than or equal to 5. If I order a pizza, right? You guys like pizza, and if the person's like, what topping do you want on it? And I'm like, sausage or pepperoni. If they bring me sausage, hey, that's great. If they bring me pepperoni, hey, that's fine. I'm okay with both. And so both can be represented on a number line, and I'm just fine. Well, that's what an or statement is. An or statement says that I can have both of these guys on the number line. So if I were to graph x is less than 3 in blue, let me get a couple numbers up in here. It looks like I can just start out with 1, 2, 3, 4, 5, 6, 7. So I'm going to put a circle at 3. Don't fill it in because I'm not including it. And I care about all the stuff to the left, so I'm going to fill like a nice big arrow to the left. If I want to do x is greater than or equal to 5, which I'll do in green, I'll go to my 5 right here. I'll put a circle. I'll fill that circle in because I'm including 5. The or equal to includes it. And I want everything greater than 5, so I'm going to go to the right, to the right, to the right. And that's my graph. That's my answer. So what this question is asking is, hey, pick a number that is smaller than 3 or bigger than 5, and including 5. So if I picked, I don't know, 1. Is 1 smaller than 3 or bigger than 5? Yes. What about 12 way over here? Is 12 smaller than 3? Well, no. But is it greater than 5? Yeah. And so since I use the word or, I'm alright to do that. So both graphs in an or statement are going to show up on my number line. Okay? So let's see what we got going on here. Solve and graph m minus 8 is less than negative 7, or negative 2m plus 4 is less than negative 2. So let's do one at a time. Let's do this left one. We get m by itself by adding 8 by adding 8. That crosses out. M is less than negative 7 plus 8, which is 1. Alright, that's the one guy. The other guy is m's not all by itself. I have a negative 2, I have a positive 4. Subtract 4 first. Minus 4, cross u out. That becomes negative 2m is less than negative 6. Right, I'm going to divide both sides by negative 2, divide by negative 2, and oh my goodness, I divided by a negative. Oh, I wish you could see my face. If I divide by a negative, you flip the sign. So negative 6 divided by negative 2 is positive 3. Bada bing. And remember, the thing that binds both of these is the word or in the middle. So my final answer is going to be m is less than 1 or m is greater than 3. That's my final answer. Now I have to graph it. So let me put a bunch of numbers here. Looks like I can do 0, 1, 2, 3, 4, 5, 6. I'll graph the purple one in purple. Put a 0, or a circle rather, at 1. Don't fill it in, because it's not equal to. Go to the left of 1, like so. Put a big arrow there, like so. Do the same thing with the green guy. Put a circle there at 3. Don't fill it in. M is greater than 3, so I want all the numbers bigger than 3, like 4, 5, 6, and positive infinity. And that's my answer. Pick a number that's less than 1 or bigger than 3. 0 or a billion. What I can't pick is 2 or 1.5 or 2.5 or 1. Because 1's not included. Alright, let's do it again, I guess. I don't know. Red, we've got 3x minus 1. So let's get rid of the guy floating around first. Let's add 1 to both sides, cross u out. 3x is greater than or equal to 9. Is x all by itself? No. What's in the way? 3. So let's divide everything by 3. Cross u out. X is greater than 3. I did it! I did it. How about dividing... Let me clean that up a bit. How about we divide everything by 4? Divide it by 4. X is now less than 6. So I got a 3 and a 6 there, so let's make a number line. I guess I could start at like 2, 3, 4, 5, 6, 7, 8. And the word that combines these is the word or, so x has got to be bigger than 3 or less than 6. Let me put a circle there. Oh, this is supposed to be greater than or equal to 3. Oh, that could have made a big mistake. Alright, so let's go to 3. Fill it in. X has got to be bigger than that, so I'm going to put a big arrow. I'll go into the right. For the green one, I'm going to go to 6. Don't fill it in, but it's kind of already filled in because that red guy right there is really filling it in. I'm going to the left of 6. Wait a minute. So if I was asked to pick a number bigger than 3 or smaller than 6, well, that's everything. Oh, it's the entire line. I didn't make a mistake. It's the whole thing. Oh. What about 5? Is 5 bigger than 3 or smaller than 6? It's both. Is 10 bigger than 3 or smaller than 6? Yeah, it's bigger than 3. Is negative 10 bigger than 3 or smaller than 6? It's smaller than 6. Any number, any of them, any number works. Oh, hooray. Hooray. Well, that's the yours. Now let's move on to the ands. With an and, both situations must be true. In the pizza situation that I brought up, if I asked for sausage or pepperoni and they brought me sausage, that's fine. If they brought me pepperoni, that's fine. But if I order pizza
and I ask sausage and pepperoni, well, I better have both. So this is how it's going to be a little different. I'm going to make my number line 1, 2, 3, 4, 5, 6, 7. And what I'm going to do is I'm going to, for the ands, I'm going to graph these above the number line. So 3 looks like that. Going to the right, I'm going to include 3 because it's greater than or equal to 3. 5, I'll do in blue, is a circle at 5, and x is less than 5, so it looks like that. So with the ands, what I want is the area where both lines overlap. And they overlap in between 3 and 5, but not including 5. So a number that's bigger than or equal to 3, but is also smaller than 5 is like 4. 3.5. And if you're like, but what about 6? 6 is bigger than 3. Yeah, but it's not also and less than 5. So with the ands, I care about things that qualify for both, which means my graph has to reflect that. Yeah? Alright. Here we go. Let's add 1. Add 1. 5x is greater than or equal to 10. Okay, divide by 5. Divide by 5. X is greater than or equal to 2. Distributive property 4x. 4 times 1 is 4. That's going to be less than 24. Let's subtract 4. Let's subtract 4. Cross u out. 4x is less than 20. Divide by 4. Divide by 4. And x is less than 5. So what I've got here is my solution is x is greater than or equal to 2. Come on, pen. Come on, pen. I'm counting on you here. X is greater than or equal to 2. And x is less than 5. So let me give myself a little bit more space. If I number these out, what do I have? 2 and 5. I can do 0, 1, 2, 3, 4, 5, 6. I'll put a circle at 2 and including 2. Go to the right. For my green one, I'll put a circle at 5, but not including 5. Go to the left. And my final answer is going to be that spot in between 2 and 5, and I'm allowed to include 2. But I'm not allowed to include 5. So my possible answers for these original inequalities are numbers in between 2 and 5, but not including 5. So 3, 4, 4.9, 2. What are my answers? I'm going to fight you if you don't believe me. No, I won't. I'd never do that. Ugh. Alright, so we've got ourselves a mess of a problem. Let's focus on one thing at a time. Zoom in. I know it's an and. I see that little a over there. That should do it. Alright, we got distributive property. 2 times 4 is 8. 2 times 2x is 4x. Less than or equal to 6 plus 3x. Variables on both sides. I like getting rid of the smaller ones, so let's subtract both sides by 3x. Let's subtract both sides by 3x, and 4x minus 3x is just an x. Well, look at that. Bring down the 8 plus. Bring down the less than or equal to. Bring down the 6. Bring down the house. You don't know what that is. Subtract 8 from both sides. Subtract 8 from both sides. Cross you out. X is less than or equal to -2. I did it. Well, I did that. Let's go to the other one. Pause if you need to see more. Let's go to the other one. Got 3x plus 5 is greater than 5. Ooh, I see something on the left that's the same as something on the right. I have a feeling that'll disappear. And look at that. I've got a feeling. Oh, I better stop before I get sued by the Black Eyed Peas. If I subtract 5 from both sides, everything kills each other out, so I'm left with 0. Cero en español. Divide everything by 3. And last time I checked, if I take 0 and divide it by 3, I get 0. So I have my... I tried to squeeze the screen and I made lines instead. Silly me. I've got my two guys, or gals, and what combines them, what connects them, is the word and. So I got -2 and 0, so let's make you -4, -3, -2, -1, 0, 1, 2. My and for green is going to be at 2 going to the left. My one for blue is at the 0, don't fill it in, going to the... Wait a gosh darn minute. If this is an and, there's supposed to be the part where both lines overlay, where the green touches the blue. Well, the green doesn't touch a blue. Well, let me think logically here. Let me think of a number that is smaller than -2, but also bigger than 0. Is there a number smaller than -2 and bigger than 0? No, 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 no. So what's my solution? There is no solution. None. So no graph. So a blank graph. We saw a blank graph in my previous video about solving regular old inequalities. Well, it's happened again. Back at it again. There's two ways that you can draw an and. Here's the other way. And what basically you're saying here is that -1 is smaller than blah, 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 which is smaller than 4. In other words, -1 is in between blah, 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 and 4. This is an and statement, because -1 is in between blah, 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 and 4. So what I could do is I could split this up into two and statements, or I could just solve. And whenever I solve, I do stuff to both sides. But wait a minute. Both sides? There's 3 sides. Ugh. So should I just... if I'm going to get y here all by itself, if I'm going to get y all by itself, should I subtract 9 from all 3 sides? Yup. -9, -9, -9. You become -10. You cross out. Drop down the less than, drop down the y. You become -5. So -10 is less than y, which is less than -5. In other words, y is in between -10 and -5. Y is in between -10 and -5. So let's make a number line that reflects that. Y is in between -10, -9, -8, -7, -6, -5, -4. Y is in between -10. Circle there. Should I fill it in? Nope. Because there's no and equal to or equal to. And -5, should I fill it in? Nope. The symbol here is just a less than symbol, not an or equal to. And y is everything in between -10 and -5. Ah, that's much friendlier. That's much friendlier indeed. I had one more. I do. -36 is in between 3w minus 6. I'm sorry, I should word that as 3w minus 6 is in between -36 and -15. So I'm going to solve by doing stuff to all three sides here. So is 3w, this guy right here, is 3w minus 6 all by itself, or is the w all by itself? No. I'm going to add 6 to both sides. Oh, I misspoke. All three sides. My face is just like this ink. Red. You can't tell, though. You can't tell at all. Let me see. You become -30. Less than 3w. Less than or equal to -9. Is w all by itself? No. I'm going to divide everything by 3. Everything. All three sides. And this becomes -10 is less than w is less than or equal to -3. And I have a feeling I don't have enough numbers to make this a proper number line. -10, -9, -8, -7, -6, -5, -4. Nope, just missed it. So I'll go by 2s. I'll do -12, -10, -8, -6, -4, -2, 0. I'm going to put a circle in at -10. I'm going to put a circle at -3, which is in between -2 and -4. I'm going to fill that circle in because this guy is a less than or an equal to, and I care about all the stuff in between. So what I'm being asked to do here is look at this original problem, find me w's that if I were to take 3 times that w minus 6, my number is going to be in between -36 and -15. Well, -8, -5, -6, -3. All these numbers in that green shaded area are possible numbers. And that, ladies and jelly spoons, will do it. It'll do it just fine. It was fun. Except my face isn't there. Oh well. I'll just... you'll make do. Although, having said that, I'm pretty sure, knowing myself, I put a video of my face on loop throughout the entire thing here so you wouldn't miss me. Oh, what a narcissist. That's it for me. Bye!
What up, what up? Today on Back to Basics, we're going to talk about solving equations where absolute variables are wrapped around my variable. It's not that bad. In fact, if I had enough time, this puppy dog right here could do it. Ugh. Couldn't you, Stella? Couldn't you? It's my dog. My dag. If you hear noises in the background, it's probably her. But anyway, I digress. Let's take a look at what an absolute value equation looks like. If I give you an absolute value wrapped around an x, and then some, okay? And I say the absolute value of x equals a, where a is a number, then I have two answers, positive and negative a. Now I know what you're thinking. No. Absolute value just makes numbers positive. There can't be two answers. Absolute value just makes numbers positive. Well, I have news for you. I'm not turning a number positive. I am trying to find out what makes this statement true. So what I'm doing is, if I were to say the absolute value of what number gives me 3, the absolute value of what number gives me 3? Well, I have two answers. The absolute value of positive 3 gives me 3. Oh, but you know what? The absolute value of negative 3 gives me 3. So, x is positive or negative 3. Yeah. Yeah. That makes sense. Dollars and cents. So my goal here is to solve these equations using a method like this. Well, are they all going to look like that? The absolute value of x equals a, and that's it? No. They're going to be a little bit more complicated, like this guy. I think she's chasing a kitty cat. Can I squeeze my face in? Can I squeeze my face? Can I squeeze it? Can I squeeze my face? That's not it. What if I hit that? No, that's a mirror. There we go. All right. What do I do? Well, first off, if my job is to solve for an absolute value or a variable wrapped inside an absolute value, I need to get the absolute value all by itself. So step number 1 here is, although I want to distribute, you can never distribute into an absolute value. Don't do it. It's against the law. Okay, so I'm just going to divide everything by 3. And dividing everything by 3, I get rid of that 3 right there. And so I'm left with the absolute value of x minus 1, close absolute value, equals regular old 3. Now, once I get the absolute value all by itself, what I want to do is get rid of the absolute value, just like we saw back here. I'm going to get rid of the absolute value, but make the right side positive or negative. So I'm going to get rid of the absolute value. There it is. I'm going to make the right side positive or negative. Now, what this is saying is x minus 3 equals x minus 1 equals positive 3, or x minus 1 equals negative 3. So I'm going to split it in two equations. X minus 1 equals positive 3, or x minus 1 equals negative 3. Let me see if I can squeeze that. I did. It looks terrible, but there you have it. Add 1 to both sides. Let's take care of red first. Add 1 to both sides. Add 1 to both sides. So x equals 4. And let's take care of blue. Add 1 to both sides. Add 1 to negative 3. And x equals negative 2. So my answers are 4 or negative 2. That kind of makes sense. If I were to take 4 and plug it into the original equation, I would get 4 minus 1, which is 3. The absolute value of 3 is 3. 3 times 3 is 9. And I could do the same thing with negative 2. Negative 2 minus 1 is negative 3, but the absolute value of negative 3 is 3. Times 3 is 9. And those are my two answers. Bada bing. So isolate the absolute value. Get rid of the absolute value. Attach a plus or minus to the right. And then split it into two equations and solve each of them. Don't forget the or in the middle. It is a lot of steps, but I shall guide you. Step number 1, make sure the absolute value and the stuff inside it is all by itself. Well, good news, everybody. It is. The absolute value is all by itself. Now, I have a bunch of junk inside of it, including negatives. Should I get rid of those negatives? Absolutely not. Absolutely. Oh my goodness, a new friend is joining me. Hello. Oh, this is Pete the cat. She's a girl. Mwah. Oh boy, all my friends are just paying me a visit today. What's next, the mailman? I just won't give him as many kisses. Oh, it's the 2020s, kids. We're allowed to get away with that. All right, so my absolute value is all by itself. I'm going to get rid of the absolute value and make the right side positive or negative. So get rid of the absolute value and make the right side positive or negative. Positive or negative 20. So what this is saying is I have negative 4 minus 2g equals 20, and I have negative 4 minus 2g equals negative 20. So I have two separate equations that I have to solve for. Negative 4 minus 2g equals 20, and negative 4 minus 2g equals negative 20. I'm going to solve each of them individually. So let's add 4. Clickety-clack goes my pen. Minus 2g equals 24. Is g all by itself? G, I don't think so. So I'm going to divide both sides by negative 2. I'm going to divide both sides by negative 2. And g equals negative 12. That's my first option. My second option is going to be add 4. Oh, yeah, just like we did in the other one. Bring down the negative 2g. That's negative 16. Divide by negative 2. Oh, yeah, just like we did in the other one. G equals 8. So my other option is G equals 8. There's an OR, and that's my answer. So if I were to plug in negative 12 into this original equation, multiply negative 2, take away 4, I get and then absolute value, I'd get 20. If I were to plug in 8, multiply by 2, I have a negative 2 actually, subtract 4, absolute value of that, I also get 20. All right. Yes? They're fighting. I hate it when they fight. The cat and the dog, they just get along like them. Is the absolute value all by itself? No. So I'm going to add 5 to both sides to get the absolute value by itself. There you go. Absolute value of k plus 8 equals 7 equals 7. And then I'm going to take away the absolute value. Make the right side positive or negative. So let me do that. And split this into two equations. My two equations are k plus 8 equals positive 7, or k plus 8 equals negative 7. I'm going to subtract 8. I'm going to subtract 8, cross u out. K is going to equal negative 1. I'll put that way down there. Over here, I'm going to subtract 8. Subtract 8, cross u out. K equals negative 15. I'm going to put that there. I'm going to put the OR in the middle. I'm going to put a big, wide box around it, and I'm done. I'm done. Because if I take negative 1 and say negative 1 plus 8, I get negative 7. I'm regular 7. Absolute value of 7 is still 7, and 7 minus 5 is 2. And I could do the same thing with negative 15, and I'll be good. But what I did while my rude pets interrupted is I subtracted out the 5 because I had to get the absolute value all by itself. Did the plus or negative thing, split it up into 2 and solve each. Split it up into 2 and solve each. Split it up into 2 and solve that one and that one. I'm feeling pretty good about this. So good that this will be my last one. Now this is a mess. But just like life, when you're given lemons, forget it. What a mess. I'm going to add 2 to both sides. I have a positive 2, or a negative 2 rather, and that negative 5 making it so that my absolute value is not alone. I'm going to always get rid of the number floating around first, and in this case I'm going to get rid of it by adding 2 to both sides. So that leaves me with 20 over here. That's supposed to say 20. That's supposed to say 20. Perfect. Now on the left side, I have negative 5 times the absolute value of 3 plus 4t. The absolute value is still not by itself, so I'm going to divide everything by negative 5. I'm going to divide everything by negative 5. And so I am left with the absolute value of 3 plus 4t equals negative 4. Now Stella is going to help me out with this one. Stella, what number must I plug in to that t so that when I take the absolute value of stuff, it gives me negative 4? What's that? What? The absolute value will never be negative? Wait. So if the absolute value of a number equals negative, it's literally impossible because the absolute value always has to be positive? Yeah, that's what she said. Stella, the dog. Not me accidentally quoting The Office. Guess what, ladies and jelly spoons? This is a no solution. Where's my pen? This is a no solution. Why? Because there is no such number that when I take the absolute value of it, I will get a negative. Nothing. There's no such number. So, can I add? I know what I'll do. I'll zoom in and create my own brand new screen. So close. Good. If the absolute value of x equals a negative number, no solution. Because no matter what number I choose, the absolute value of it will be positive. That's it. So, pretty tricky stuff. Impossible? Certainly not. And I may have ventured into the realm of Algebra 2 just a little bit here. Instead of doing more Algebra 1-y things, but hey, I like to have a good time. I like to live life dangerously, and Algebra 2 is a dangerous beast, like my mother-in-law. Well, that's that. I had fun. Like and subscribe. Bye. What up? Today, on our adventure of Back to Basics, we're talking about absolute value inequalities. Now, in a previous video, we talked about absolute value of equations, which were Now we're going to talk about absolute valuable inequalities. They are valuable, but we're going to talk about absolute value inequalities, and they're worse. So enough chit-chat, because I can't really do that too well. This is my brainchild. I'm a wordsmith, as you can clearly see from about 30 seconds ago. I created a foolproof system to help you remember how to do these problems, and it's called greater less than. Now, what greater less than is... My puppy's back. If you didn't see my last video, lots of puppy in that video. Her name's Stella. Greater less than says this. If I have the absolute value of blah, blah, blah greater than a number, then what I'm going to do is I'm going to split it up into two parts where I keep the entire equation exactly as is, or I flip everything less than the negative version. Okay, so if I'm given absolute value of stuff is greater than... How do we screw this up? Come on, I just want to make you smaller. There we go. If I have the absolute value of stuff is greater than a number, I split it up into two equations where I keep one exactly the way it was, just no more absolute value. I have the word or. And then I keep the left side the same, flip the sign, and then make it the negative version. Similarly, if I have the absolute value of stuff is less than a number, less than, I'm going to write out the original equation exactly the way it was, just no more absolute value, and then I flip the sign to make it negative. So I never said it would be easy. I just said it would be fun. So let's have some fun, shall we? We have a less than, which means it's going to be an and problem. I'm going to isolate the absolute value. Oh, look at that. It already is. I'm going to rewrite the equation exactly how it was at the very beginning. 3x is less than 9. Since it's an and, I'm going to write out and then I'm going to write out the second equation, inequality, I guess I should say. It's not equation. 3x, flip the sign, make the 9 negative. Okay? I solve each one individually. Divide by 3. Divide by 3. X is less than 3. I solve the right one. Divide by 3. Divide by 3. X is greater than negative 3. And this is the word and. Now you may remember from the video 2 videos ago with regular old compound inequalities. When I make a compound inequality, let me get a couple numbers here. What do I have? 3 and negative 3. Could I make that work? Negative 3, negative 2, negative 1, 0, 1, 2, 3. Negative 3, negative 2, negative 1, 0, 1, 2, 3. What I do is I graph each one separately. If it's an and, I graph each one separately. Notice that I'm not filling in the circle for 3 because it doesn't count. And I'm going to do greater than negative 3, so I'm going to put the circle here. Terrible line drawing by me. Good thing I'm not a tattoo artist. But since this is an and graph, I care about everything in between. So I am going to put a circle at negative 3, but not fill it in because it's not included in both. And I'm going to put a circle at regular 3 and not fill it in because it's not included in both. But what is included in both is everything in between. Yeah. So pretty much the original problem is saying the absolute value of 3 times what is going to be smaller than 9? Well, 3 times 0... 3 times 1, the absolute value of that's smaller than 9. 3 times negative 2 is going to be negative 6, which the absolute value is smaller than negative 9, regular 9. So, yeah. So as long as things go well, the less thans are going to deal with stuff in between most of the time. Most of the time. Not all the time. So I even hesitate saying that phrase, but I said it. Great or less than. Well, this is a great or problem. And so what I do is I isolate the absolute value, already done. I'm going to rewrite the original equation just without the absolute values. There you go. I'm going to write out the other one where I rewrite out the left side. Oh, I wanted a different color. I'm going to rewrite the left side, no absolute value. Flip the sign, make it negative, which means negative, negative 1. So positive 1. And this is great or. And then I solve each one individually. Okay? 2 times x minus 5 is greater than negative 1. Well, let's add 5 to both sides. Let's add 5 to both sides. Cross u out. 2x is greater than 4. Let's divide by 2. Let's divide by 2. And I've got x is greater than 2. Or add 5, cross u out. 2x is less than 6, divide by 2, and x is less than 3. That took me a second there, and I'm not sure why. Now with the ors, I could just graph both lines on the same line. So I'm going to graph x is greater than 2. Let me number things out. I have 1 and 3, so I'll just put 1, 2, 3, 4, 5, blah, blah, blah. X is greater than 2 means I put the circle at 2. Don't fill it in. Go to the right. X is less than 3 means I put the circle at 3. Don't fill it in, go to the left. Well, wait a minute. With the double arrows and with the ors, I'm supposed to include everything on that line that the line touches. So since one starts here, the other starts there, and they overlap and completely cover each other, what I'm going to end up with is the entire number line. That's right. What this means is I can pick any number and plug it into that entire equation, and it'll be true. Any number. 5, 12, negative affinity. And this makes sense because this is saying the absolute value of blah, 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 blah has to be bigger than negative. Well, the absolute value of anything is positive. So the absolute value of whatever I choose is going to be greater than negative 1. Ah, that's why it makes sense. That's why it makes sense. Don't just do the math, kids. Understand the why. Of course, whenever I do this, she stops doing it. So is the absolute value all by itself? I don't think so. So I'm going to add 1 to both sides. That's going to be my first step, step number 1. The absolute value of 9x is greater than or equal to. Is that going to change anything? No. So I have absolute value, blah, 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 greater than, or equal to 9. So this is an or, which means I'm going to write out the original equation or the original inequality without the absolute value, or I'm going to write out the original left side, flip the sign, and make it negative. Yeah. You solve each one individually. 9x is greater than or equal to 9. Well, I'm just going to divide everything by 9. I'm just going to divide everything by 9, and that gives me x is greater than 1 or equal to 1. X is greater than or equal to 1. And I'm going to do this guy where I'm going to divide both sides by 9, divide both sides by 9. X is less than or equal to negative 1. I got my or in between. So I'm going to graph each one both on the line. So x is greater than or equal to 1. So let me do negative 3, negative 2, negative 1, 0, 1, 2, 3. If I'm going to graph the red one, I'm going to put a filled in circle at 1. Go to the right. And if I'm going to graph the green one, I'm going to put in a filled in circle at negative 1. Go to the left. And there you have it. There you have it. Okay. I think I have one more. I thought correctly. Stuff to do before I even consider splitting things up. I'm going to subtract 1 from both sides. That gives me 2 divided... Oh, great. I gave myself fractions. Wow. Oh, well. Divide by 2. Oh, my gosh, Stella. Divide by 2. Cross you out. This gives me the absolute value. Come on, the the absolute battery died. The absolute value of 2y minus 1 is less than negative 5.5, and we'll leave it as a decimal. Now, I'm kind of crossing into Algebra 2 territory here. This is pretty difficult for Algebra 1, but I believe in you. I believe in me. I believe in us. I believe in we. I made that up just now. I'm going to split this up into two equations. This is a less than. So I have a big and hovering around. I'm going to write out 2y minus 1 is less than negative 5.5 and 2y minus 1 is greater than the negative version of negative 5.5, which is 5.5. I solve each one individually. All right, I add 1. 2y is less than negative 4.5. I divide by 2. I divide by 2. And y is less than negative 2.25. Gross. I add 1. I add 1. Let's keep going. I meant to make it purple. 2y is greater than 6.5. Divide by 2. Divide by 2. Y is greater than 3.25. And I know what's going to happen. Let's just I'll tell you what. Let's just do it. I have all right, so I can yeah, watch what I do. This ain't gonna be pretty. Negative 3, negative 2, negative 1, 0, 1, 2, 3, and I'm gonna add 4 right there. Why? Well, this guy says that since this is an and statement, I'm going to put a dot at negative 2.25, which lives right around there, and I'm going to go to the left, don't fill it in. And I'm going to put a circle for this guy, for purple, right around there, don't fill it in, go there. And I need to find out where these two lines overlap. Oh, what's that? They don't overlap? Oh, you know what that means. This is a NAR solution. Why? Because once I get to this point right here, I ask you, the absolute value of what times 2 minus 1 is going to be smaller than negative 5.5. Well, the absolute value of nothing is ever going to be smaller than a negative because the absolute value of something has to be positive. So this is a no solution because there's no such answer that makes sense. There's nothing I can plug in that when I make it positive, it will be less than negative 5.5. That doesn't make sense. That's wacky. It's best to understand the why. And now that joke lands a little bit harder because I understand the why and it's no solution because the letter is Y. Sully, you want to say goodbye to everybody? If this is the first time you howl on screen, this would be the best. Say bye. Bye. All right, graphing points on just quadrant 1 of a coordinate plane. Quadrant 1 means all of my ordered pairs are going to be positive x value, positive y value.
Your first number tells you where you go left or right. In all of these cases, I'm going to go right. So A, which is 2, 5, is going to be right 2, and then the second number tells you where to go up if it's a positive number. So A is 2, 5, which means I go right 2, up 1, 2, 3, 4, 5, put a dot, call it A. B is 6, 1. So I'm going to go right 1, 2, 3, 4, 5, 6 because it's a positive X, and go up 1 because it's a positive Y, call it B. And C is 0, 7. So 0 means I don't move, but the 7Y value means I go up 1, 2, 3, 4, 5, 6, 7. And that's my C.
Back to basics. What's slope? Well, slope is how steep a line is. How steep a line is. If I give you a line, slope is going to tell us how steep that line is. The larger the number, the steeper the slope. So, the way we calculate that is a little fraction called rise over run. Positive slopes go up and to the right. Some people might consider that also down and to the left. Negative slopes go up and to the left. Some people might consider that down and to the right. Zero slope is perfectly horizontal, like that. And an undefined slope is a slope of a line that goes up and down. So let's do a few problems. If I'm defining this slope, what I have to do is I have to find the rise over run. So the first thing that you do is determine if it's positive or negative first. This is a positive slope because it's going up and to the right or down and to the left. So positive. Remember that in my head, positive. Now I'm going to figure out what it takes for me to get from one dot to the next dot. I'm going to rise 1. So my slope so far is 1. And I'm going to go over to the right 1, 2. So up 1 over 2. 1 over 2. That's it. My slope is positive 1 over 2. Done. Let's do it again. This is going to be a negative slope. So let me see. So I'm going to put negative, and that's going to be my fraction bar. I'm going to figure out what it takes to get from one dot to the next dot. And it really doesn't matter which dot you choose, which one you start out with. So I'm going to go up 1, 2. So my rise is 2. And I'm going to go over 1, 2. Negative 2 divided by 2. Can I simplify that? Oh, yeah. Negative 2 divided by 2 is negative 1. With these guys, what you're going to want to do is simplify them, but keep them in proper. Simplify the fractions, but keep them in proper. Okay? Oh no, I don't have dots. Maybe I'll just make them. So let me see. I could put a dot there. And I could put a dot there. Is that positive or negative? Negative. So I'm going to put negative. And here's my fraction bar. What does it take to get from one dot to the next dot? Again, it does not matter which dot you start out with. I'm going to go down 1, 2, 3, 4, 5, 6. So down 6 over 1, 2, 3, 4. Negative 6 over 4. Oh yeah, I can simplify that by dividing both of those numbers by 2. So 6 divided by 2 is 3. 4 divided by 2 is 2, and it's negative. Simplify it, but keep it improper. There's several dots that I could have put on this graph. I could have put a dot there, could have put a dot, I could have put a dot there. But those are the two I chose, and that's probably why I didn't get a simplified answer right away. All right, where can I put dots over here? I could put a dot right there. I could put a dot there. Positive. So here's my fraction.
up 1, 2, 3, 4. Over 1, 2, 3. And my slope is, as you can see, clearly positive 4 over 3. Simplify it, but keep it improper. So 4 over 3 is like 1.3. Negative 3 over 2 is negative 1.5. So that slope is just a little bit steeper than the one on the right. Okay? The larger the number, the steeper the slope. What if I don't give you a graph, though? Well, if I give you 2 points instead of a graph, what you're going to do is you're going to label each point, call them x sub 1, subscript, y sub 1. Call the other point x sub 2, y sub 2. I take those points and I plug them into this formula right here. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So if I'm given 2 points instead of a graph, I label the points and plug them into that red formula right there. This is called the slope formula. Very, very, very important formula. So let's try it out. Find the slope connecting those points. So step 1 is label the points. X sub 1, y sub 1, x sub 2, y sub 2. I'm going to write out the slope formula in full. I like to write out the formula every time. The slope formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Now what I have to do is replace the y sub 1 and the x sub 2s and all of those with the letters that, or the numbers rather, that I have there. So y sub 2 is negative 4. So instead of y sub 2, I'm going to write out parentheses negative 4. I'm going to write out the minus sign that was there. And instead of y sub 1 is 7. So I'm going to replace y sub 1 with 7. Divided by x sub 2, according to what I labeled, is negative 6. So I'm going to replace x sub 2 with negative 6. I'm going to write out that minus sign. And I'm going to replace x sub 1 with negative 4. Like so. Now I simplify. Negative 4 minus 7 is negative 11. Negative 6 minus negative. Ooh, a double negative. Whenever you see a double negative, make the double negative a plus positive. So negative 6 plus 4 is negative 2. I can take it one step further. A negative over a negative is a positive. So negative 11 over negative 2 is positive 11 over positive 2. And that's my answer. Simplify it. Keep it improper. We don't want mixed numbers here. I want to be able to look at that and say, if I were to graph that, I'd put a dot and go up 11 spaces and go right 2. Let's do 2 more, speaking of 2. Find the slope connecting the points. All right. I'm going to call you x sub 1, y sub 1. And I'm going to call you x sub 2, y sub 2. I'm going to write out my slope formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Instead of y sub 2, I'm going to write out 16 because I called y sub 2 16 up there. Minus is minus. And instead of y sub 1, I'm going to write out 20 because, I'm sorry, not 20, 8, because y sub 1 is 8. If I put 20, that would be a completely wrong answer. Instead of x sub 2, I'm going to write out 9 because that's what I labeled up there. Minus is minus. And instead of x sub 1, I'm going to write out 20. There's my 20. It's also what I said when I found a $20 bill on the floor this morning. Just kidding. I only keep hundreds. 16 minus 8 on the top is 8. 9 minus 20 on the bottom is negative 11. A negative divided by a positive, or in this case, rather, a positive divided by a negative is a negative, so that simplifies out to negative 8 over 11. 8 over 11 can't change, but that negative can come out. It just looks better that way. One more. X sub 1, y sub 1. Step 1, label your points. X sub 1, y sub 1. X sub 2. Interesting. Y sub 2. The next step is to write out your formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Y sub 2 is 8. Minus is minus. Y sub 1 is negative 13. X sub 2 is 17. Minus and minus. X sub 1 is 17. Very interesting. Double negative. 8 plus 13 is 21. And 17 minus 17 is 0. What happens when you divide by 0? You can't divide by 0. It's undefined. Oh. I wonder if I could have figured out by looking at the original problem that it was undefined. Oh yeah. See how x is 17 and x is 17? If the x's are the same exact number, your slope is going to be undefined. If the y's are the same exact number, if these guys would be the same exact number, then the slope would be 0 because the 0 would show up on top. All right. Well, that's it for slope. Those are some shortcuts to end there. Bye. Back to basics. Let's talk about graphs and how to graph graphs on a graph. Let's do it. I think that's all we're doing today. We're just going to graph a bunch of lines. How do I know it's a line? Well, because it's in the form y. Well, how do I know it's a line? Well, because it's in the form y equals mx plus b. And anything in the form y equals mx plus b is going to be a line, where m is my slope and b is my y. There's a lot of lag here. B is my y-intercept. All right. What does that mean? Well, that means my slope is negative 1/3. But that's not where I start. Where I start is my y-intercept, which is positive 1. Again, there's a lot of lag here. So I start at positive 1, and my positive 1 is a y-intercept. So it would only make sense to put a dot on the y-axis, which is right there. Not the one on the right, the one on the y-axis. The one on the right would be the x-intercept, and that's not what I'm doing. Now I take my slope. My slope is negative 1/3. Negative slopes look like that. If it's 1 over 3, that means I literally go up 1 over 3, up 1 over 3, up 1 over 3, and I'm going to go up 1 and left 3, up 1, left, I can't do it anymore, so I'm going to go back to my original point and go down 1, right 1, 2, 3, put a dot there, go down 1, right, 3, up, can't do that either. I have 3 dots, and I can connect those dots by drawing a perfectly straight line. Okay, so if y is all by itself, the number in front of x is the slope, and the number floating around is the y-intercept. And that's what I did. And I graphed according to that information.
Shall we do it again? Shall we do it again? Shall we do another one? Oh my goodness. All right. Here we have something in the form y equals mx plus b. M stands for our slope. So what's our slope? Our slope is 7/4, positive 7/4. Yeah, I don't know what's going on with my computer today. My y-intercept is -3. So where I start is with the y-intercept. Start with the y-intercept. Put a dot at -3 on the y-axis, which is down here. Not the one on the left, down there. My slope is positive 7/4. Positive slopes look like that. And I do rise over run. So up 7, right 4, up 7, right 4, up 7, right 4, rise over run, up. So I'm going to my green dot and I'm going to count up 1, 2, 3, 4, 5, 6, 7, and I'm going to go right 1, 2, 3, 4, and put a dot there. And since these numbers are pretty big, those are the only dots that I can put on the graph. Once I have enough dots, or all the dots that I can draw, I draw a straight line through those dots. And there you have it. There you have it. Let's do another one. Hey, it worked. All right. So is y all by itself? Yes. So when y is all by itself, I can compare it to y equals mx plus b, where m is my slope. So my slope is 1/2. And b is my y-intercept, 3. I start with my y-intercept. I put a dot at 3 on the y-axis, which is that guy right there. Then I start at that dot, and since my slope is positive 1/2, I go up 1, right 2. So I go to that green dot, and I'm going to go up 1, right 2, put a dot. Up 1, right 2, put a dot. Up 1, oh, I can't. So I'm going to go back to my original dot, and I can go in the complete opposite direction, which is down 1, left 2, put a dot. Down 1, left 2, put a dot. Down 1, left 2. Up, I ran out of room. So I have 5 dots there, and I always like to draw as many dots as I can. That way, if I screw up a dot, I know I did something wrong. It's better to be safe than sorry. Once you have all the dots that you can, you draw a perfectly straight line through all those dots, and you have yourself y equals 1/2 x plus 3. I think we have one more. Maybe not. I have y equals 4x minus 4. Is y all by itself? Yeah. So what do? Well, I write out y equals mx plus b, and I'm going to compare the two. What that means is my slope is 4. But you know what? If slope is supposed to be rise over run, I'm going to turn 4 into a fraction. So 4/1. My slope is 4/1. What's my y-intercept? -4, because there's a negative in front of that 4. So where do I start? I start at -4 for my y-intercept, which is down here, not the left one, on the y-axis. See that y at the top? You're going to put the -4 there. My positive 4/1 means I'm going up 4, right 1, up 4, right 1, up 4, right 1. This is a positive slope. So I'm going to draw as many dots as I can. Up 1, so I'm starting at the green dot that I drew out. Up 1, 2, 3, 4, right 1, put a dot. Up 1, 2, 3, 4, right 1, put a dot. Up 1, oh, I can't. And I'd love to go to that green dot and go down 4, left 1, but I can't. I have 3 dots, and that's really all I need to draw myself a straight line. So let's see what I have next. I have myself an equation that is not solved for y. So what do I do if my equation's not solved for y and I'm asked to graph? How about you solve it for y? So I have x plus y equals 3. I'm just going to write that out. Is y all by itself? No. What's in the way? X. Anything else? Nope. How do I get rid of x? subtract it from both sides. Cross u out. I can bring down the y. On the right side, I have 3 and I have negative x. 3 and negative x don't combine. Now, am I going to write out 3 minus x? I could, or I could put the negative x first, and since that's a positive 3, put a plus 3. Is y all by itself now? Yeah. So what do? Compare it to y equals mx plus 3. This is the tricky part. The number in front of x is not there. It's just a negative symbol. So negative what? Well, negative 1. Now, is that a fraction? No. So how can I turn negative 1 into a fraction? Make it negative 1 over 1. So that's my slope. Negative is negative 1 over 1. What's my y-intercept? 3. I accidentally wrote it out instead of saying b. Silly me. Where do I put my dot? Start at the 3 up here. My slope is negative 1. So I can go up 1, left 1, up 1, left 1, up 1, left 1. Uh-oh, ran out of room. What else could I do? I'm going to go back to my purple original dot and go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. So many dots. Now that I have all those dots, I can draw my perfectly straight line like I'm really good at. I'm getting better. I mean, it's straight. It's not perfect, but it's in the right direction. Now we're at our last one, and easily the worst one yet. So I'm going to move my face up there, and I'm going to rewrite this equation up here. What am I doing rewriting this equation up there? Well, it's definitely not solved for y. It's not even close to being solved for y. Not even close. So what I have to do is get y all by itself. Once I get y all by itself, then I can say y equals mx plus b and figure out what my slope is and what my y-intercept is. But it's important to know that if y is all by itself, you're not allowed to look at the numbers that you have and say, that's my slope and that's my y-intercept. You're not allowed to do that. So is y all by itself? No. What's in the way? Negative 5x. What else is in the way? 4. Which one should I get rid of? Negative 5x. How do I get rid of negative 5x? I add 5x to both sides. Add 5x, add 5x. That crosses u out. On the left side, I have 4y. On the right side, I have a negative 16 and a positive 5x. A negative 16 and a positive 5x. Do they combine? No. What should I write out first? 5x. Why? Because if I'm going to compare it to y equals mx plus b, I want the x part first. So I have 5x, and then I have a positive 16. They don't combine because 5x has an x and 16 doesn't. Is y all by itself? No. What's in the way? 4. How is 4 in the way? It's being multiplied. How do I get rid of 4? Divide it. So I'm going to divide every piece by 4. Divide every chunk by 4. Cross u out. Is y all by itself now? Sure is. 5 over 4 is going to stay 5 over 4 because when I'm talking about slope, I want to keep my fraction improper. Simplify it if you can, but keep it improper because I don't want to make it mixed number. Remember, slope is rise over run. It's not a number in front of rise over run. So I have 5 over 4 x plus 16 over 4. Can I simplify 16 over 4? Of course I can. It's 4. So now I can compare that to y equals mx plus b, where my slope is 5 over 4 and my y-intercept is regular 4. Where do I start? At my y-intercept, at 4. Should I put a dot on the right 4 or on the up 4? The up 4. What's up 4? I don't know. What's up, dog? Nothing much, homie.
All right, so that's my black dot is my y-intercept. Now I'm going to look at my slope and put more points there. My slope is positive, which means I go up and to the right or down and to the left. So if it's rise over run, it's going to be up 5, right 4, up 5, right 4. No, I can't go up 5. So I can go down 5, left 4, down 1, 2, 3, 4, 5, left 1, 2, 3, 4, put a dot. Obviously, I can't do it again because I don't have enough space. But if you're drawing a straight line, all you need are 2 dots. All you need are 2 dots. Dots. 2 dots are all you need. Beatles. Well, very important section. Graphing lines isn't going to go away anytime soon, so we need to know how to do that. And that's how we graph lines. We did 6 of them. 4 of them were easy. 2 of them were not. That's going to do it, though. Bye! Back to basics, back to basics, back to basics, back to basics. Today we're going to talk about writing equations of a line when I give you that line. Now the directions here say write each equation in slope-intercept form. Okay, well, what's slope-intercept form? Let me see if I can remember. Slope-intercept form is y equals mx plus b. Y is always y. M is slope. And b is the y-intercept. So it seems to me that what I have to do is I have to find out my slope, find out my y-intercept, and just kind of throw it in that red equation there, and then I'm done, right? Right. So let's find out my slope first. My slope requires me taking 2 points on the graph and figuring out the rise over run. I have 2 points, so that makes life easy. And it's positive. And the way I get from one point to the next point is I go up 1, 2, 3, 4, 5, 6. I rise 6 and I run 1, 2, 3. So my slope is rise 6, run 3. Now the thing with slope is if you can simplify it, but if you can't simplify it enough, keep it improper. 6 over 3 simplifies to 2. So my slope is 2. My y-intercept is the point where my line crosses the y-axis. Here's my y-axis. My green line crosses right there at 0, 4, or just 4. So my y-intercept is 4. So y equals mx plus b. I just found out that m is 2, so y equals 2x, and b is 4, so positive plus 4, that's my equation. Let's do another one. Write an equation in slope-intercept form. Okay, so I'll do it again. Y equals mx plus b. M is the slope. So let's find out what the slope is. Let's pick 2 dots. Here's a dot. These are weird looking graphs, but it's still the same thing. It just says 6.0 instead of 6. I don't know why. Maybe they think they're computers. I go up 1, 2, 3, 4. I can go left 1, 2. So my slope is negative 4 over 2. Negative 4 divided by 2. Can I simplify that? Yep, simplifies to negative 2. My y-intercept is the point where my line crosses the y-axis. So let me see. My red line crosses the y-axis right there. Where is that? In between 4 and 6, so it's going to be 5. So my y-intercept is 5. So putting it all together, y equals m is negative 2, x plus b, and b is positive 5, so plus 5. Y equals negative 2x plus 5. Where are my dots now? Where are my dots now? Well, let's pick a couple of them. I could put a dot here, and then I can put a dot here. Y equals mx plus b. M is my slope, so my slope is negative. I go up 1, 2, 3 over 1, 2, 3, 4. So my slope is negative up 3 over 4. Can I simplify that? No. My b is the y-intercept. Where does my line cross the y-axis? Right there at 4. So b is 4. When I put it all together, I write out the red. Y equals m? No. M is negative 3 over 4 now. M equals negative 3 over 4x plus b, which means plus positive 4, so plus 4. Another weird graph. Okay, I can do it. I believe myself. Y equals mx plus b. M is my slope, so here's 2 dots. Every big chunk is 1. So if I go up 1, 2, every big chunk is 1. So it's up 2 over 1, 2, 3. So my slope is positive up 2, right 3. Positive 2/3. My y-intercept is going to be that 4 right there. So when I put it all together, I could say y equals 2/3 x plus b, which is 4. Seem to be getting faster at these as I do more of them. I'm getting better, I guess. I don't know. Which equation, write each equation in slope-intercept form. All right, I can do this. Y equals mx plus b. M is my slope. So let's pick 2 dots. There's 2 dots there. I go up none, and I go over 1, 2, 3, 4, 5, 6, 7, 8, 9. So my rise is 0, and my run is 9. Weird. What's 0 divided by 9? Oh, 0. That's right, I forgot horizontal lines have slopes of 0. Okay, so my slope is 0. Easy. Where does my line cross the x-axis? Y-axis, right there at 5. So my y-intercept is 5. So putting this all together into that green or that blue equation over there, I have y equals 0x plus 5. Well, I can simplify that a little bit further. 0x just disappears. So I'm left with y equals 5. And that makes sense because no matter what on this line right here, y is always going to be 5. Y is always 5. Y is 5. Why? Because I said so. Bye. Back at it again with basics. Darn, Daniel, back at it again with basics. What I'm doing here is similar to what I did in the last Back to Basics, which was called writing equations or writing linear equations using graphs. Well, what if I'm not given a graph and I'm being asked to do the same thing? The directions here are exactly the same as the previous Back to Basics video, but in this case, I'm not given graphs. I'm given something different, charts, points. I don't know. I guess I'll find out. Well, this is where we're going to have to be a little creative. Okay, slope-intercept form is y equals mx plus b. M is the slope. By definition, slope is rise over run. I don't have a picture, so I'm going to have to be creative. So rise has to do with the y values, and run has to do with the x values. So what I'm going to do is I'm going to pretend that this guy right here, this little chart that I have, is a graph. So if I were graphing and I were to count how far up I would go along the graph, I would say to get from 3 to 11, I go up 8. I go up 8. I go up 8. I go up 8. So since y is rise, and I'm going up by 8, my rise is 8. So far my slope is 8 over, I don't know, over what? My run is the x values because the x is the x-axis. It goes like that. So my run is going to be positive or right 2, right 2, right 2, right 2. In other words, 8 over 2. 8 divided by 2. Oh, it's 4. So my slope is 4. How do I find my y-intercept? My y-intercept exists along the line where x is 0. Look, x is 0. Where? At 3, which means at 0, 3 is my y-intercept. So my y-intercept is 3. So let's put it all together. Let's take that black equation and let's write it out. Y equals m. No, I just found out that m is 4. So y equals 4x plus b. Just found out that b is 3. So plus 3. Tricky. Tricky. Again, what I'm doing is I'm just pretending that's a graph. And I'm imagining there's this point, 0, 3, and then another point, 2, 11. How would I get from that point to the other point? Being creative here. Oh, it's the same exact problem. So let's see if we can do the same exact thing. Slope-intercept form. Y equals mx plus b. Slope is rise over run. So rise is going to be the y value. So rise, wise. It would be wise to rise. 13 to 17 is 4. 17 to 21 is 4. That's supposed to be an arrow, but there's lags. 4, 4. So my rise is 4. So what I have so far is 4 over, I don't know. Let's see my run. My x is my run, so it's positive, so it's plus 2, positive 2, going right 2, going right 2, going right 2. So 4 over 2. 4 over 2 is 2. Cool. All right, and the last problem, when x was 0, I found b. Oh no. I don't have x is 0. Well, let's see what I can do. If I'm not given a 0 value for x, I could still find b, and this is how. What I have so far is I have y equals, m is 2, so 2x plus b. I don't know b. Oh, but look, if I have an x and a y, the way I can find b is I can take an xy. So see how x is 5 and y is 13? I can replace y with 13. I can replace x with 5 and find b. 2 times 5 is 10. Is b all by itself? No. What's in the way? 10. How do I get rid of 10? Subtract 10. Subtract 10. 13 minus 10 is 3. So b is 3. B is 3. So now I know that b is 3. I can take what I wrote up here, and I can take the fact that b is 3 and write out y equals 2x plus 3. Tricky. These are difficult problems. In reality, I have a video on my YouTube where I teach you how to do this using linreg. And linreg is a way that you can use your graphing calculator and find this easily. But I don't have a calculator. The only thing I have in my hands is this stylus and this Band-Aid from when my cat scratched me. That's what I call cat scratch fever. It's a song. Look it up. All right. Ooh. So I don't even have a graph here. I'm given 2 points, and I'm supposed to write something in slope intercept form.
How do I find the slope if given 2 points? The slope formula. The slope formula gives me an equation and lets me find the slope connecting 2 points. That's the slope formula right there. All right, let's plug everything in. I got to label my points, x sub 1, y sub 1, x sub 2, y sub 2. And I'm going to start replacing these letters with those numbers. Instead of y sub 2, I could put 4 up there. Minus is minus. Instead of y sub 1, I could put 5 up there. Instead of x sub 2, I could put 3 down there. Minus is minus. And instead of x sub 1, I can put 0. Upstairs in the numerator, 4 minus 5 is negative 1. In the denominator, 3 minus 0 is 3, and negative 1 divided by 3 is the fraction negative 1/3. Cool! So I have my slope. Took a while, but my slope is negative 1/3. My y-intercept is whenever the x value is 0. So my y-intercept is 5. Well, that's easy. So if my y-intercept is 5, then I can take that red equation up there and rewrite it out and plug in what I know. Y equals m. Well, I just found out that m is negative 1/3. X is x. B is positive 5, so plus 5. These are tough problems. Again, you can use LinReg, but I don't have a graphing calculator. If you struggle with that, I suggest you watch it again. Or maybe this problem's almost exactly the same. It's not. It's worse. So I have the points negative 2, negative 4, to negative 2. I'm supposed to write an equation in slope-intercept form, which is y equals mx plus b. M is my slope. Do I have a graph? No. Can I find my slope? Yes. How? Slope formula. The slope formula says m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I can change those points or label those points to x sub 1, y sub 1, x sub 2, y sub 2. I go to my slope formula right there, and I replace those letters with the numbers up there. So instead of y sub 2, I found out that y sub 2 is negative 2, so negative 2 minus is minus. Instead of y sub 1, I have negative 4 over. X sub 2 is regular 2, minus is minus, and x sub 1 is negative 2. I have a double negative, so let's make that to a positive. I have another double negative, so let's make that a positive. I have negative 2 plus 4 in the numerator, so if I owe $2 but I get $4, I now have $2 in the positive, baby. And I have 2 plus 2 on the bottom, which is 4, I think. And can I simplify 2 over 4? Sure. This is the problem that I have. In the last problem, I had a point that was 0 something. I don't have a point that's 0 something. So I'm going to do what I did in the second problem and say what I have so far is y equals 1/2 x plus b. I need to find b. How can I find b? Well, if I have a point right here, okay, and let me erase that because that was the worst circle I've ever made in my entire life. If I have a point right there, this is an x value, that is a y value. So I can replace that y with negative 4 equals 1/2, and I can replace that x with negative 2. Do some math. Half of negative 2 is negative 1, so I have negative 4 equals negative 1 plus b. Is b all by itself? No. What's in the way? Negative 1. How do I get rid of it? Add 1. -4 plus 1 is -3. So I had y equals half x plus b, and I just found out that b is -3. So y equals half x plus -3. Well, I'm not going to put plus -3. That's crazy. I'm not going to put plus -3. I'm going to put -3. I don't like it. I don't like it. I don't like it at all. But you know what I do like? This problem. I'm going to do this problem in warp speed. Are you ready? I have 2 points. -4, -5. And 6, -5. -5 repeats. Now, in the previous problem, I had 2 -2s, but this -2 was an x value, and that -2 was a y value. This -5 and that -5 are both y values. So it appears to me that no matter what, y is -5. Guess what that means? My answer is y is -5. And I'm done. If you notice, if you're being asked to write an equation, and you notice that 2 of the letters are exactly the same, if x's were the same, then you would write out x equals 2, or x equals whatever. And in this case, y's are -5, so y is -5. I can go through the whole process and find the slope if I wanted to, and then plug stuff in and blah, blah, blah. But why should I? Oh, man. Oh, bye.
Well, hey y'all, Peyton Manning here, former quarterback for the Denver Broncos, and I'm here to teach y'all how to find a line in slope-intercept form using your calculator. So let's see what we've got going on here. We have ourselves our TI-84 Plus calculator. It looks like we have ourselves a problem. Write an equation of a line passing through 6, 1, and 3, -1, and we are going to do that in slope-intercept form. Y'all, the process we're going to use today is called linear regression. Linear regression helps us find a line. Linear regression. And this is how we're going to do it, y'all. Pay attention. Do this along with me. First, you're going to hit Stat, and you're going to go to Edit. Hit Enter right away. What it does is it gives us a list of numbers that we could input. In fact, more important, it gives us 2 lists. So the 2 points that we have are 6, 1 and 3, -1. In L1, I'm going to put 6, hit enter. And in L2, I'm going to put 1. That inputs the point 6, 1. Here in L1, we're going to do 3, enter. L2, we're going to hit -1, hit enter, and what we have is we have our 2 points, 6, 1, and 3, -1. Very good, y'all. You did great. Now let's quit out of this. The way we quit is we go to second mode, and that takes us to quit. We're going to go back to our stat, so hit stat there right in the middle. Go to calc. And since we're using the process called linear regression, we're going to go to our 4th option here called linreg. Linreg. So go down to 4, 1, 2, 3, 4. Hit enter on that linreg. Hit enter again. And the way it gives this to us is it gives us y equals ax plus b, where a is 0.6 repeating and b is -3. So even though this is not my final answer, I'm going to first write out that I am going to have y equals a, but instead of a, I have 0.6 repeating. Okay? Y equals 0.6 repeating, x plus b would be plus -3. I'm just going to put -3 instead. Now, y'all, back in Louisiana, I was always told that you never write your slope as a fraction. Or I'm sorry, pardon me, as a decimal, specifically a repeating decimal. I have to find a way to get that 0.6 repeating as a repeating decimal. So this is what I'm going to do. It's a little trick I learned at the University of Tennessee. If I want to turn 0.6 repeating into decimal, I'm going to hit 0.6, and I'm going to hit 6 a bunch of times. Just keep going, keep going, keep going. 0.6 a bunch of times. I need to turn that into a fraction, so I'm going to hit math, and right away, frac, and that turns 0.6 repeating into a fraction. Just so happens that 0.6 repeating is the fraction 2 over 3. So my final answer is going to be y equals 2 over 3x minus 3. I just changed 2 points into an equation in slope-intercept form. Yippee-yi-yo, y'all. That was awfully exciting. Boy, oh boy, I could scarcely contain my glee. Thanks, y'all, for watching. I always appreciate the grit and determination that y'all show while watching these videos. Have a great day. Go sports! How do I turn this? I'm sick of it. This happens every time. I don't never know how to turn these things off. It's probably that red button, but I'll try another option instead. Is it this button? Nope. Fine, I'll try the red button and see what happens. All right, here we go. Back to basics. Catch myself looking at myself on the bottom screen. Because I'm just so good looking, I guess. I don't know. It must be it. Today, friends, we're going to talk about proportional relationships. And there's really nowhere I can put my face. Maybe that'll do. Proportional relationship is when you use a rate to describe what something's doing, like miles per gallon, feet per second. And proportional relationships always give you a graph, or it can be a graph that will always go through 0, 0. Proportional relationships always go through 0, 0. Okay? If it doesn't, it's not proportional. So, what is the slope of the graph? Remember, slope, and I'll write it out here for all you forgetful heads, is rise over run. I picked 2 points. Here's a point, and here's a point. Look at me just going out of the ordinary. And then I figure out if it's positive or negative. Well, the slope is positive because it goes up and to the right. And then I count up 1. Oh, no. Look at this over here. Each little chunk doesn't go up by 1. It goes up by 5. Tricky. So I don't go up 1. I go up 5. 10, 15, 20, 25, 30, 35, 40. So my rise is 40. My run is actually still the regular numbers because every little dot here is 1, 2, 3, 4. So I can run 1, 2, 3, 4, 5, 6, 7, 8. So my slope looks like it should be 1 over 1 or 8 over 8. But it's actually 4 over 8 because this side is all screwy. And last time I checked, according to my calculator, 40 divided by 8 is 5. What's the slope mean? Well, let's eliminate some of this mess here. Slope is rise over run. The rise is the up-down part. So this part over here is my rise, and this part over here is my run. I came up with 5 for my slope. So I'm using water, according to that, and I'm using 5 rise over run, or gallons is my rise, over minutes. So I'm using 5 gallons per minute. So if I had more space, I would turn that into a nice little sentence
saying I am using water at a rate of 5 gallons per minute. Okay? Maybe you're running a hose or something. I don't know. All right, let's move my face so I can move that. Where should I put my face now? No. Yep, on the bottom left again. What is the slope of the graph? All right, where are my points? I don't have points, so I'm going to put points there. Let's make life easy and put it at 0, 0 because I can. And let's put it at the first point, actually the only point that I can. So every time I go up a block, am I going up 1? No, I'm going up 200, 400, 600, 800, 1,000. So my slope is positive 1,000 over, my time is 4. So over 1, 2, 3, 4, because it does go over by ones. That's a 1, that's a 1, that's a 1, that's a 1. So 1,000 over 4 is 250. What does the slope mean? All right, well, this is a problem that I stole from the internet, and it's talking about the flight of an airplane. My slope is rise over run, so miles over hours, miles per hour. So it looks like the flight of the airplane, looks like the speed of the airplane is 250 miles per hour. So I can write that. That's the, oh no. That's all right. I'll make it a nice short sentence. The speed of the airplane is 250 miles per hour. All right. Cool. That's it. The amount Y in dollars. The amount Y in dollars that you raise by selling X fundraiser tickets is represented by the equation Y equals 5X. Graph the equation and interpret a slope. Okay, so let me make a little chart here. This is called an XY table or a T table. And what I'm going to do is I'm going to pick a bunch of X's to plug in and see what I get. If I plug in 0, if I plug in 1, if I plug in 2, if I plug in 3, if I plug in 4, what Y will I get? There's my equation. If I replace X with 0, I get 5 times 0, which is 0. If X is 1, that means 5 times 1, which is 5. If X is 2, that means 5 times 2, which is 10. If X is 3, that means 5 times 3, which is 15. And if X is 4, that means 5 times 4, which is 20. So let's graph those points. Okay, that is the point 0, 0, which makes it proportional. Makes sense to me. That is the point 1, 5. So that's right 1, up 5. Put a dot there. .210 is 210. So that's right 2, up 10. If you're not getting a straight line, you did it wrong. That's 315. So that's right 3, up 15. And I'm not even going to bother with the next number. Why? First, it offends me, and also I can't even graph it. So why bother? Perfect. Perfect straight line. Well, the phone's ringing, which means I got to be done. And I am done anyway. So that's proportional relationships. Proportional relationships is you're going to just have or graph a straight line that goes through 0, 0. And it usually involves a rate of some kind, miles per hour, gallons per minute. In this case, what am I doing? Dollars per ticket is what I'm doing. Okay? That should do it. Bye.
What up, what up? On today's video, we are going to talk about point-slope form. In a previous video, we talked about slope-intercept form, which is an equation that uses a slope and the y-intercept to help graph. Well, point-slope form is going to be an equation that utilizes a point and the slope of a line, whether it's for graphing, but in most cases, it's actually finding out the equation. You can graph in point-slope form, but today, we're mostly going to be finding the equation using point-slope form. So what is point-slope form, you ask? That is point-slope form. It's a lot sloppier than slope-intercept, but it's manageable. Y minus y sub 1 equals m times the quantity x minus x sub 1. Now the m here stands for the same old m that we're used to. It's slope, okay, right there. And if I give you a point like 3, 5, the 3 would be x sub 1, and the 5 would be y sub 1, and you just plug it into the equation. Now the fun thing about point-slope form is if I ask you to write an equation in point-slope form and your equation looks something like this, and I'm just making this up as I write it out, sloppy as it is, that's technically correct. And you might look at that and say, no, that can't be correct. It looks terrible. I mean, you have to distribute and add 5. Not if I ask you to find an equation in point-slope form, which is what we're going to be doing several times today. So, first problem number 1 is I'm going to graph something in point-slope form. So what I'm going to do is I'm going to write out point-slope form underneath it. So I have y minus, that looks terrible, oh my goodness, let me start over. Y minus y sub 1, I'm going to write that out underneath, equals m, which is the slope, times the quantity x minus x sub 1. Okay, so this is where it gets weird. First of all, let's find the slope. The slope's the easiest part. The m matches up with a half right there, so my slope is a half. Easy peasy. Easy peasy. This is where it gets weird. My point is in the form x sub 1, y sub 1. But here I have a minus in front of it. So this is negative x sub 1. So negative x sub 1 equals positive 2, which means regular x sub 1 equals negative 2. Did you catch that? Negative x sub 1 is positive 2, so x sub 1 is negative 2 because it's all opposite land there. Similarly, negative y sub 1 is negative 3, so positive y sub 1 is positive 3. And like an idiot, I started writing out y when I should have just wrote out 3. Now I'm going to start out by plotting the point negative 2, 3 right here on my graph. And I'm going to use that slope to make more points. Up 1, right 2, up 1, right 2, up 1, right 2, up 1, right 2. Or I can go down 1, left 2, down 1, left 2. Do my best to draw a straight line. It's unbelievable. I spent $20 on this here pen from the internet, and that's the straightest line that I can draw. Great. This is going to be fun. All right. That's how we graph. I guess we're going to do it again. Good job by me. Let's write out the equation again. Y minus y sub 1. There is no number after the y. I wonder if that means anything. Let me see if I could scooch this over so I can line up the equal signs. Yeah, this is not going well at all for me. All right. Equals m x minus x sub 1. Let's start out like we did last time. What's my slope? Well, m matches up with the negative, just the negative, which tells me that m is negative 1. Negative x sub 1 is positive 1, which means positive x sub 1 is negative 1 because it's opposite land. And I have y blankety blank has to match up with y minus y sub 1. Well, there's no number after that y, which means the number is that, as Steph Curry would say. Boom. So I'll plot negative 1, 0, which is supposed to be right there and not where that line accidentally went. If my slope is negative 1, that's the same as negative 1 over 1. So I go up 1, left 1, 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 or down 1, right 1, down 1, right 1, down 1, right 1, and my face is in the way. Let's make another attempt to draw a perfectly straight line. This is going to be awesome. Oh my goodness gracious. I'm going to try that from here on out. Okay. Find the equation of a line with the slope of negative 5 and goes through the point negative 1, positive 3. All right, well, my slope-intercept form is y minus y sub 1 equals m times the quantity x minus x sub 1. The purpose of point-slope form is to write an equation using a point and a slope. Oh, look, a point. Let's label it x sub 1, y sub 1. Oh, look, a slope. Let's label it m. And so should I just kind of plug in what I have? Yup. Y minus y sub 1 is 3 equals m, which is negative 5, times x minus x sub 1, which is negative 1. Double negative. Curses. We'll just clean that up right now. Final answer. Y minus 3 equals negative 5 times x double negative, which is plus 1, and that is my answer. What I did is when it says find the equation of a line with slope and point, I write out point slope. I label my slope m. I label my point x sub 1, y sub 1. I plug it all in, and if there's a double negative, make it positive. Bada bing. Bada bing. Ooh, what if I don't give you the slope, though? No matter. I could still find the slope of a line if I give you 2 points, which is what I have right there. The slope formula is found by doing m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So let's label the points. I've got x sub 1, y sub 1, x sub 2, y sub 2. So to find a slope, I just plug those points in. And I know I have videos on my channel where I use the slope formula. So if this is throwing you off, just type out slope formula. Of course, Nick Parrish slope formula, and you'll be in great shape. Y sub 2 is 9. Minus y sub 1 is negative 3, so I have a double negative. Deal with that in a second. X sub 2 is 4 minus x sub 1 is negative 2. I have a double negative. Deal with that in a second. What I'm just going to do is I'm just going to make those double negatives positive. Look at that. Double negative positive. Y plus 3 is 9. Plus 3 is 12. 4 plus 2 is 6. And that simplifies to 2. Gang. Now my slope is 2. What's my point? Easy. I have a point. And you know what? I have 2 of them. But I labeled this guy x sub 1, y sub 1. So let's just keep with that. Oh, what's that? Could I use the second point as my x sub 1, y sub 1? Of course. There's 2 possible answers to this problem using those 2 points, but I'm only going to do one. So my point slope form is y minus y sub 1 equals m times the quantity x sub regular x. I'm getting my slope formula, and my point slope formula mixed, x minus x sub 1, according to what I pointed out up there, y sub 1 is -3, so y minus -3, I'll fix that in a minute, equals m, which I called 2, times the quantity x minus -2, another double negative. So let me clean it up right now. Y double -3 is the same thing as y plus 3, because the opposite of a negative is positive, equals 2x double -2, which means x plus 2. And there you have it. Crack! Now, before you yell at me and scream at me and say, well, why don't we do distributive property and subtract 3 from both sides? I could, but why? This is an acceptable equation. This is point-slope form. It's fine by me. It's fine by me. Gross. What is the equation of a line that goes through the points 1.5, -5, and 4.52? This is the exact same type of problem as the last guy. Okay, I'm going to use point-slope form. I could use slope-intercept, but this video is learning how to use point-slope form, so I'm going to use point-slope form. I'm going to start out by noticing, do I have a point? Yep, I have 2. Do I have a slope? No. But if I have 2 points, I could use the slope formula to find my slope. So I'm going to label you x sub 1, y sub 1. I'm going to label you x sub 2, y sub 2. My words are faster than my pen because I messed up. I'm going to write out the slope formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1 equals y sub 2 is 2 minus y sub 1 is -5, double negative there. I'll deal with that in a minute. X sub 2 is 4.5. Don't freak out. Minus x sub 1 is 1.5. That's why you shouldn't freak out, because the math turns out nice. Oh, look, a double negative on the top. Let me just make it positive. 2 plus 5 is 7. 4.5 minus 1.5 is 3. My slope is 7 over 3. Not a problem. Slopes are supposed to be fractions, especially improper ones. Now, did I find my equation yet? No, I just found my slope. So I'm going to write out my equation, which is going to be y minus y sub 1 equals m times the quantity x minus x sub 1. I already have a point labeled x sub 1, y sub 1. Why don't I stick with it? And I know my m is 7 over 3. So y minus y sub 1 is -5. I'll fix that in a minute. Equals m, which is 7 over 3. Times the quantity x minus x sub 1, which is 1.5. Now, since I'm kind of running out of space there, this is what I'm going to do. The only issue I have is that double negative, y minus -5. I'm just going to make it look like a pretty plus sign. And ladies and jelly spoons, there you have it. Y plus 5 equals 7/3 times the quantity x minus 1.5. And that is point slope form in a nutshell. You get the point? It's a joke. All right. Thank you. Bye. What up? Today we're talking about standard form. Standard form is the equation of a line. Now, if you watch my videos in order, you're going to be like, another one? Didn't you show us slope-intercept form? Didn't you show us point-slope form? And now you're giving us standard form? Yes! Why, you ask? No reason. So let's get started. Standard form is what they used to back in the olden days. They used to use it back in the olden days. And that's what it looks like. ax plus by equals c, where a and b are just numbers, and so is c. X is x and y is y. Now what's a? Nothing. What's b? Nothing. What's c? Guess. Nothing. You see, the reason why a point-slope form was so convenient is it gave us a point and a slope. And slope-intercept was so convenient because it gave us a slope and a y-intercept. Standard form serves very little purpose, but no matter. No matter. I'm going to turn that guy into slope-intercept form and see if we can learn a few shortcuts. And guess what? We will. So let me get a pen. Let's go with green, my favorite color. I'm going to take that guy and solve for y. So the first thing I have to do is subtract ax from both sides, subtract ax from both sides, cross u out. This solves for by, so that's supposed to be a by equals, slope-intercept form is mx plus b, so I want the guy with the x first, so I'm going to write out negative ax positive c. Many of you might put, what about c minus ax? Sure, but I want this to look like slope-intercept form. Is it slope-intercept form? It certainly is not. So what I'm going to do is I'm going to divide both sides by b, which means you divide everything by b. And what that does is it tells us y equals a and b don't combine, so I have negative a over b living in front of x plus c over b. So what I just found out is if I give you something in standard form, my slope is negative a over b, and my y-intercept is c over b. My slope is negative a over b, and my y-intercept is c over b. So, I need to graph that. Well, that's standard form, isn't it? So let me label things. Your A, your B, and your C. My slope is negative A over B. So my slope is negative A, 6, over B, 2, which is negative 3. My y-intercept is C over B. So C, which is 12, over B, which is 2. So my slope is 6. No, my y-intercept is 6. Dummy. Sorry. Now we can graph it. So if you're thinking, can I just solve that by subtracting 6x and then dividing everything by 2? Yes. But if you want to do these in your head, which I can, I don't need to do that. I can just memorize a few letters and I'm in good shape. Let's put a dot at 6 because that's my y-intercept. 1, 2, 3, 4, 5, 6. My slope is negative 3, which is the same as negative 3 over 1. So I can go up 3, left 1. No, I can't. I can go down 3, right 1, down 3, right 1, down 3. Can I move my face? Down 3, right 1, down 3, right 1. And ladies and gentlemen, I have myself a line. Now there's another way that I can graph that, but I'll save that for later. Capiche? Looks like I'm doing it again. Oh, look, standard form. Something x plus something y equals something. So I have A, which is my 4, B, which is negative 3, and C, which is regular 3. So my slope is negative A over B, so negative 4 over 3. That's my slope. There it is. And my y-intercept is C over B. So 3 over negative 3, which means my y-intercept is negative 1. So in order to graph it, I put a dot at -1 right there. My slope is up 4, left 3, up 1, 2, 3, 4, left 1, 2, 3, up 1, 2, 3, 4, left 1, 2, 3. And my face is in the way, but you know what? Ouch! Ouch! Right in the face. Nope, wrong way. Mirror. It's a mirror. Again, if I wanted to, I could have subtracted 4x and then divided everything by -3. But what fun is that? What fun is that? All right. The other way that we could handle these are dealing with the concept of y-intercept and x-intercept. You already know what a y-intercept is, and that's when you have y all by itself. The number that's floating around is my y-intercept. Great. There's another way that you can look at y-intercept. Okay. Any point that is a y-intercept is going to be the point 0 something, 0, 5, 0, -2. That looks like 0 regular 2. Okay. And an x-intercept, similarly, is when my y is 0. So that looks like -2, 0. So simply put, a y-intercept is when x is 0. And a x-intercept is when y is 0. So how do I solve? If I ask you, just like a regular old problem, hey, find the x-intercept, and you're like, I've never learned that before. Okay, well then make y equals 0, and then solve for x. Okay, and if I ask you to find the y-intercept, normally you would solve everything for y and then find the number floating around. But now I could just throw 0 in for x and then solve for y. And that'll be your y-intercept. So let's use that method to do this problem right here. And this problem right here, I ask you to find the x-intercept and the y-intercept. Let's move my face again for the 18th time today. Find the x-intercept and the y-intercept of 3x minus 6y equals 21. Let's start out by doing the x-intercept. To find the x-intercept, I'm going to rewrite that equation right there. But I'm going to plug in 0 for y. I'm going to rewrite that equation right there, but instead of y, I'm going to have 0. See? -6 times 0, well, that just becomes 0, so you're pointless. Which is funny because we're talking about points. Not so much today. 3x equals 21. Divide both sides by 3. And my y-intercept is 7. Boom. That's it. Basically, you're just like getting rid of y and everything attached to it. Solve. To find the y-intercept, what I used to do is solve everything for y, but you know what? There's just an easier way to do it. And I'm going to rewrite that equation out, but instead of x, I'm going to put 0. I'm going to rewrite that equation, but instead of x, I'm going to put 0 minus 6y equals 21. You're pointless. Drop down the -6y, which equals 21. Divide by -6. Divide by -6. And the y-intercept is 3.5. -3.5. Yeah, it is. Okay. So those of you who are getting used to this, you know, my method of doing like the y-intercept is I just kind of close my eyes and make the 3x disappear, divide everything by -6, and there you have it. Not so bad. Not so bad when you understand math. Not so bad at all. I'm going to ask you to graph. -4x minus 3y equals -12. I'm going to label you A, I'm going to label you B, and I'm going to label you C because you're in standard form. Slope is -a over b. Okay, -a over b. So my slope is negative a, which is -4, over b, which is -3. I have a triple negative, which makes it negative. Because if I have 3 negatives, the double negative becomes positive, and I still have a negative left over. So I have negative 4 over 3. That's my slope it is. Just because I don't have a ton of space, the way I find out what my x-intercept is I make believe that the y is 0, which makes the negative 3 go away. So I'm finding the x-intercept. I'm making that part go away, which means I have negative 4x equals negative 12. Divide everything by negative 4, divide everything by negative 4, and my x-intercept is 3. The way I find my y-intercept is I pretend that x isn't there, and I make everything in front of that go away. And so I have negative 3y equals negative 12. So I'm going to write that out. Negative 3y equals negative 12. I'm going to divide everything by negative 3, divide everything by negative 3, which means my y-intercept is regular 4, because negative 12 divided by negative 3 is 4. So if my y-intercept is 4, boop, boop, and my x-intercept is 3, I have 2 points. That's enough to graph. But I also found out that my slope was negative 4/3. So like if I wanted to, I can't go up 4 over 3. I don't have enough space, but I can go down 1, 2, 3, 4, right 1, 2, 3, and there I have another dot, and it makes it a little bit easier to graph if I would just hit all 3 of those dots. And that is not pointless because I had 3 points. Standard form, everybody. A lot of fun. Thanks for watching. Bye. Well, a good day to you. Welcome to Back to Basics, and today we're talking about parallel and perpendicular lines. Before we really talk about what we do with them and what the numbers are behind parallel and perpendicular lines, let's talk about what parallel and perpendicular mean. Parallel lines never intersect, ever, except for an infinity, but that's a different discussion that you can talk about in college. Parallel lines will never intersect. So if you look over there, you have 2 lines that will just simply not touch each other. And if I were to slap that on a coordinate plane and try to go up and over and find out what the slopes are, it's obvious what the slopes are. They're the same, the exact same. Parallel lines have the same slope. It's just if one's a little bit higher than the other, it has different y-intercepts. That's it. Parallel lines have the same slope. And if you're talking about coordinate planes, they have different y-intercepts. Easy, but they will never intersect. Ever not in a million years. Maybe a billion. But not in a million years. Perpendicular lines, however, as you can see from the graph, they do intersect, but intersect in a very specific way. Look at that graph over there. If I were to look at that graph over there, I might be able to say, I could find out that one slope appears to be, let me see, the red slope appears to be up 1, 2, 3, 4, 5, 6 over 1, 2, 3. So this red slope appears to be 6 over 3, which is 2, or 2 over 1. And that blue line appears to be negative up 1, 2, 3 over 1, 2, 3, 4, 5, 6. Negative 3 over 6 is negative a half. Well, one was positive. One was negative, one was a half, and one was 2 over 1. Perpendicular lines are the same thing, but one's negative and flipped, also known as negative reciprocals. A reciprocal is when you take a number and reflip it. Oh, I'm sorry, flip it. Oh, I accidentally made reciprocals sound like reflipricals. What an accident I made. Bing, I didn't make an accident. And I haven't in many years. Thank you. Lost my train of thought. Okay, so I have one is going to be positive and one's going to be negative, and the other one is going to be the flipped version of the other. So if I found out that a line was a half and I wanted to find out what the negative reciprocal of a half is, it would be negative 2 over 1, or just negative 2. If I gave you negative 3, I might think, well, negative 3 is the same thing as negative 3 over 1. So you flip that and take the negative of a negative, which is just a positive. So perpendicular lines, their slopes are negative reciprocals of each other. I don't care about their y-intercepts. I only care about their slopes, and their slopes are negative reciprocals of each other. And you find the negative reciprocal by flipping it and making it opposite. Flip it, opposite, flip it, opposite, flip it, opposite, flip it, opposite. Find if the two equations are parallel, perpendicular, or neither. Okay, I can do this. In a previous episode, I used standard form to find the slope. But what I'm going to do is to find the slope for this blue guy is I'm just going to solve for y like I normally would. So I'm going to solve for y like I normally would. I'm going to subtract 3x from both sides, minus 3x, cross u out, drop down the 4y. I'm going to write this out in a way that makes me happy because it'll look more like slope-intercept form. Minus 3x, positive 12. I'm going to divide everything by 4. I'm going to divide u by 4. I'm going to divide u by 4. And now I need to find the slope. Well, now that y is all by itself, the slope is negative 3 over 4 because when y is all by itself, the slope is the number in front of x. So my slope for the blue guy is negative 3 over 4. That is point slope form. When you're in point slope form, the number in front of the parentheses is my slope. So I'm just going to say, well, my slope is 3 over 4. So compare 3 over 4 and negative 3 over 4. One's positive, one's negative, which means it can't be parallel. Wait a minute. Wait. One's negative 3 over 4 and one's regular 3 over 4. So they're not flipped versions of each other, which means they're just neithers. They're neithers. Okay? So I did it. I did it. Neither. That was a close one, though. It's like I purposely did that. I did. Find an equation parallel to that guy right there and goes through 5, 6. Well, if I'm going to find something that's parallel, I care about them having the same slope. Well, look at this guy. That's point slope form, which means the number in front of x, or the number rather in front of the parentheses, is going to be the slope that I want. So the slope that I want is m. Hooray! It also goes through that, and that's a point. So I needed a slope, and I'm given a point. I'm going to use point slope form again. So I'm going to label my point x sub 1, y sub 1. So again, I'm given a point, and I need to find a slope, so I'm going to use point slope form. What's point slope form? Y minus y sub 1 equals m times the quantity x minus x sub 1. What's my y sub 1? 6. So y minus 6 equals m. What's my m? Negative 3 times the quantity x. So popular. Minus x sub 1, which is 5. No trickery. That's my answer. I'm done. So as you can see, they both have the same slope, but since they have different points, if I were to do the math out, they would have different y-intercepts. And if you're like, well, let's do the math, that looks terrible. No. Because in a previous episode of Back to Basics, I said that if I ask you to find an equation and you write it out in point slope form, well, by golly, that's perfectly fine. Sorry for cursing. I don't like cursing. But sometimes I just have to get my point across, and I don't know how else to do it. Oh, my point across. My point slope across. Now what I need to do is I need to find an equation perpendicular to that guy right there in standard form. but it also needs to go through negative 1, 4. I'm not given the slope right away. I'm not. So what I'm going to do is I'm going to take that guy and solve it for y. Why am I going to do that? Well, if I get y all by itself, then the number in front of x is my slope. So I'm going to add 2x to both sides. Add 2x to both sides. I did this in a previous problem. That gives me 5y equals 2x plus 1. And I wrote it out as 2x plus 1 to make it more look like slope-intercept form. Y is not all by itself. I'm going to divide everything by 5. I'm going to divide everything by 5. I'm going to divide everything by 5. Y equals 2/5 x plus, who cares? Because my y-intercept doesn't matter. All I care about is my slope. What is my slope? 2/5. However, the slope that I want has to be perpendicular to that. And perpendicular is the negative reciprocal of 2/5. What's the negative of a positive? A negative. And if I flip the 2/5, I get 5/2. So there's my slope. Oh, look, a point. So I will label that point. So if I have a slope and I have a point, guess what I have? Point slope 4. So I have y minus y sub 1 equals m times the quantity x minus x sub 1. My y sub 1 is 4. Y minus 4 equals my m, which is negative 5 over 2. X minus x sub 1, which is negative 1. That double negative looks terrible. Yeah, that'll do. And that's it. That's it. Point slope form is A-okay with me. I'm running out of space according to my computer, so I'm going to end this video now. Bye! Back to basics. We're going to talk about functions today. Who's ready to talk about functions? Anytime you're given a bunch of points, it's called a relation. Sometimes what we have to do, though, is find out if it's a function and list those points. Here, all I have to do is list out the points. Easy. Input is always an x value. Output's always a y value. Input is also known as the domain. So if you were to see the same type of problem, it could be input, it could be domain, it could be x. Input is x, output or range is y. So in this case, I have 1 going to 3, which means I have the point, if I can get this, 1, 3. I have 2 going to 6, which means I have the point 2, 6. I have 3 going to 9, which means I have the point 3, 9. And I have 4 going to 12, which means I have the point 4, 12. Oh boy. Similarly, I have 0 going to 0, which means I have the point 0, 0. I have 2 going to 1, which means I have the point 2, 1. I have 2 going to negative 2, which means I have the point 2, negative 2. And I have 4 going to negative 3, which means I have the point 4, negative 3. Easy. Easy. Now what I have to do is determine if these guys are functions. You can determine if something is a function if every input goes to exactly one output. In other words, the inputs can't repeat. It's as if I were to take a dart and my darts were labeled -9, -2, negative, irregular 5, and 12. And if I were to throw them at targets, my -9 would hit it would give me 0 points. My -2 dart would give me 5 points. My 5 dart would give me 10 points, and my 12 dart would give me 10 points. And you might be like, well, hold on, 10 is used twice. You can't do that. Sure I can. If I'm playing darts and things are listed 1 point, 2 point, 3 point, and I hit 10, and then I throw a dart and I hit 10 again, that's fine. So this is a function because every x value is used exactly once. Every input is used exactly once. This guy, on the other hand, is not a function. So if I were to talk about the same kind of dart scenario, if I have 5 darts, it looks like, and I label, if I write on each dart -2, -1, 0, 1, 2, and if I were to throw -2, it would get me 4 points. And if I were to throw -1, it would get me 3 points. And this is where it gets all weird. If I throw 0, it will split in half and hit 2 different targets, 5 and 6, which is impossible. You can't do that. 0 cannot go to 2 different places. I lost my pen. So the fact that an x value splits off and is used twice, that's what makes it not a function. The mapping diagram represents the cost of reserving a hotel room for different numbers of nights. Is the cost a function of the number of the nights reserved? Well, let's see. 1 is used once, 2 is used once, 3 is used once, 4 is used once. Yes, it's a function. Describe the relationship between the cost and the number of nights reserved. Well, it looks to me that every extra night, or each night, costs $85. I think that should do it. I mean, it's a positive correlation if you want to say that, but I think that's describing that real-life problem well enough. The table shows the cost of purchasing 1, 2, 3, or 4 t-shirts from a souvenir shop. Now, is the cost a function of the t-shirts purchased? Well, if I buy 1 shirt, I pay 10, or if I buy 2, I pay 18. Ooh, they're giving me a bargain. Ooh, if I buy 3, 24. If I buy 4, 28. Well, look at that bargain. Why would I go there and only buy 3 shirts? It's wacky. Describe the relationship between the cost and the number of t-shirts purchased. Well, it actually asks me that. How does the cost per t-shirt change as you purchase more shirts? Each additional shirt has a small price reduction. So it went up $8, and then it went up $6, and then it went up $4. So we could say by $2. So 1 shirt I paid 10, and then I only had to pay 8 more, and then I only had to pay 6 more, and then I only had to pay 4 more. Okay? That's it. Functions, relations, nothing crazy there, nothing wacky about it. Easy peasy, t-shirt sleazy. T-shirt sleevesy. I just made that up. I'm so good. Bye.
Vertical line test. We are going to figure out which of these are functions by seeing if a vertical line passes through it more than once. So let's take this here popsicle stick and pass it through. The vertical line does not hit it, so this is a function. The next one. We're good. Function. The next one. Nope. Draw a vertical line anywhere, really. Vertical line hits the circle twice, so that's not a function. How about this one? So far, so good. So far, so good. So far, so right here. Somewhere in the middle here. Hits it more than once. That's no good. This one, though, is good. So this one is a function, and the one to the left is not.
F is for friends who do stuff together. U is for you and me. N is for anywhere and anytime at all. Down here in the deep blue sea. You know, they say you can't spell functions without fun, and you know what? It's true. And today we're going to talk about function notation. Function notation. See this thing right here? I know what you're thinking. F times X. No. For whatever reason, when people invented math, they decided to have this thing called function notation, which is pronounced or rather said as f of x. F as a function of x, where x is your most important variable, is basically what it means. But most importantly, f of x is not f times x. It's just the same as y. So if I give you a problem like f of x equals 3x, that's the same thing as y equals 3x. F of x is y, f of x is y, f of x is y. So f of blah just tells you that whatever blah that is going to be your most important variable that you have in the problem. Okay, so we're going to do this is going to be a pretty short one. If I give you f of x equals 7x minus 2, and then I say find f of 3, what you're doing is you're saying, well, here's f of x. Let's just rewrite this guy and replace x with 3. So f of x equals 7x minus 2 turns into 7 times 3 if I give you f of 3. And of course the minus 2. 21 minus 2 is 19. The real 9 plus 10, if you ask me. If f of x is 7x minus 2, then f of negative 2 is just me writing out the original equation but replacing x with negative 2. That's it. That's it. 7 times negative 2 is negative 14. Negative 14 minus 2 is negative 16. Yeah. That's it. That's it. Pretty exciting stuff. Looks like I just have to make it worse, don't I? I have g of x, which just means I'm naming a new function. Instead of calling it f, I'm calling it g. That way, if I have two functions floating around, I can tell the difference between the two. So g of x is 2.5x minus x squared. So g of negative 4 means I replace every x with negative 4. 2.5 times negative 4 minus negative 4 squared. 2.5 times negative 4 is negative 10. Minus, parentheses, negative 4 squared is 16. And negative 10 minus 16 is negative 26. An old PEMDAS problem. It'll never go away, will ya? G of 10 means I'm just going to rewrite the original equation, but for every x, I'm going to replace x with 10. So 2.5 times 10 minus 10 squared. Notice every time I substitute that 10, or like when I substituted the 4 in the negative 4, I threw a parentheses there. And that's extremely important, especially when you deal with the squaring and stuff like that. 2.4 times 10 is 25. 10 squared is a hundo. And 25 minus a hundo is negative 75. Those of you with high aspirations in life, you will see stuff like this in good old calculus. Now that's like a year and a half away, or 4. But why not get a jump start? F of x is 5x minus 7. F of x plus 3 means you replace every x with x plus 3. So I'm going to rewrite the original equation and replace x with x plus 3. Now it looks like I could do distributive properties, so why not? 5x plus 15 minus 7. 5x doesn't combine with anything because it has an x attached to it, but these guys turn into 8. 15 minus 7 is 8, and that's my answer. That's it. That's function notation for you. Function notation is f of x, and f of x is just the same thing as y. It just looks different. All right? That's it. Bye. Basics. back at it again to the basics with the white bands. Today we're going to talk about writing things as function rules. What's a function rules? Is directions to help us live and go through our daily lives? No. A function rule is just y equals blah, 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 or f of x equals blah, blah, blah. Anytime we see the word output, that's the y value. Anytime we see the word input, that's the x value. So let's write some function rules, shall we? The output, y, is equals the cube of the input. So input cubed. Done. The output, y, is 3 less than, which means I take away 3, the input. Fun fact, if you see the word than, just switch them. So I know you want to say 3 minus x, but you're actually taking away 3, which means minus 3. The output, y, is equals half of the input, x. The output, y, is equals 1 more than, so I see that word than again, so why don't I put 1 at the end, and if it's more, you're adding, twice the input. All right? Function rules. Now I'm going to evaluate the function. So I'm given y equals fx minus 7. Great. Oh, and y equals negative 22. So what I have to do is I have to substitute in negative 22 for y, and in this case, solve for x. I can handle that. This is just like chapter 1. So instead of y, I'm going to write out negative 22 equals 5x minus 7. Is x all by itself? No. What's in the way? 5. Anything else? Negative 7. So I can add 7 to both sides, cross you out. Negative 22 plus 7 is negative 15. Negative 15 equals 5y. Just kidding. X. Is x all by itself? No. What's in the way? 5. Divide everything by 5. And negative 3 equals x. But I hate the way that looks because I always believe that your variable should be on the left. So if negative 3 is x, then x is negative 3. Cool. Y equals 3x plus 2 and x equals 0.5. All right, so I'm going to rewrite that equation, but instead of x, I'm going to put 0.5. So this is actually a little bit friendlier than the last one because I don't really have to solve for anything. All I have to do is do some math. 3 times half is 1.5, and 1.5 plus 2 is 3.5. Cool. No. Y equals x over 4 minus 7, and y is 2. So let's turn y into 2, and that's going to equal x over 4 minus 7. Is x all by itself? No. What's in the way? Divided by 4 and minus 7. So why don't I add 7, 2 plus 7 is 9, equals x over 4. Is x all by itself? No. What's in the way? 4. How do I get rid of divided by 4? Multiply 4. 4 times 9 is 36 equals x. If x is 36, if 36 is x, I'd rather write it out as x is 36. It just looks better. See, I even accidentally said it correctly when I meant to say it wrong. Look at that. Graph the equat. Okay. By making a table. Oh no. My picture is completely ruined. Well, let's see if I can do anything. Let's see if I can move anything. Nope. So I guess when I turn this into a little smartboard thing, it didn't work. Let's add 4. How about that? So I'm just going to make it 4 now. I have y equals x over 4 plus 4. I want to make a table of points that I can graph. So this is called a t-table. And a t-table is when you just pick a bunch of x values, plug them in, and get a bunch of y values. So I'm always going to start out with x is 0 to start out. And what I do is I plug 0 into my original equation, do some math, and see what y I get. So if I plug in 0 for x, I get 0 divided by 4, which is 0, plus 4 is 4. So that gives me the point 0, 4. Now what I don't want to do is try 1. Why? If I plug in 1, I would get 1 over 4 plus 4, which is 4.25. And I guess it's possible, but I'm going to be a little clever here. I'm going to plug in 4, because if I plug in 4 for x, 4 divided by 4 is 1, and 1 plus 4 is 5. So that gives me the point 4, 5. Now, common sense would tell me, let's plug in 8. But guess what? I can't. I can only plug in, and if you're wondering why, 8's not there. So I have one more option that I can plug in, -4. Now, if you're like, do we always have to plug in those points? No, if you wanted to plug in 0, 1, 2, 3, 4, 5, 6, 7, be my guest, be my guest. But I'm plugging in points that seem to be convenient for me. Besides, I already know how to graph this guy because I've done these things before. Tons of them. If I plug in -4, I would get -4 divided by 4, which is -1. And -1 plus 4 is -3. So that would give me the point, +3. That would give me the point -4, +3. I have 3 dots, and that's all I need to draw my line. So I already know how to graph, but this is just like, hey, try it out in a different way. And so I did. Functions. You can't spell function without fun. That's what I always say. Bye. What's good? I heard that's something that you could say at the beginning of videos and it makes you sound cool. Back to basics. We're going to talk about specific types of functions today, and those types of functions are called linear functions. Linear. Now there's a word inside linear that might help me understand. Is it the word ear? No. Oh, the first 4 letters in linear are line. Ugh. So linear functions are straight lines. That's simple. I can remember that even if I run out of room. They can look like this. The most standard straight line ever, the slope-intercept form. Y equals mx plus b. What don't you see? Well, you don't see x squared. You don't see x cubed. You don't see square root of x. You don't see x on the bottom. You can have a number attached to x, but you can't manipulate x itself. X has to be x. You also can't change y either. You can't make it y squared or x square root of y, stuff like that. Okay? So that's that. They also follow, let's get a different color, follow a pattern of y over x values. Y over x values, that's like rise over, slope. So whatever the slope is has to be the same slope. If the slope changes, then it can't be a straight line anymore. So they have to follow a pattern of y to x values. Okay, I think I can handle this. So it looks like what we're doing today is just figuring out if stuff is linear or not. Are you a line? Yes. Are you a line? No. Are you a line? No. A lot of people are like, but it's 2 lines. I know. But is it a line? No. Gotcha. Easy, right? Now, I have to make sure that these are in the form y equals mx plus b, and you can't have x squared, and you can't have x cubed, and you can't have x to the whatever, and you can't have square root of x, and you can't have x on the bottom, and y can't be all funky. So y equals x plus 4. Is x x? Yep. Is y normal? Yep. Is that linear? Yep. I know how to graph that. I would start at 4 and my slope is 1 over 1. That's a line. Is that guy linear? Nope. And you might say, yeah, but x is just x. Yeah, x is x on the bottom where Drake started. So this is non-linear. Because if I were to rewrite this out, I would write out y equals 6 over x, and the fact that x is on the bottom is a problem. It wasn't a problem for Drake, though. I know I made that joke, but I just felt like I had to do it again. Is that bottom one there? You know who else? Is that bottom one there linear or non-linear? Non-linear. Why? Because x to the cubed is all freaky weird. It's actually called a cubic function. Can't have it. Can't have it. Look at that, we're done almost already. Now this is going to be the last part of that first slide that I showed you. In order for this to be linear, there has to be a pattern of y over x values. So let me find the pattern for my x's and let me find the pattern for my y's. My pattern up here for my x's is plus 1. Plus 1, plus 1. All of these are plus 1, plus 1, plus 1. My y's are plus 2, plus 2, plus 2, plus 2. So all of my y's are plus 2. All of my x's are plus 2. So I have 2 over 1, 2 over 1, 2 over 1, 2 over 1. Does that follow a pattern of y over x values? Yes. So is it linear? Yes. So basically, if you have like the same pattern for your y's and the same pattern for your x's, you're done already. You don't have to think too much into it. This is easy. I add 1, add 1, add 1, add 1. What do I get from 1 pi to 2 pi's? I just add a pi. So add a pi, add a pi. Add a pi. This is like when my family gets together for Thanksgiving. So let me see. I have all of my x's are add 1. All of my y's are add pi, which means they all follow the same pattern all along. I don't have to overthink it. This is linear. There's no break in my pattern. Now, when my pattern starts to break, that's when I have to be a little bit more careful, and I have a feeling that's going to happen here. Maybe, maybe not. I don't know. Add 3 for my x. Add 3 for my x. Add 1.5. Add 1.5. So my x's went up by 3 and by 3. My y's went up by 0.5 and 1.5. 1.5 and 1.5. So did my patterns change? No, they follow a pattern. What does that mean? Linear. Well, I did a pretty lousy job showing you the difference between linear and nonlinear with these types of problems. But simply put, if that was plus 3 and plus 3, and that one was plus 1.5 and plus 0.5, it broke the pattern. That's what would make it nonlinear. But since all of these follow the patterns, we're all good. We're all good. Okay, quick video. Bye. What up? Today we are talking about linear translations. The heck is that? Linear means straight line. And as you may remember from earlier this year, translate means to move it. Or as our friends from Madagascar, that place, like to say, I like to move it. That joke is now destroyed because of my stutter. That's all good. All I have to do is just read what's on the slide, and I can't possibly go wrong from here on out, except that my face is in everything's way. Always in the way is my face. Can I squeeze my face? Nope. Linear transformations, basically, or translations. Basically, what we're looking at is if I give you a line of some kind, right, and I move it up, down, left, right, make it steeper, make it upside down, make it shallower, what would that do to the equation that I'm given? Well, let's look at the three possibilities that we have. If I were to take a line and have that line move up or down, that would be called a vertical translation. Now, what a vertical translation looks like is I'm just going to add a regular number, constant, at the very end of my equation. So if I were to graph the line y equals x, it would be great if I had a pen. If I were to graph the line y equals x, right? And I were to just simply do this to it. Like, it looks like I moved it up. In fact, it was right here. That's y equals x. That's a parent function. That is the simplest possible linear equation known to man. If I were to add 3 to that, okay, I'm literally taking my line and going 1, 2, 3. That's it. If I were to make this minus 2, I'm literally taking my line now and I'm going minus, here's my line, that's my original, I'm going to go down 1, 2. That's it. That is a vertical translation. All I do is I basically take my y-intercept and I add to move it up or I subtract to move it down. Done. 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 A horizontal translation is if I were to take a constant and I'm going to try to move it. No, it's not that one. I know this is just going to make my face bigger. Is it this? A horizontal translation is if I want to take that y equals x again. So I'm going to try to draw a nice perfect diagonal. I could have done better. Oh my gosh. Can I undo? Yeah, we'll just reset the page. If I want to take that line and if I want to move it left 1, 2, or move it right 1, 2, 3, this is what you do, and it's backwards land. When you move left to right, it's backwards land. You have stuff moving inside or living inside of the parentheses, and if I subtract 3 inside the parentheses, I know you're thinking, move left 3. Actually, if you subtract 3, you move right 3. So a negative number inside that parentheses means you move right, and a positive number, so if I were to make that plus 3, a positive number would be me taking the original equation and we're moving it 1 left, 2 left, 3 left. Right there. Okay. Now, what if I wanted to make it steeper or more shallow? Well, the number in front of x is a slope. Okay, and what we're going to do is we're going to manipulate the slope to have it do whatever I want. Now, this is called a stretch or a compression. If I were to take a number and multiply it to my variable x, in other words, my slope, okay, if I were to put a 2 in front of this, that would be a positive number that's being multiplied to my variable, and that's going to make my line steeper. That makes sense. A slope of 2 is steeper than the slope of invisible 1. All right? Any number in between 0 and 1, for example, and let me write it up here because I didn't really give myself a whole lot of space. If I were to take y equals x and throw a half in front of it, okay, now instead of going up 1 over 1 and having that, I'm going up 1 over 2 and having a shallow slope. So any number between 0 and 1 makes it more shallow. Now you might be thinking, why don't you just say any number smaller than 1? Well, if I have a negative slope, it flips. So the same rules apply. It's just now, if for any reason, if I were to say, well, let's make the number in front of x 3, all right, there it is, but make it negative, all right, now there it is. So pretty steep, but negative slope. All right, so if I were to put that all together into a nice little equation, like that one, I can basically look at an equation and know exactly what to do with that equation. Right? If I were to give you something like y equals 3 x minus 4 plus 2, right? And I'm going to draw a very rough draft, okay? I know that my slope is 3, which is pretty steep. I know that being negative 4, it's going to move left 4, and I know it being, it's going to move right 4. I fell for it. It's going to move right 4, and being that it's positive 2, it's going to be up 2, and my slope of 3, that should have started right around here. So if this is x, right? If that's 3x, by throwing that minus 4 in there, I move it right 1, 2, 3, 4, and then that plus 2 means I move it up 2, and then I have a line that looks something like that. Now, this equation is kind of special because it looks like an old friend. If I were to take an old friend that looks like this, and if you're like, oh, I recognize that, that's point slope form. And if I were to add y sub 1 to both sides, like so, and then turn that m into k, and then turn that x into h, and then turn that y into v, it's the same exact thing. So this is point slope form manipulated. And remember, point slope form gives me a line given the point and the slope. And when I take like something that's like an equation that's centered around an origin, right, and I make it 3 times as steep, and then I move it this way and that way, I'm just having a slope and a point. Those are my knuckles. So let's see how we're going to use this today in my Back to Basics video. I'm given a function. I'm given 3x minus 4. I know what that looks like in my head. I know in my head that I have something that starts at negative 4 way down here and is very steep. I know it's going to look like that. But what if I turn it into negative 3x minus 2? Well, if I make it negative 3x minus 2, 2 things happen. That positive 3x is now negative 3x. So what happens here? It flips. Okay, so my line went from that to that. Now that minus 2 used to be minus 4. So by turning negative 4 into negative 2, I moved up 2 units. So my line changed in 2 ways. My 3x became a negative 3x. All right, great. It looked like that, now it looks like that. My negative 4 became negative 2, which means it just moved up higher 2 units. That's it. That's it. That's it. That's it. That's it. Oh, much worse. Ugh. All right, well, let's see what happens. There's several things. There's 3 things that I care about. The number in front of x, the number next to x, and the number all the way at the end that's floating around all by itself. And it looks like we're dealing with all 3 of those things. So let's look at the number in front of x first. Let's look at the difference between the two. 4 became 8. The difference between 4 and 8 in multiplication terms is times 2. So what happened? It's 2 times steeper. Because 8 is 2 times 4. My x has no parentheses, so invisible parentheses is now x minus 2. So I'm now subtracting 2 within a parentheses next to x. When I subtract 2, that means I move 2 to the right. Remember, it's opposite land when it's inside the parentheses. And if you're wondering why, well, because when I showed you point slope form, it was x minus x sub 1, so it's opposite when you're living inside the parentheses. That 1 is now a -7. And to go from 1 to -7, you subtract 8, which means I move 8 down because we subtracted 8. All right, so what used to look like this, 4x plus 1, is now steeper, moved to the right, and moved way down here. Pretty exciting. Pretty exciting. Take g of x, g, equals 3x plus 1, make it half as steep, move up 3, move right 4. I can do this. It's a little out of order, but I can do it. G of x, to make it half as steep, that means I need to multiply a half to the number living in front of x. So half of 3 is 3 halves. So 3 halves. To move it up, let's save that for last. To move it right 4 means I need to take my x inside of the parentheses, and when you're moving it right 4, it's opposite land, so it's -4. Close that parentheses, and if I'm moving it up 3, I'm taking 3 and adding it to that 1, so 3 plus 1 is 4, and that's my equation. Very bizarre lesson. It's basically teaching you how to graph equations or understand the graph of an equation without the use of a calculator. Or without having to do a whole lot. If you just remember, well, if I manipulate the number in front of x, or if I manipulate the number contained within a parentheses next to x, or if I manipulate the number all the way over there, I can make it thinner or more shallow, or move it left, or move it right, or move it up, or move it down. Stuff like that. Okay? Translations. More than meets the pie. Math. Bye! Oh, I should have said more than meets the bye. Translations, more than meets the bye! Hello, brochachos and brochachettes. Or cis-chachos. Today we're talking about arithmetic sequences. And I know what you're thinking. Arithmetic sequences? Don't you mean arithmetic sequences? No. So what is an arithmetic sequence? Well, what's a sequence? A sequence is a pattern. Okay? Probably the first pattern you ever learned in your entire life, other than 1, 2, 3, 4, 5, 6, is 2, 4, 6, 8, 10, 12. That is an arithmetic sequence. An arithmetic sequence is when you add the same number to get to the next number. And in the case of 2, 4, 6, 8, 10, 12, you add 2 every time. Now that 2 has a specific name, and it's called the common difference. Whatever you add to get from one number to the next in an arithmetic sequence is called a common difference, and we call it D. Now, we call each number in a sequence a term. So that's another word that we're going to use a lot that we haven't used a whole lot before. So when I look at this sequence right here, I have a term of 11, 8, 5, 2, negative 1. And it seems to get from one number to the next. I subtract 3, I subtract 3, I subtract 3, and so on and so forth. Now, the common difference is what I add to get from one number to the next. Well, we always consider it adding. So what do I add to get from 11 to 8, from 8 to 5, from 5 to 2, and so on and so forth? Well, I add negative 3. So if the common difference, or if the pattern is subtract 3, my common difference is whatever I add, which is negative 3. Okay, so we're going to have our common difference. Our D is going to equal negative 3. All right? Now, there's going to be two formulas that we're going to look at. The first formula we're going to look at is called the recursive formula. Okay, the recursive formula is just a way of finding out what a specific term is if I'm given like the previous term. It's kind of very, 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 very basic. Even though it doesn't look basic at all, it's very basic. If you're wondering what all of these A's and N's are, okay, the N stands for the number term in the sequence. So if I have 15 terms in a sequence, N is 15. Okay? A sub N is the specific number that I'm talking about. So if the 15th term of a sequence is 100, then A sub 15 is 100. Okay? D is the common difference. So really, for us to understand this formula, because it is kind of weird to look at, it's kind of confusing to look at with all the subscripts and stuff like that, the best way to understand it is to actually do it. So my job is to write a recursive formula for this arithmetic sequence, 4, 7, 10, 13. Right? What I'm going to do is I'm going to write out the definition of a recursive formula, which look like that. And I'm going to write out what I know. And the only thing that I know is what the common difference is. So what do I do to get from 4 to 7, from 7 to 10, from 10 to 13? I add 3, add 3, add 3. So my common difference is going to be A sub N equals A sub N minus 1 plus 3. So kind of a dumb problem if we're going to keep it 100. And really the only time you're going to use a recursive formula is if you have a previous number. So if you want the 18th term of a sequence, you're really only going to use the recursive formula if you have the 14th, or what did I say, 18th? You're going to have the 17th term. So, like in a case like this, where I have only the first 4 numbers, and I'm like, find the 18th term in this sequence, this isn't going to help me. Not at all. And that's when we're going to use the next guy, which is the explicit formula. Now, the explicit formula is more important because it contains more cursing. I'm just kidding. I'm just kidding. I'm just kidding. No cursing. No cursing. Not in my videos. Those other YouTubers, they may curse a lot, but not me. No, this is a kid-friendly YouTube channel. So what does the explicit formula look like? What do you need? What's important? Well, it has a few more things attached to it, a few more letters. You really need to know A sub 1, which is the first term in the sequence. N is the same as it was last time. D is the same as it was last time. A sub N is the same as it was last time. But if I have the first term in the sequence, right, and if I can find the common difference, and someone's like, find the 23rd term in the sequence. Like if I'm doing 2, 4, 6, 8, ... and someone's like, find the 24th term in that sequence, I don't have to be like, okay, fine, 2, 4, 6, 8, 10, 12, blah, 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 and keep going. I don't have to do all that. I have enough information to use that formula, plug it in, and get myself an answer. Okay? So let's see. Let's see if that's what we have directly in front of us. Find the 12th term in the sequence, 4, 7, 10, 13, blah, 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 blah. All right? Well, what I said last time is the recursive formula is only helpful if I have, in this case, the 11th term in the sequence, which I don't. The explicit formula is useful if I'm trying to find some number way the heck out here, which is what I want to do. So I'm going to write the equation in its full, a sub n equals a sub 1 plus n minus 1 times the common difference. I'm going to find out what I can find out, okay, and then plug in everything I can. I care about the 12th term in the sequence, so n is 12. Okay. It looks like my first term, a sub 1, is 4. And then I have 4, 7, 10, 13. Looks like I'm adding 3 every time. My job is to find the 12th term. So I need to find a sub 12. Do I have the first term? Yup. Do I know what n is? Yup. Do I have 1? Yep. Do I have d? It's 3. I can move on. So I need a sub 12, the 12th term. That's going to equal a sub 1, which is 4, plus parentheses, n, which is 12, minus 1, times the common difference, which is 3. And now it's just a good old-fashioned PEMDAS. 4 plus 11 times 3. PEMDAS says you always do stuff inside the parentheses first. PEMDAS says you always do multiplication, division before you add, subtract. And then you just add them numbers. And there you go. So would it have been the end of the world to go 4, 7, 10, 13, 16, blah, 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 all the way up to 12? Nah. No, not really. But this is a lot, maybe faster, and it's a whole lot more convenient if I were to ask you to find the 83rd term or something crazy like that. Because I can count up to 12 just fine, but I really don't want to have to count up to 83 by 3s using different numbers if I don't have to. Rather not. Big no thank you on that one. The first term of an arithmetic sequence is 9, and the sixth term is negative 6. Find the fourth term. Okay. The first term of an arithmetic sequence is 9. And the sixth term is negative 6. Find the fourth term. Okay, so let me write out my equation. I have a sub n equals a sub 1 plus n minus 1 times d. Let's plug in what I know. Right now, I'm not going to focus on that. I'm just going to put a squiggly there. I'll get to it later. The first term is 9, so a sub 1 is 9. The sixth term is negative 6, so a sub n is negative 6, and it's the sixth term, so n is regular 6. Alright, so a sub n is negative 6. That equals a sub 1, which was what? 9, all sloppy over there, plus parentheses 6 minus 1, and I don't know the common difference. Kind of working backwards here. All right, I can handle this. I know Algebra 1. 9 plus 6 minus 1 is 5, so 5d. Right now it's just a two-step equation. Subtract 9 from both sides. Subtract 9 from both sides. Cross u out. That gives you negative 15 equals 5d. Divide both sides by 5. D equals negative 3. Yuck! Done? Nope. See, I have to use this information to do this exact same thing again and now find the fourth term. So let me erase this. Now I need to find the fourth term. So all this information I'm just going to erase for a moment. Okay, I need to find the fourth term. Let's get a different color. The first term of an arithmetic sequence is 9. I still care about the first term. The sixth term is -6. Probably don't need that because now I need the fourth term. So n is now 4 and d is -3. So if I were to use the same exact equation that I did over here, right? A sub n, and I care about the fourth term, so a sub... Okay. A sub n is a sub 4 in this case, equals a sub 1, which is 9 like it was last time, plus, parentheses, n, which is 4, minus 1 times the common difference, which I just found out to be -3. So let me put parentheses, -3. According to PEMDAS, I do stuff inside the parentheses first. 4 minus 3 is regular. I'm sorry, 4 minus 1 is regular 3. Look at me accidentally working ahead. -3 times regular 3 is -9, and a number plus its opposite is 0. So the fourth term in this sequence is 0. Interesting. So that was a weird one. We had to kind of go backwards a little bit and do some interesting stuff. But that's arithmetic sequence. Okay? We learned 2 formulas. First one, not that important. The second one, much more important. And you're going to really want it when you have to find like an 800th term in a sequence. That's not stuff that you'll do until like, Algebra 2 or pre-calc or something like that. Okay? Okay, that was great. Bye. What up, what up? So today in Back to Basics, we are going to discuss scatter plots. In this first problem, we are to identify any outliers, gaps, or clusters. Well, let's just see what we have. We have ourselves a negative correlation, so I'm just going to write out neg for correlation. I see a gap right there. And I see an outlier right there. No clusters. No clusters at all. It is a negative correlation. And if you're wondering why is it a negative correlation, I mean, there's that big space in the middle and there's an outlier. There's so many dots going in the correct direction that just one person out of place doesn't make a difference. Okay? Negative correlation. The problem on the right, on the other hand, is a no correlation. And the reason why it's a no correlation is because it goes down, and I don't have any room. I'm just going to erase and say no correlation. Again, the reason why is it's going down and up. It's negative and positive, which is impossible. So it's nonlinear, unlike the first one, which was linear. It's nonlinear, and there's no correlation. I don't see any outliers. I don't see any gaps. And I don't see any clusters. So that's easy. Okay. Now a cluster, for those of you who are wondering, where if I would have put like a bunch more dots like right here, boop, 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 that would be a cluster, but it doesn't really happen. What happens if I do this? Ooh, thicker dots. Yeah. Now that would be a cluster. It wouldn't change much anything. All right. About how many? Okay, so what do we have here? We have the scatter plot shows the total earnings of a food server in one day. So after it looks like that they make nothing if they work 0 hours. That makes sense. And and then it just goes in that direction. So it's a positive correlation. The more hours they work, the more dollars they make. That makes sense. About how many hours must the server work to earn $70? All right, well, 70 is here. All right, so maybe I'd say around 3.5 hours. So we'll say 3.5 hours. The key word is about, which means you're not looking for an exact answer, so don't expect an exact answer. I knocked my iPad over. That's embarrassing. It's embarrassing. About how much does the server earn in 5 hours? All right, well, 5 hours is a little over 80, and it looks like each of these marks go by 10, so we'll say 85, because it's right there in the middle. Describe the relationship shown in the data. I'm not going to write it out because writing with this Chromebook is never the best idea, but it's a positive correlation. The more hours this person works, the more money this person makes. And my face is gone. All right. The more hours that person works, the more money that person makes. Makes sense. Estimate the line of best fit. Okay. So I'm going to draw a line to the best of my ability. It's a shame I can't draw a line, an actual line. But we start out at 0, 0, and we go like that. Is that line perfect? No, absolutely not. But I'm going to put 2 dots there that might be a good estimate. I'll put, first off, I like 0, 0, and I like that one. Now remember, a line is going to be in slope-intercept form. Y equals mx plus b, where m is the slope and b is the y-intercept. So I have my slope there, and I have my y-intercept there. Okay? My y-intercept is 0. That makes sense because if I don't work any hours, I'm not going to make any money. So my y-intercept is 0. If I want to find the slope, see the green dots that I put there? This is an estimation, by the way. It's not a perfect science. Okay, so I could do slope by doing rise over run. I rise 10, 20, 30, 40, 50, 60, and I run 1, 2, 3 hours. So my slope is going to be rise 60, run 3 hours. In other words, 20. So a line of best fit that I could use is going to be y equals m is my slope, and I said that my slope is going to be 20, 20x, 0 is my y-intercept. So I can put plus 0, but why would I waste my time? Even though I literally just did, I don't need it. That would be a line of best fit. And what this means is this person makes about $20 an hour. About. Okay. The scatter plot shows the number of drifting scooters sold by the company. I don't know what a drifting scooter is, but they're probably homeless and we need to get them help. In what year were 1,000 scooters sold? All right, well, here's the scooters sold. 1,000's right there. That seems to match up with 2014. About how many scooters were sold in 2015? Well, here's 2015, even though the number is not there. It looks like it's between 800 and 1,000, but much closer to 1,000. So we'll say 950. It's a good estimate. And the key word there is about. Describe the relationship shown by the data. I'm going to use words to describe because I don't have writing again on this thing is not the best idea. It seems that as the year goes on, or better yet, as the year goes on, we sell less and less and less drifting scooters. Now, that's because we have ourselves a negative correlation like that. As the years go on, I'm selling less drifting scooters. Whatever a drifting scooter is. Oh, probably like a Razor scooter. Those are cool, yeah. Problem D. Assuming this trend continues, in what year are about 500 drifting scooters sold? So, let me see. 500 would be somewhere around here. So if that's 17, 18, we'll say 2019 is a good guess. That would be my guess. And again, these things aren't an exact science because that's the purpose of scatter plots. You're assuming and estimating quite a bit. Speaking of that, estimate the line of best fit. So I'm going to draw myself a line that kind of cuts through all the points there. I'm really nervous, so it's a squiggly line. Remember, slope-intercept form gives me the equation of a line, so y equals mx plus b. My y-intercept appears to be like right there. So every one of these marks goes up by 200. So this guy would be 1400, and it looks like my line went through a little bit underneath 1400. So I'm going to let my y-intercept be a little bit under 1400. How about 1350? How's that sound? And look what I have. Look what I have. I actually have two dots placed perfectly on the graph. So I could do the rise over run to easily find out what my slope would be. It's a negative slope. So negative slope. I rise 200. Remember, every one of these marks is 200. So I rise 200. And I run 1 year, 2 years. So negative 200 over 2. So writing everything out and simplifying, my final equation is going to be y equals m. Negative 200 divided by 2 is negative 100. That means they sell 100 less scooters per year. Oh, x, sorry. Plus... Oh, what did I say? 1350. Cool. All right. That'll do it for that one. Bye-bye, scatterplots. Nice knowing you. Bye. The scatter plot below shows the relationship between the time in minutes and the distance in miles that Julie walked on several occasions. Alright, so basically we have a scatter plot, line of best fits glued on it. So one day Julie went out and walked for about 15 minutes and walked for a little over a mile. And one day Julie walked for 55 minutes and walked for 4 miles, stuff like that. Based on the line of best fit, which is most likely the number of miles Julie would walk in 105 minutes. So basically what I need to do is I need to pretend that this line is still going. And given the fact that I have a track record of never being able to draw straight lines on this thing, I nailed it. Okay, 105 minutes is going to be this dot up here that's not even on the graph. But that dot up there, I can use a little bit of, estimation and say that dot up there would be a 7 if the graph kept going. So 7 it is. I'm sticking with it. 105 minutes should be around 7 miles if using this line of best fit as an estimate. A scatter plot shows the relationship between the distance x in miles from a local airport to airports in various cities and the time y in minutes a flight between the airports takes. The equation below describes the line of best fit. Based on the equation, which value is the most likely distance in miles between two airports when a flight between the airports takes 240 minutes? Now, 240 minutes is y, so be very, 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 very careful. It's tempting to plug 240 into x, but you're actually taking 240 and plugging it into y. So 240 equals 0.16x plus 58.62. Okay. Let's subtract 58.56, subtract 58.56. This gives you 181.44, I think. Comment if I'm wrong. That equals 0.16x, and you are now gone. Now, no matter what, there's no way I could do that divided by 0.16. So I'm going to have to refer to my calculator, or in this case, I'm going to use Siri. Okay, my calculator says 1134. Bada bing, I like it. How many more people chose summer instead of winter? Well, let's see. We've got summer right here, and it looks like 12 people chose summer. Rightfully so. Summer's the best holiday, or season, whatever it is. What else do we want? Winter. Winter lines up with 10, so it looks like winter is going to be 10 people. And the question was, how many more people chose summer instead of winter? Well, 12 people chose summer. How many more means you subtract the other guy, which is 10. And last time I checked, 12 minus 10 is 2. So 2 more people prefer the summer over the winter. Dunzo. How many black cherry trees are in between 70 and 85 feet tall? Well, this is a histogram. So it's like a bar graph, but things kind of give you a range instead of a definitive category. So in between 70 is going to include this block right here, that block right there, and that block right there if we're going to 85. So it looks like 70 to 75 is 8 people. Or what is this? 8 trees. 75 to 80 is 10 trees, not people, unless they're ents. And 80 to 85 is 5. So let's add them up. 8 plus 10 plus 5 is going to be 23 black cherry trees in between 70 and 85 feet tall. The bar graph below shows the average number of minutes Frank spends each week participating in 4 activities. All right, let's see what Frank's into. Frank likes to play games online. He likes to play sports. He likes to read. And he likes to social network, like a TikTok. Based on the information shown in the bar graph, which value is most likely the difference between the number of minutes Frank will spend reading the next 4 weeks and the number of minutes Frank will spend gaming online in the next 4 weeks. All right, so there's a little bit of trickery here. And the trickery is these phrases. It doesn't say week. See, this is Frank's weekly activities. So this is the challenge that you have to do. Yeah, we care about what happens with reading, and reading appears to be 175. And yeah, we care about Frank gaming online, which appears to be 120 maybe, because it's right below the line. So we'll say 120. So every week he spends 175 minus 120 more than, which is 55. Right? That's per week. This problem isn't asking for per week. It's asking for 4 weeks. So every week is 55, but every 4 is 220, which is awfully close to 224. So the actual number probably should have been 56, but how am I supposed to know that by looking at that? It's a prediction. Yeah. I like that. It was, you really have to read that carefully. I think most people would put A if they don't read this carefully, because they're like, oh, difference. I know what that means. That means minus that, minus that. And that makes sense, but you're not done with that. Tricky, tricky, tricky. All right, we have a stem and leaf plot, and we're supposed to find the median. Now, the nice thing about a stem and leaf plot is they're already in an order. So we have 5 and 7, and all the way up here we have 43. So the way you normally find the median is you put things in order and you go to the middle. So I'm just going to do this. Small, big, small, big, small, big, small, big, small, big. And I have my guy in the middle. My guy in the middle is 1, 9, which means 1.9. That changes everything. That's my answer. What up, what up? Today on Back to Basics, we are going to talk about box and whisker plots. Let me make my face smaller and move me over here. This is a box and whisker plot. It is a way to show data with an entire range and throw it all on a number line. What is it? What does it mean? What does any of this mean? Well, what a box and whisker plot does is it takes all of these numbers, okay, and it creates what over here is called a maximum. So I'll write that out. And a minimum right here. So if I were to list out all of, like if I were to play something realistic, a bunch of games in the NBA. And like I had 10 games where like one of the games I scored like 48, and another game I scored like 39, and another game I scored blah, 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 blah. I could use a box and whisker plot to say, well, my biggest was like, let's just say 82 points, and my lowest was that 38. My maximum is that number, my minimum is that number. But what's all this other, what are these things? Well, these are the whiskers. That's the box. And every chunk here, 1 chunk, 2 chunk, 3 chunk, 4, is going to be a quartile. Now, what a quartile means is 25% of the data. So if I had listed out all the points that I scored in a game in 10 games, okay, the lowest 25% of the data would live in this zone. The second lowest would live in that zone. This guy right here is the exact middle. We call that median in the math world. Now I'm above average over here, and my top 25% is here. Now this has a name. That's called lower quartile. You guessed it. This guy right here, upper quartile. That's supposed to be a U, upper quartile. The biggest minus the smallest is your range. That covers all 100%. And upper quartile to lower quartile is called your interquartile range. So lots going on here. Lots going on here. Okay? So let's do a few problems. We'll probably make one of these ourselves. Let's have some fun. Let's go. Use the box and whisker plot to answer the following. So Mrs. Sanchez period 1 math class results. So let's analyze what we have going on here. Somebody scored a 20. That's the lowest score. Somebody scored a 93-ish. That's the highest score. The median score is like 62. We could say something like 25% of the kids scored between 70 and 92. 50% of the kids scored between 29 and 70. Where did I get that 50 from? There. My interquartile range is 70 minus 29. Stuff like that. My lower quartile is 29. Stuff like that. What's the difference between the highest score and the lowest score? So we're going to estimate that this looks like a, what did I say before? 92. Let's go with it. This looks like it could be a 19. Let's go with that. 92 minus 19 is going to carry the 1, is going to be 73. That's the difference between the highest and the lowest score. The range, the regular range, is 73. Ooh, Miss Sanchez again. What percent of the class scored between a 29, which was here, and a 70, which was here? Well, between a 29 and a 70 is this chunk right here, which is 25% of the data, and this chunk right here, which is also 25% of the data. So what percent of the class scored between 29 and 70? 50% of the class, because 25 plus 25 is 50. Now you might be thinking, no. That is not the same size as that. I know that. It doesn't have to be. What this is telling us is that a lot of people scored in between like 63 and 70. And these scores down here are a lot more spread out. So we're not looking at the size of the rectangle. Okay? It's just what it looks like. You know what I mean? You know what I'm saying? Use the box and whisker. Again, Mrs. Sanchez. Did half of the class score a 63? Well, the median is 63. Does that mean half the class scored a 63? No. That just means the score in the middle is 63. Half the class scored higher than that. Half the class scored lower than that. So if the question was, did half the class score higher than a 63? We could say yes. But this question is saying, did half the class score a 63? And the answer is no. No. Now, what we're going to do is we're going to use this information and we are going to make ourselves a box and whisker plot, and this is how we're going to do it. Okay, we have 3, 5, 3, 7, 9, 8, 1, 6. Order the numbers from least to greatest. Got it. 1, 3, 3. 5, 6, 7, 8, 9. Find the median. All right, how many numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8. So the median is going to be the average of those two. All right, so the median is going to be 5 plus 6 over 2. 11 over 2 is 5.5. So the median, so let's get rid of you. I don't need you. Look like a stapler. I don't need you anymore. The median is 5.5. Find the lower quartile by finding the median of the data below the median. All right, so here's the regular median. I need to take this information and find the average between that. So the two middle numbers are 3 and 3. So what I would do is like, oh, there's two medians, so you got to add them and then divide by 2. Well, this is 6 divided by 2, which means this median, the red line, or in other words, the lower quartile is going to equal 3. Okay, we're going to do the same up here, find the upper quartile by going above the median and finding the average here. So 7 plus 8 divided by 2 is going to be 15 divided by 2, which is 7.5. That makes sense. 7.5 is directly in between 7 and 8. And now we have all the information we need. All the information we need. I know that you are the minimum. It's also called the lower extreme, by the way. You are the maximum, called the upper extreme. And I have enough information to do everything I need. So let's create a box and whisker plot. Let's start at 0 and go up to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll throw an 11 in there for good measure. My minimum is 1. My lower quartile is 3. My median is 5.5. My upper quartile is 7.5. So I'm drawing a line in between 7 and 8. And my maximum, my upper extreme, is going to be 9. Connect the whisker to the box. Create your box and finish your box. And this looks awful, but that's how you do it. Yay! Let's move that out of the way. So we just created a box and whisker plot. Yeah. I'm trying to fix the way it looks by doing that, and I'm not sure that helped. But it doesn't look that bad. I mean, it doesn't look good. It doesn't look that bad, though. Yeah, that's better. That's better. Yeah. Yeah. What do we got next? Make a box and whisker plot. All right. So I have a bunch of numbers. I've got 26, 27, 29, 29, 29, 30, 30, 31, and 33. All right, what do we have here? How many numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so this is nice. My median is 1, 2, 3, 4, 5. The number directly in the middle, which is 29. Okay, what I now need to do is I need to find, so this is my median, there it is. My lower quartile is going to be the median of these 5 numbers to the left. So 1, 2, 3, 4, 5. So my median, my lower quartile is U. My upper quartile, let's change number colors here, is going to be the median of the right side. So that's my upper quartile. You are my minimum. You are my maximum. So let's create a line. Do I have enough? 26, 27, 28, 29, 30, 31, 32, 33. Perfect. 26, 27, 28, 29, 30, 31, 32, 33. My minimum is 26. My lower quartile is 27. My median is 29. My upper quartile is 30. And my maximum is 33. Connect, 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 connect. There you have it. You can do these on the calculator too, but what fun is that? I had so much fun making these. I actually do like box and whisker plots. You know, they're called box and whisker plots. Reminds me of cats. I love cats, and cats love to sleep in boxes. Oh man, this is probably the best math thing on the entire planet. Thanks for watching. Have a good day. Bye. What up, what up? Today we're learning about one little, two-way tables. Remember multiplication tables when you were in elementary school, and when you had to do like 6 times 7, you'd find the 6 up here and you'd find the 7 over here, and you'd match them up to find out that 6 times 7 is 42. Remember that? Remember that? Of course you do. Two-way tables are similar, just it gives you 2 pieces of information. For example, in this problem, we have some information about a fundraiser and then genders participating in the fundraiser, and we can see if a female did or didn't participate, or if a male did or didn't participate. And when we're being asked a question, we literally just look at the fundraiser information, whether they participated or not, and the gender, whether they're male or female, and just kind of, see where they meet. So in the first question, where we have how many female students participated in the fundraiser, we're looking at our female row, we're looking at our did participate column, and they match up here at 51. So the answer is 51 students, 51 females did participate in the fundraiser. How many males did not is the next question. So we look at our males, we look at did not, and our answer is 30 males did not. Okay? Those are probably one of the more friendlier types of problems that you will see in all of 8th grade math. We're going to do it again. How many male students participated in a science fair? So we're talking about whether people did or didn't participate in the science fair, and we're talking about whether people are female or male. How many male students participated in the science fair? So that would be the yes column and the male row, and we get 32. How many female students did not participate? That would be the female row and the no column, and we have 15. Okay, again, these types of problems are very friendly. This is where it gets slightly complicated, but not too much. The first question is find the marginal frequencies. Marginal frequencies is just a fancy word for totals. And let me tell you something, I like totals. Alright, so I'm going to add a new column over here, total. And I'm going to do the same thing down here. Again, marginal frequencies is just fancy talk for totals. And the way I find the totals is I add up the rows and the columns that lead up to that section. For example, if I wanted to find this total right here in that area, what I'd do is I'd add up 41 plus 30, and that gives me 71. And what this means is there are 71 juniors because 41 attended, 30 did not. So if I wanted to find out what my total seniors were, I would do 52 plus 23, which is 75. 75 seniors total attended. Okay? Moving further, sorry, I'm going to quick adjust something so I don't have so much lag on the video. I don't like lag. Let me clean some of this up too. Now, if I wanted to find out how many total people attended the school play, I would add 41 and 52, and that gets me 93. If I wanted to find out the total number of people who did not attend the school play, 30 and 23 make 53. Now I still have one total area that I haven't added up yet. And that's the bottom right above my face, right there. Okay, and the way I can calculate that is I can either add 71 and 75 vertically, 146, or I can add 93 or 57 horizontally, 146. And either way, I'll get 146. That's my total people total. So, usually there's a word problem before this, and it'll say, you interviewed a bunch of students. And 41 juniors said they did attend the school play, and 23 seniors said they did not, and blah, 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 blah. And you can add everything up, find your totals, which is a fancy word for marginal frequencies. So step 1 is done. How many seniors are there? Now, did I say anything about the school play? No. I just said how many seniors are there. So you care about those who attended and those who did not, and I already know the answer to that. It's 75. So when it asks you one category, these are two-way tables, so it gives you two categories, but when it completely removes the one category, you care about the total. So if I asked you how many juniors are there, I could just go right to 71. If I asked you how many total people attended, I can go right to 93, so on and so forth. What percent of everyone was a junior who attended the play? Remember, when you're talking about percents, you're talking about a part over a whole. Okay, and so what percent of everyone? So my whole group is everyone, and that's 146. What percent of everyone was a junior who attended the school play? Now, how many juniors attended the school play? 41. Now, I have to find percent, and the way I do that is percent literally means out of 100. So I'm going to have to figure out what 41 divided by 146 is. What's 41 divided by 146?
It's about 0.2808.
2808. Now, is that a percent? No, that's a decimal. How do I turn decimals into percents? Multiply it by 100. And the way you multiply 100 is you just move that decimal over twice. So 0.2808 is the same as 28.08%. So we could say that 28%, a little bit more than 28%, was a junior who attended the school play. Okay, so these problems get a little confusing once you start throwing percents in there, but it's not a world ender. It's just you're going to have to whip out a calculator usually. Sometimes the numbers are friendly enough, but in this problem too, the numbers are not going to be friendly enough. So step 1 is find the marginal frequencies, find the totals, and I like totals. So I'm going to add total over there. I'm going to add total down there, and I'm going to start adding things up. The total for plan A means I'm going to look at the plan A column, and that's 78 plus 175, which is 223. No, 23. No, it's not. 43. No, it's not. 53. Oh boy. The total people who have cell phone company plan B is going to be 94 plus 135, which is 229. Handled that one a little bit better. The total people who have the limited plan is 78 plus 94, which is 172. And the total people that have the unlimited plan is 175 plus 135, which I believe is 310. The way I find my total is I can either add up 172 plus 310, or I can add up 253 and 229. Either way, I will get 482. Why did I put 9? 482. So I'm just double checking my numbers, making sure I didn't make any mistakes, because I kind of made a mistake by putting that 9 there, and I don't know why I did that. I think I'm good. And what I'm doing is I'm adding all the rows, all the columns, and all of them together, and it looks like I'm in okay shape. So find the marginal frequencies, cha-ching. How many people have a limited plan A? A limited plan A. So I'm talking about limited, I'm talking about A, and that's 78. Okay, so let's clean all this up, because I have a feeling with the next problem saying percent, it's going to be wacky pants. So the next question says, what percent of people on plan B? So now I don't even care about the plan A kids. I only care about, remember, percent is part out of a whole. And in this case, the whole group that I care about, the whole is 229. I'm removing A from the question. So what percent of people on plan B has unlimited? That group of people is 135. So be very careful. When it's very specific for your percents, you have to be a little bit more careful. You have to exercise a little bit more caution. What is 135 divided by 229?
It's about 0.5895.
Is that a percent yet? Nope. Got to multiply it by 100. So my final answer is going to be 58.95%. All right, two-way tables. I had to make my face smaller to fit it all in. It's very, very upsetting. Here, let's see if I can fix it now. Yeah, no, I give up. All right. What's this do? Whoa! Bye! What is the probability of randomly selecting a green marble? Probability is what you want out of your total amount. So let's find our total amount. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We got 20 marbles. I care about how many of them are green. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 20 simplifies out to a half. Now you can answer a probability problem as a fraction, but if you also want to be fancy, you can turn it into a decimal or a percent. So you have half chance of reaching into here and randomly selecting a green marble. What is the probability of randomly selecting a green marble, putting it back, and selecting a blue marble? All right, this is compound probability. In this jar, we have 20 marbles total. I counted ahead of time. First, I want to pick a green marble. I counted the green marbles, and there's 10 green marbles. So our probability of pulling out a green marble is 10 out of 20. Now we're taking that marble and putting it back. So once again, we have ourselves 20 marbles. So I have a total again. Okay. If I want to find the probability of selecting a blue marble, I have 3 blue marbles. So my probability of selecting a blue marble is 3 out of 20. When you have compound probability, you multiply the fractions together. I'm going to simplify that guy to 1/2. So I have 1/2 times 3 over 20. 1/2 times 3 over 20 is 3 over 40. So this problem, which is called replacement, by the way, because I put my marble back, says, what is the probability of getting a green marble, putting it back, getting a blue marble? In that order, 3 out of 40. What is the probability of randomly selecting a blue marble, keeping it, and selecting a red marble? Right now, we have 20 marbles in here. So selecting a blue is going to be 3 out of 20. So once that blue marble is gone, that leaves me now with 19 marbles. What's the probability of me reaching in here and randomly selecting a red marble? Well, I have 1, 2, 3, 4, 5, 6, 7 red marbles. And when you have two things going on, this is called compound inequality. Since I kept that marble, it's called without replacement. What you do is you multiply the fractions, you get 21, and 20 times 19, I'm pretty sure, is 380. Those guys do not simplify, so that is your answer, 21 over 380. Back to basics again. Systems of equations. Systems of equations are just one of those topics that people don't really seem to enjoy. Unless you're me, in which case I love them. But this is what systems of equations look like. I give you 2 equations and I ask you to solve that system of equations using whatever method I ask you to. Now there's 3 methods that we're going to use: graphing, substitution, and elimination. Today's focus is graphing. So what's our answer going to look like? Well, our answer is going to be me graphing 2 equations on the same coordinate plane and finding out where those lines intersect. That's going to be my answer. So let's graph this guy. Let's graph. I have y equals 1/3 x minus 4. So I'm going to start at -4 on my y axis because that's my y-intercept. Put a dot there. My slope is positive 1/3. So that means I go up 1, right 3. Up 1, right 1, 2, 3. Up 1, right 1, 2, 3. Uh-oh, I'm out of room. So I can go to my original dot and go down 1, left 3. See, I'm literally taking my little pen here and I'm going to my dot and going down 1, 1, 2, 3, and then drawing that dot out. Once I have as many dots that I can draw, I'm going to draw a straight line through those dots. I like to put as many dots as I can just because you never know what's going to happen. Let's graph the second one in blue. My other equation is y equals -7/3 x plus 4. So that means I start at 4 on the y-intercept, on the y-axis, because that's my y-intercept. Getting ahead of myself. Just so excited. If I want to use the slope -7/3, I would go, since it's a negative slope, I go up and to the left. Up 7, left 3. Well, I can't go up 7. I can't even go up 2. So instead of going up 7, left 3, I can go down 7, right 3. And that's what I'm going to do. I'm going to count down 1, 2, 3, 4, 5, 6, 7, right 1, 2, 3, and put a dot there. And as you would have guessed it, I can't do it again. So I have 2 dots, but that's really all I need. I'm going to draw a line straight through it. Perfect straight line. Now my 2 lines intersect at that guy right there. And a solution to a system of equations, when I solve a system of equations, it's the point that makes both equations true. In other words, it's the point where the lines intersect. To get to that green dot from my origin, I go right 3, down 3, which means my answer is going to be +3, -3. So if I were to take the point +3 and plug it into x, and the point -3 and plug it into y, I'm going to get a true statement for both equations. That's how I would check my work. Let's do it again. We have ourselves y equals 1/3 x plus 3 and y equals 2x minus 2. So I'm going to graph that top one in green. I start at 3, so I go up 1, 2, 3, put a dot there. My slope is 1/3. So I'm going to go up 1, right 3, up 1, right 3, put a dot, up 1, right 3, ran out of room. Go to my original dot, and instead of going up and to the right, I can go down and to the left, which gives you the same line. Down 1, left 3, put a dot. Down 1, left 3, I can't. But I have 3 dots, and that's all I need. Well, that straight line there. I'm going to graph the other one in red. I'm going to start at -2 because that's my y-intercept. So I'm going to put it on the y-axis. My slope is 2. Or, since it's not a fraction, I'm going to turn it into a fraction, 2/1. Positive slope, up and to the right. So up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2, ran out of room. Go to my original dot and go down to left 1, down to left 1. I'm going to put a line through all of my points. Boom. That's where the magic happens right there. If I actually knew how to draw a line, it would look a whole lot better. But my 2 points, this is why I always put as many points as I can. Because even though my line wasn't perfect, I know where that red line and the green line meet because of the dots that I made. And it falls right there on that blue dot that I made. So that dot exists at 3, 4. So my answer is the point 3, 4. My answer is not a graph. I use graphing to get to my answer. My answer is a point where my lines intersect, and I have to write out the point. So my x value is 3, my y value is 4. If I wanted to plug them in and check my work, I would plug the 3 into the x values, the 4 into the y values, and I'll get answers that match up for both of them. That's how I know I did it right. Let's do it again. Do it again. This is actually going to be friendly. It doesn't look friendly at first because of the missing x on the bottom and the -7 as a slope. Ugh, trust me. I'm going to start at -3. My slope is -7 or -7/1. Negative means I go up and to the left, so I can go up 1, 2, 3, 4, 5, 6, 7, left 1, put a dot there. I only have 2 dots. That's all I need. All is well. Now my other equation is y equals 4. Where's my slope? It's not there, which means my slope is what? 0. And 0 lines are perfectly horizontal lines. Zero slopes are horizontal. Plus, if y is 4, then y is going to be 4, and 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 no matter what, y is going to be 4. These two lines intersect at, you guessed it, y is 4, but also in this case, x is -1. In order to get to that red dot, I go left 1, up 4, so -1, +4. Okay, so that one looked pretty bad at first, but as Eminem would say, it's not so bad at all. I guess his friend said that. Is it Dido? More like Dodo, right? So I have one more. Let's just do it. Let's not mark everything up. I don't know why I'm just waiting. I'm going to start at -2 in red. -2. My slope is -2/3. So up 1, 2, left 1, 2, 3. Up 2, left 1, 2, 3. I can't go left 3, so I'm going to go to my original dot and go down 1, 2, right 1, 2, 3. I can draw 3 dots. I only need 3 dots. And so there's my line. Pew pew. My other line starts at +4. My slope is -8/3, so negative slope is up and to the left. Well, I can't go up 8 and left 3 because I can't even go up 1. I can go up 1. But I can go down 8 and right 3, so I'm going to go down 1, 2, 3, 4, 5, 6, 7, 8, and go right 1, 2, 3, and look at that. Look at that. Draw your line. My lines are so bad. But I know where they intersect because of the dots. And they intersect at go right 3, go down 4, 3, -4. And that's going to do it, kids. Okay, solving systems of equations means finding out where the lines intersect. Now, that's graphing. Wait until substitution. Wait until elimination. Just you wait. Bye.
Well, hey y'all, Peyton Manning here, quarterback for the Denver Broncos, and I'm here to teach y'all how to solve systems of linear equations by graphing. So let's see what we got going on here. We have ourselves our TI-84 Plus calculator, and it looks like we have ourselves a problem. Solve the system of equations by graphing. Y'all, as everybody already knows, the way you solve systems of equations by graphing is finding out where these two lines intersect. Now, what I did for y'all, because I'm so kind and friendly and such, is I solved both of these equations for y so that we could just throw them in right into our calculator. So this is how it's done, y'all. First things first, hit the y equals button right there. Now, we're going to graph both of these equations at the same time. This first equation we're going to make our y1. So type that in, -1/2. The way we'll show 1/2 is by typing 1 divided by 2. Seems to make sense. Your x is up here. Hit that. -6. All right, y'all, that's the first equation. Hit down to get to the second equation. This is a little friendlier. 2x -3. Now that we have both of our equations tapped in, let's hit graph and see what we have. There's the first equation. And there's the second equation. Now we're supposed to find out where these two lines intersect, but let's get a closer look. I can't really tell. I mean, I don't know, is it -1 point? I don't know, y'all. I'm kind of confused. My eyes aren't that great. So what I'm going to do is I'm going to calculate where these two intersect. Well, it only makes sense that the way to calculate them is by hitting that calc button right there. So hit second trace. And since we want to intersect, go down to 5. 1, 2, 3, 4, 5. Now these calculators are kind of confusing. I don't know why they do this first curve stuff. I'm going to make this super simple. Once you hit intersect, you just hit enter again, and hit enter again, and lo and behold, we have ourselves an answer. The intersection between these 2 points is -1.2 for x and -5.4 for y. So, the answer to this question, solve the systems of equations by graphing, is the point -1.2, comma, -5.4. 4. And there it is, y'all. That's our answer. Yippee-yi-yo-ki-yay. Boy, oh boy, what a great answer that was. That is more exciting than getting draft first overall in the NFL draft. That happened to me, y'all, and I won like a bunch of MVPs afterwards. Go me. Well, thanks, y'all, for watching. I hope you learned a little bit about graphing. Go Broncos! Not how? How do you turn this thing off? Is it that button? No, it's not that button, right? No. Wait, no. Is it this button? No, that's... Oh, here it is.
Back to basics. Welcome to part 2 of our journey. And this journey is called Solving Systems of Equations. In part 1, we learned how to solve systems of equations by graphing. And so we graphed a line, and we graphed another line, and we found out where those lines intersected, and our answer was a point. Well, we're not doing graphing today, kids. We are doing substitution. So let's get started. I have a billion trillion videos on substitution on my YouTube, so if this video doesn't do it, I literally have like 4 or 5 more. So you can watch one of them. But here's one just for fun. This one you get to see my face. Look at that. Handsome. All right, solve by substitution. Step 1, make sure one of your equations is already solved for a variable. Check. It took a while there. Step 2, take that equation and plug it into the variable in the other equation. So according to the bottom, y is 2x. So what I'm going to do is rewrite the top. 6x plus 7, but instead of y, remember I found out that y is 2x. So I'm going to turn y into 2x. And I'm going to continue writing out the top equation. Equals 20. Now I have just a bunch of x's, no y's. So 6x is 6x. I can combine like terms by doing 7 times 2, 4, which is 14x. And that's going to equal 20. 6x plus 14x on the same side means I can combine those because they're on the same side. That's going to give me 20x. And 20x equals 20. Let me see, is x all by itself? No. What's in the way? Oh, 20 is being multiplied by x. So the opposite of times is divide, and I can divide both sides by 20. 20x's sounds like my dating history. Maybe subtract like 18. So x is 1. I guess I'm done, right? No, I'm not done, because I found x yesterday. In the last video when we did these problems and we graphed, we had a point. And a point is an x and a y value. Well, I just have the x. Can I find the y? Sure I can. It says right here that y equals 2x. So now that I know that x is 1, I'm going to rewrite that equation, but instead of x, replace it with 1. And 2 times 1, let me see, let me get out my calculator, is 2. So if I know I'm going to get a point for an answer, and the x value of that point is 1, and the y value of that point is 2, then my point is going to be 1, 2. And that's my answer. Okay? This one's a little worse. Let me see. I have 2x minus 3y equals negative 1, and I have y equals x minus 1. Step 1 is take any equation and solve it for any variable. Oh, check. The bottom is already solved for y. Step 2 is take that one and plug it into the other equation. So now that I know that y is x minus 1, I'm going to rewrite the top and replace y with x minus 1. I'm going to rewrite the top and replace y with x minus 1. Substitute. It's like if you had a substitute teacher. The substitute teacher comes in and just takes the place of the regular teacher. They're not as handsome or as exciting. They do the job and they do it adequately. Now look what I have. Distributive property. I have 2x. That just drops down. Negative 3 times x is negative 3x. Very, 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 very often when you do these problems, you're going to have to do distributive property. Not every single time. We didn't have to do it last time. But very often, I'd say about maybe half the time. Negative 3 times negative 1 is positive 3, and that equals negative 1. Is x all by itself? No. In fact, you have 2x's on the left that I can just combine right there. 2x minus 3x is negative 1x, or negative x, but I'm going to write out negative 1x because it's easier for me to visualize. And then plus 3 comes along for the ride, and equals negative 1 comes along for the ride. Is x all by itself? No. What's in the way? Negative 1 and positive 3. Which one should I get rid of first? The negative 1 on the left or the positive 3 on the left? Well, the thing that's floating around is what I should get rid of first. So why don't we subtract 3? Why don't we subtract 3 and cross you out? I'm going to bring the negative 1x down. Negative 1 minus 3, let's see, I'm already down a foot, and if I go down 3 more feet, I'm now down 4 feet. So negative 4 feet. Is x all by itself? No. What's in the way? Negative 1. How is negative 1 in the way? It's being multiplied. How do I get rid of it? Divide. Divide everything by negative 1. Divide everything by negative 1. And let me put it up here. X equals negative 4 divided by negative 1 is positive 4. I have my x. Do I have my y? No. How do I find my y? Take that x value and plug it into any of the original equations. In the last one, I had something like y equals 2x, so it was easy to plug it into that one. Similarly, in this guy, I have y equals x minus 1. So it would be easier if I took that bottom equation and rewrote that out to find my y, and instead of x, replace x with 4. So I have 4 minus 1, and y is going to equal 3. So if x is 4 and y is 3, I'm going to get the point 4, 3. All right. All right. It just seemed to get worse and worse and worse and worse and worse. Step 1. Make sure any equation is solved for any variable. Is that done? Yeah. The top equation is already solved for y. So I'm going to take that guy and plug that into the bottom equation. So I'm rewriting the bottom equation. But I now know that y is negative 3x plus 5. So I'm going to replace the bottom y with negative 3x plus 5 because y is the same thing as negative 3x plus 5. I'm just saying, hey, look, why is this guy up here? Why don't you replace the y down there with that? And that's exactly what I did. Distributive property. Negative 4 times negative 3x is going to be positive 12x. Negative 4 times positive 5 is going to be negative 20. 5x should have come along for the ride originally. Equals is equals, and negative 3 is negative 3. Right next to each other, I have 5x and 12x, and since they're on the same side, I can just combine them. 5x and 12x makes 17x. Take away 20, and that equals negative 3. Is x all by itself? No. What's in the way? Negative 20. Anything else? 17. Which should I get rid of first? How about that negative 20? How about we add 20, add 20? So if I'm down $3, but I get $20, looks like I am $17, baby. Is x all by itself? No. What's in the way? 17. How's 17 in the way? Times. How do I get rid of it? Opposite of times. What's that? Divide. Divide. Divide both sides by 17. X equals 17 divided by 17 is 1. So I found my x. What should I do now? Find y. Look at the original equations. Which one would be easier to find y for? The top equation or the bottom equation? Well, it looks like to me that it should be the top equation, because if I'm finding y, why don't I select the equation that has y equals, because I'm finding y. So I'm going to rewrite the top equation, but instead of x, I'm going to put 1 because x is now 1. So I'm rewriting the top equation, y equals negative 3x, but instead of x, I have 1 plus 5. Negative 3 times 1 is negative 3. Wow, that looks really choppy. Negative 3 plus 5 is positive 2. Y equals 2. X equaled 1. Y equals 2. My final answer is the point 1, 2. Okay? Is it becoming a little bit more clear now? This is where you repeat back. Crystal, I'll try it again. Is it becoming a little more clear now? Good. I'm going to Blue's Clues these types of problems and just expect you to answer back. Are you guys ready to do the next problem? Good. What's that? Oh, it's a board. That's my Dora impression. Step 1. Make sure one of my variables is already solved for one of the equations. Oh no, none of these variables are y equals or x equals. None of the equations are, I mean. So what's the easiest to do? To solve the top one for x, solve the top one for y, solve the bottom one for x, or solve the bottom one for y? Looks to me that since y is almost all by itself, it would be easier to solve the top equation for y. So let me rewrite out the top equation. Negative 4x plus y equals 6. Step 1 is to get x or y all by itself. And in the previous 3 problems, y was all by itself every time. Right now it's not. But it's not a bad problem. All I have to do is just add 4x to both sides. Add 4x. Cross that out. Now I can bring down y equals positive 4x, positive 6. I'll write it out as 4x plus 6 because I want to keep in that habit of writing it out in slope-intercept form. So that was the top equation. Now that I have y equals 4x plus 6 on the top equation, I could take that and plug it in to the bottom equation. So I'm going to rewrite the bottom equation, negative 5x minus, but instead of y, I'm going to put parentheses 4x plus 6 because y is 4x plus 6. And I'm going to finish writing out the bottom equation. I have a negative in front of a parentheses. Does that mean I just get rid of the parentheses? No, that just means the entire parentheses is its opposite now. So you take the negative and multiply it to everything. So negative 4x is negative 4x. Negative positive 6 is negative 6. It's called distributing the negative. Whenever you have a negative in front of a parentheses, take everything in that parentheses and flip the sign. Okay? Negative 5x lives in front. Equals 21 lives out there. Look, 2 x's right next to each other. It's like my high school reunion. Just kidding. I wasn't invited, but I can combine those. Negative 9x minus 6 equals positive 21. Is x all by itself? No. I have a negative 6 that I can add to both sides. I have a negative 6 that I can add to both sides. So now I have negative 9x equals 27. Is x all by itself? No. What's in the way? Negative 9. How do I get rid of it? The opposite, which is divide. Divide everything by negative 9. Divide everything by negative 9. And positive 27 divided by negative 9 is negative 3. So I have my x now. How can I find out my y? Well, look what I did. Look what I did over here. I found out that y equals 4x minus 6, plus 6. So if y is 4x plus 6, why don't I just say y is 4, but instead of x, say negative 3, because I know x is now negative 3. And then keep writing that out, plus 6. Y is negative 12 plus 6. Negative 12 plus 6 is negative 6. So my x was negative 3. My y was negative 6. My final answer is going to be the point negative 3, negative 6. So that's substitution. Okay, that's an algebraic method of solving systems of equations. The next one we're going to do is elimination, which is another algebraic way. And if you ever take a test or if you're ever given a problem and it says use any algebraic method to solve, you're going to learn when it's convenient to use substitution and when it's convenient to use elimination. These were convenient to use substitution for the most part because y was all by itself. But in this problem, I could have used elimination. What does that mean? You're just going to have to watch the elimination video to find out. Give me that. Give me those sweet YouTube hits, baby. It's the second time I said baby today. Whew. I'm on fire. Bye. Back to basics, part 3 of our series involving systems of equations. This is the part that involves us going back in time and having a Western themed. I think I'm getting things. Oh, that's Back to the Future. Two things I love so much. I just, want to enjoy both at the same time. Can't. This is elimination. Those of you who have profoundly amazing memories might look at that and say, wait a gosh darn minute, sir. When we did the substitution method, that was the last problem in the video that you did. Are you telling us that we're going to do this exact same problem again? Yes, I am telling you. And we're going to use elimination to do this problem. The concept of elimination is you're going to eliminate a variable based on the way your equations stack up. Now, I am purposely wording my words appropriately. And when I say stack up, look at the x's. See how the x's are just like right on top of each other and the y's are right on top of each other and the equal signs and the numbers are just right on top of each other? That's what I want to happen for elimination. What I also want to happen for elimination is I want one of my letters to be the exact same as the other letter, but opposite. What do I mean but same but opposite? Well, same but opposite would be like 3 and negative 3, negative 8 and 8. Positive and negative. Look at my y's. They're already positive y and negative y, and everything's all stacked up. This problem is all primed and ready for elimination. This is what I do. If you can get your equation to the point, or equations to the point that they're completely organized just like this, and one of your variables is a positive blah 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 and a negative same blah blah blah, then you add those lines. So if I add these two lines up, I have negative 4x and negative 5x, which makes negative 9x. I have positive y and negative y, which become nothing. Because positive y minus y is no more y's. So I have nothing. 6 plus 21 is 27. Now x is all by itself and y is gone. How can I solve for x? Divide both sides by negative 9. And those of you with a profoundly good memories might remember that the answer had x equals negative 3. So I made this all, no, I don't want to reset the page. I made this all super sloppy, so let me erase things. Now, similarly with substitution, once I have my x, I can find my y. And I'm going to try to find my y the easiest way possible. In this case, y is almost by itself for the top equation. So if I want to find y, I'm just going to rewrite the top equation, but instead of x, write out negative 3 because x is negative 3. So negative 4x, x is negative 3, plus y equals 6. Negative 4 times negative 3 is positive 12. 12 plus y equals positive 6. Is y all by itself? No. What's in the way? 12. How do I get rid of 12? Subtract 12 from both sides. 6 take away 12 is negative 6. So my answer is x equals negative 3, y equals negative 6. Just like we got last time. This one was a lot faster, wasn't it? See, when we did substitution and it said y equals blah, 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 y equals blah, 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 substitution was easy because all we had to do was plug it into the other equation. This one, elimination, is easy because everything is already lined up and I have a y and a negative y, and they eliminate right away because they cancel each other out. Let's take a look at the next one. So I'm looking at this and I like elimination again. I have negative 4x minus 2y equals negative 12 on top. I have positive 4x plus 8y equals negative 24 on the bottom. I'm looking at my x values, a negative 4x and a positive 4x. Perfect. They're the same but opposite. My y's aren't, but who cares? In this case, I can right now immediately add up those two lines and my x's will disappear. Whew. I would love to see my x's disappear from my life. Am I right, guys? Girls? All right, anyway, when I add these two lines up, negative 4x and positive 4x cancel each other out because they're the same but opposite. When I add negative 2y to 8y, I get positive 6y because 8y take away 2y is 6y. When I add negative 12 and negative 24, that gives me negative 36. Is y all by itself? No. What's in the way? 6. How do I get rid of it? Divide it. And y equals negative 6. I have my y value. Now I have to find my x value. So let me erase this because I made it all sloppy. I'm going to take the y equals negative 6 and plug it into one of those equations. And since the bottom one has less negatives, I think I'd rather plug it into the bottom equation. Whenever you're looking at this and saying, well, what equation should I plug it into? Does it always have to be the top one? Does it always have to be the bottom one? No. Whatever's easiest for you. And what's easiest for me is the bottom because I don't want to deal with negatives. Too much negativity in this world. Am I right? So I'm rewriting the bottom equation, positive 4x, plus 8y, but I now know that y is actually negative 6. So I'm going to replace y with negative 6 because I solved the fact that y was negative 6. And I'm going to finish rewriting the bottom equation. This is the part that might take a little bit, but not really. 8 times negative 6 is negative 48. That's going to equal negative 24. Is x all by itself? No. What's in the way? 4 and negative 48. Let's get rid of the negative 48 floating around first because it's just floating around. Do the opposite, which means add 48. I have 4x equals 24. Is x all by itself? No. What's in the way? 4. How do we get rid of 4? Divide 4. So I'm going to divide 4. Divide 4, x equals positive 6. So if x is positive 6 and y is negative 6, my final answer is going to be positive 6, negative 6. Okay, not so bad. Not so bad. Not so bad. Well, the x's are already stacked up. The y's are stacked up. The numbers and equal signs are stacked up. I have a 2y and a 2y. However, both of them are positive. What I need to do is I want one of them to be negative. How can I make one of them negative? That's right. I can multiply one of them by negative 1. Let's multiply the top one by negative 1 because why the heck not? I'm multiplying literally everything in the top equation by negative 1. So positive 7x becomes negative 7x, and positive 2y becomes negative 2y, and equals is equals, and positive 24 becomes negative 24. And I'm going to rewrite out the bottom equation, which is going to be 8x plus 2y equals 30. Everything's already stacked up. I now have a negative 2y and a positive 2y, which means when I add these two lines together, the y's are going to cancel out. And this is great. Negative 7x plus 8x is 1x, or just x. It's almost as if I did that on purpose. Nah. So right away I have x equals 6. Isn't that nice? Sure is. Let's go to the original equations. Let me erase this mess. I have to find y. So I pick one of those equations. None of them are any easier. So I'll pick the top one, and I'll rewrite the equation. But instead of x, I'm going to write out 6. So I'm going to have 7 times 6 plus 2y equals 24. And now I have to solve for y. 7 times 6, 42, plus 2y equals 24. 42 is in the way. 2 is in the way. Let's get rid of 42 first. Drop down the 2y. 24 minus 42 is negative 18. Struggled with that one for a second there. Is y in the way, or is y all by itself? No. What's in the way? 2. Divide everything by 2. Y equals negative 9. So x was 6, y was negative 9. X was 6, y was negative 9. My final answer is 6, negative 9. Nice. Questions? Oh, you want to do another one? Good idea. Last one. Ugh. Blah. So this is all a mess. I have negative 4x. Everything's like stacked up nicely, but the x's, one's negative 4 and one's regular x. The y's, one of them is 9, the other one's negative 3. Can't do much there. So which one do you want to get rid of, the x or the y? Click like. I can't do it. Let's flip a coin. If this lands on, all right, I'm going to spin this, and you can't see, but I'm going to spin it. If the pointy points me in any way, we'll get rid of x, and if it points away, then we'll get rid of y. It's pointing at me, I swear. All right, so we're going to get rid of x. How can I get rid of x if I have a negative 4 up there and a positive regular x down there? Well, if only I can make the bottom x regular 4x. That way the negative 4x up here and the 4x down there can cancel each other out. Well, we can do that. Why don't we just multiply the entire bottom by 4? It's kind of like in the last problem when we multiplied everything by negative 1. This is the same thing, but I'm just multiplying the entire bottom by 4. Rewriting the top. All I'm doing right now is rewriting the top. Negative 4x plus 9y equals 9. The bottom is going to be positive 4x. 4 times negative 3 is negative 12y. And 4 times negative 6 is negative 24. I multiplied the bottom equation by 4. And now what I have is I have a negative 4x and a 4x. So when I add these two lines together, the x's disappear. 9y minus 12y is negative 3y. 9 minus 24 is negative 15. Divide everything by negative 3. And y equals 5. So I need to find x. So let's erase this. And it looks like the bottom equation would be the easiest to find x because x is almost all by itself already. I have x minus blah, 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 but I don't have anything in front of x. So let's use the bottom equation, rewrite the bottom equation, but instead of y, I'm going to write out 5 and then solve. Negative 3 times 5 is negative 15. Is x all by itself? No. What's in the way? Negative 15. How do I get rid of it? Add 15. Add 15, and x equals 9. So if y is 5 and x is 9, x is 9 and y is 5, x is 9 and y is 5. I'll tell you what, working from 9 to 5, there's no way to make a living, Dolly Parton once said. Dolly Parton, look her up. She also has a theme park in Tennessee called Dollywood. I was there once when I was a little kid. Very underwhelming because I was a little kid. Well, that's it. Systems of equations, fun, fun, fun. I have tons of elimination videos and tons of substitution videos on the tube, so make sure you go check them out if you need more help. Other than that, I'll catch you on the flippity flip. Bye! A software company is selling a new game in a standard edition and a collector's edition. The box for the standard edition has a volume of 20 cubic inches. Volume of 20 cubic inches. And the box for the collector's edition has a volume of 30 cubic inches. The company receives an order for 75 copies of the game, and the total volume of the order to be shipped is 1,870 cubic inches. All right. Which of the following systems of equations can be used to determine the number of standard edition games S and the collector's edition games C that were ordered? So whenever we're given total stuff, we are always going to create the equation, whatever letter plus whatever letter is going to be that total. So S plus C is 75. Now, looking over here, that's not an option. They have to go and make it more difficult for us. So let's give them what they want. What do they want? They want me to get 75 all by itself? No, not 75. Do they? I mean, it's neither one of these guys. So they want me to get C all by itself. So let's subtract S from both sides. That gives me C equals 75 minus an S. So either one of these is exactly just fine. So we have our first equation. Okay, our first equation is there, and that was the total equation. Let me write the other equation that I'm going to need up here. I also have information about the fact that 20 cubic inches for the standard edition, standard was S, so 20 cubic meters for this cubic inches for the standard edition. On top of that, 30 cubic inches for the collector's edition, and all of those cubic inches is going to add up to that thousands number, which is 1,870. So 20S plus 30C equals 1870, not 30S plus 20C, not U, not B, not C, not D, but A. So I don't like this one because they had to make this different. And I don't know why they would do that except to test you, to test your knowledge. But we figured it out. It took me a few seconds there, but we figured it out and it worked just fine. Charlene owns a bookstore. She purchases used books from customers. She pays $3.50 for each hardback book. She pays 75 cents for paperback books. Charlene pays a customer a total of that much for 149 used books. So whenever you're given what is obviously a system of equations type problem, usually what you're going to deal with is cost, like a cost formula, and a total formula. So they're using hardback is X. So if hardback's X, my cost formula is going to be 350X. If paperback is Y plus 0.75Y is going to equal the total amount that she paid, which is that $199, blah, blah, blah. I ran out of room. The other equation is going to be your total, which is X plus Y equals 149. So eliminate 2 and eliminate 2. So 350X, and that's my guy. That's my 1. That's my answer. The answer is D. So this is pretty typical for a system of equations word problem. And with system of equations word problems, you have a cost equation and you have a total equation. So this is my cost parts and this is my total part. And I like totals. Remember that kid? The zombie kid? Remember it? The answer is D. In 1884, yes, my birth year, U.S. presidential election candidates James Blaine and Grover Cleveland received a total of 401 electoral college votes. So looking at this, it looks like I have a system of equations that I have to figure out. So unless there's anything crazy, the first equation's easy. The number of electoral college votes Blaine received, and so Blaine is B, was 37 less or fewer than the number of electoral college votes Cleveland received with system of equations. All right, so it gives me a total here. So Blaine plus Cleveland received, that's a C, received 401. So that eliminates U and eliminates U. I don't know why they gave me those two options, but they gave me those two options. Blaine was 37 fewer than Cleveland. So I had my total equation. It compared Blaine to Cleveland using those words. Blaine was is the same as Blaine is. 37 taken away from C. Speaking of C, that's going to be my answer.
Well, hey everybody. We are going to do a word problem about a landscaping company. And what we're going to do is we're going to do this word problem using substitution and elimination, one of each method. And of course, we know that we'll end up with the same answer because that's what substitution elimination does. So, a landscaping company placed 2 orders with a nursery. The first order was for 13 bushes and 4 trees. Total that much money. The second order was for 6 bushes and 2 trees, totaled that much money. The bills do not list the per item price. What were the costs of one of each? So, let's label things. We care about bushes, we care about trees. Let's let bushes be X. Let's let trees be Y. So, order number 1. Okay, and this is going to be the same exact system for both problems, but I'm just going to write it. I'm going to do substitution first. Order number 1, 13 bushes, 13x, 4 trees, so plus 4y, 13 bushes and 4 trees totaled $487. Okay, 13 bushes, 13x, 4 trees, 4y, totaled 487. Okay. Second order was for 6 bushes, so 6x, and 2 trees, 2y, and that's going to total $232. Okay. So to do substitution, what I have to do is I have to get one variable all by itself. And that's not at all the case in either of these. Now, looking at this, I have an x up here, I have a y up here, 13 is attached to x, 4 is attached to y. I know if I had to get any of those by itself, I'd have to eventually divide those numbers. And looking at that number right there, I really don't want to divide anything. So what I'm going to do is I'm looking at this x, but more specifically that y down there. That y only has a 2 attached to it. So if I were to get y all by itself for the bottom equation, it's not the end of the world. So I'm going to take the bottom equation. I'm going to rewrite it out right here. And I'm going to get y all by itself. So starting us out is subtracting 6x minus 6x. 2y equals, these two don't combine, negative 6x plus 232. Y is still not all by itself. I have to divide both sides by 2, divide both sides by 2, which means divide everything by 2. Y will equal negative 6 divided by positive 2 is negative 3. X comes along for the ride. 232 divided by 2 is 116. All right, so that was my bottom equation. Now solve for y. My bottom equation. What I have to do is, now that I know what y is, I have to throw that into the top equation. So I'm going to rewrite the top equation, and instead of y, I'm going to replace y with negative 3x plus 116.
So this is the top equation, 13x plus 4y. And instead of y, I now know y is negative 3x plus 116. And then continuing equals 487. Okay? 4 is attached to a parentheses, which means distributive property here. 13x, 4 times negative 3x is negative 12x. 4 times 116. 464, I knew that. 464 equals 487. This is convenient. 13x is right next to negative 12x, which means I have 13 x's, or in this case 13 bushes. Take away 12 of those bushes leaves me with just one of them. X plus 464 equals 487. In order to get x all by itself, I have to subtract 464 minus 464. Cross that out. X equals 23. Now that's my x. I still need to find my y. I could plug that into either of the original equations, or since I have an equation right here that says y, I could just take that x equals 23 and plug it in there. So that's what I'm going to do. Y equals, I'm rewriting this equation right here, y equals negative 3. Instead of x, I'm going to substitute x with 23 plus 116. Negative 3 times 23, I don't know why I did that, negative 69 plus 116. Negative 69 plus 116 is 47. All right. Now, what I needed to do was find the costs of one bush and one tree. So what this means is, since x was 23, y was 47, bushes was x, bushes cost $23. Trees, which was y, cost $47. All right. So that's substitution. Elimination. Same exact system of equations, okay? 13x plus 4y equals 487. 6x plus 2y equals 232. Now, the nice thing about elimination in this case is everything is already lined up. The x's match up, the y's match up, the equal signs, and the regular numbers. However, at this very moment, the x's won't disappear and the y's don't disappear. Now, the closest thing that will disappear is the y's. If I have a 4y up here, all I have to do is multiply this guy down here by negative 2, and that will turn that into negative 4y, and then the y's will go away. So this bottom equation, if I multiply negative 2 to everything, becomes negative 12x minus 4y equals 464. So let me rewrite everything without that sloppiness, okay? The top equation stays the same. Okay, that's me writing out the top equation. My new bottom equation is negative 12x, negative 4y, and negative 464. If I add these equations, it's going to look very familiar to what I did in substitution. 13 plus negative 12x is going to be regular x. These guys disappear, and as I might remember from that guy right there, 487 plus negative 484 is 23. Looks familiar.
Now, if I have x, I need to plug it into one of the original equations to find y, so let's plug it into the bottom. I'm going to rewrite that bottom equation, 6x plus 2y equals 232. I now know that x is 23, so I'm going to rewrite this and replace x with 23 plus 2y equals 232. Multiply these guys together. That is 100, 6 times 23, 100, I don't want to risk it. 138 plus 2y equals 232. Subtract 138 from both sides. 2y equals 94. Divide both sides by 2. Y equals 47. So up here, x was 23. Down here, y is 47. And what we know that means is bushes cost $23, trees cost $47. So, there you have it. In all of its glory, doing a word problem using both methods and finding out that we get the same exact answer no matter how we do it. Okay? Thanks for watching. Bye!
Hi! Today we are going to talk about graphing linear inequalities in two variables. See, back in the day, when it was one variable, you'd have a number line, and then you just put a circle somewhere on that number line, and you either fill that or don't fill it in, and you go that way or that way, depending on which way it tells you to go. Now we have two variables, and it'll look a little something like that guy. So that is a two variable inequality. So I would graph that on a coordinate plane, as you can see right there. Now, there's two things that you have to remember, two caveats. If you remember what graphing an inequality looks like, you are saying by filling that circle in and going that way, all of these guys are my possible answers. Same thing here. We are going to graph on a coordinate plane all the ordered pairs, so x and y values, that are possible answers to that equation. So if I give you a less than or equal to or a greater than or equal to, when I graph this line, I'm just going to graph it like a normal equation and make the line solid. Nothing's changed. Why am I making the line solid? Because if it's or equal to, I'm including the line. So when I don't have the equal sign, when it's just less than or greater than, I'm going to dash the line, because the line doesn't count. Just like if I were to graph it, I would have a circle, but I wouldn't fill it in. Now that's caveat number one. Either you make it solid or dashed, depending on whether it has an equal sign attached or not. Caveat number two is I care about shading above the line or below the line, above the mountain or inside the mountain. And I shade above the line if it's greater than or equal to. I shade below the line if it's less than or equal to. So let's move my face. I don't need to have the word how there. Let's graph that guy. Again, I graph this normally, but I have to remember, do I make it dashed or solid? And do I shade above or below? That's what I'm looking for. So if I were to graph that guy normally, it's in slope-intercept form, but with the less than or equal to, I would start out by drawing the -5 right there, and my slope is +3 over 5. +3 over 5. So up 1, 2, 3, right 1, 2, 3, 4, 5. And those are the only dots that I can make. I'm out of room. Now I need to draw my line. Do I make it solid or dashed? Solid, because it's less than or equal to. So I'm going to draw my line as usual. Bada bing. Now I need to determine whether I shade above or below the line. I wish I had like a highlighter thing, but I'll just use big pen. Oh, I do have a highlighter. Yay! All right, now what I have to do is I have to decide if I shade above or below the line. This is a less than or equal to. Less than or equal to. So I'm going to shade below the line. Here's my line. Shading below it looks like that. I thought I'd choose. Yeah, it's not that. Let me choose green. Yeah, that's better. That's better. Okay. What this means, and I'm going to repeat myself affinity times, affinity times, affinity times. What this means is, here's my original inequality. So many choices to choose from. There's my original inequality, right? If I were to plug in 0, 0, that wouldn't make sense because it would say 0 is less than or equal to 0 minus 5, which is 0, just negative 5. So 0 is less than or equal to negative 5? No, it's not. All of these points here, all of these points, so 5, negative 5, that dot right there, if I were to plug into the original equation, would be a true statement. So again, I'm choosing all of these dots are saying all of these points, whether it's whole numbers, decimals, whatever, these are all coordinates that if I were to plug into that inequality would give me a true statement, including the points on the line because the line is solid. So if I were to plug in 5, negative 2, that point right there, it would be a true statement because it would say negative 2 is less than or equal to blah, 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 negative 2. And negative 2 is less than or equal to negative 2. So it all works out. It all works out. All right, let me do another. I should be okay with my face. All this room, and I don't need any of it. I'm going to graph this normally. And I'm going to make sure my line is solid. Why am I going to make sure my line is solid? Because that's a less than or equal to, which means my line is solid. So there's my y-intercept at negative 4, put a dot. That is a positive slope, so up 4 over 3, up 1, 2, 3, 4 over 1, 2, 3, dot, up 1, 2, 3, 4 over 1, 2, 3, dot. And I'm going to make a solid line because I'm including the line because it's or equal to. Now I have to figure out where to shade. If it's greater than, I shade above. But in this case, it's a less than, so I'm going to shade below the line. So I'm going to shade this area here. You might be able to hear my almost 2-year-old in the background yelling, as she always does. What that shaded area means is all of these coordinates, 5, 0, 3, negative 3, 0, negative 6, all of those coordinates, if I were to plug into this original inequality, would be a true statement, including if I were to plug in 6, 4, because if I plug in 6, 4, I would get 4 is less than or equal to 4, which is true because 4 is less than or equal to 4. Okay? Okay, so that one was very similar to the first one because positive slope, negative y-intercept, less than or equal to. So very similar problem. Hopefully this next one's going to be different, and it will be very different. In fact, it's not even set for y. So there's a reason why I gave myself all that space, so I could solve that inequality for y. So let me do that. Now I have 3x minus 2y is less than 10. If I want to get y all by itself, the first thing I have to do is subtract 3x from both sides. Subtract 3x from both sides. Sorry, a pop-up just popped up, so I'm getting rid of it. That goes there. Negative 2y is less than, I want to make that look as much like slope-intercept form as possible. So negative 3x plus, because it's positive 10, bada bing. Is y all by itself? No. What's in the way? Negative 2. How do I get rid of negative 2? Divide both sides by negative 2. And let us not forget that when you divide an inequality or multiply an inequality by a negative, you have to flip the sign. So y is now greater than negative 3 over negative 2 is going to be positive 3 over positive 2, because a negative over a negative is a positive. X, positive 10 divided by a negative 2 is negative 5. So I'm going to put a dot at negative 5, another negative y-intercept. Oh, look, another positive slope. Didn't do a really good job figuring these problems out. Up 1, 2, 3 over 1, 2. That's what I get from stealing them off the internet. 1, 2, 3 over 1, 2. 1, 2, 3 over 1, 2. All right, on to the graphing part. Now is when things get a little crazy. I have a less than, I have a greater than symbol. Okay, that's dead to me. So we're not going to worry about that symbol because it's now greater than. I have a greater than symbol. I don't have the equals part attached to it, which means I'm going to make my line dashed because the line does not count. What's new here is the fact that it's greater than. So what I'm going to do is I'm going to shade above the line, which is all of this. I meant to choose the bigger highlighter, but you guys get the idea. All 4 of you who watch my videos. Which means if I were to look at the original inequality, so you're no longer dead, unshun. If I were to plug in 0, 0, if I were to plug in 3, 3, if I were to plug in negative 6, 0, if I were to plug in any of these purple coordinates, even the decimals, into the original equation, it would make it true. For example, if I were to plug in 0, 0, it would be 0 minus 0 is less than 10. 0 is less than 10. Boop. Now, if you're wondering, what about the dots on the line? No. Because if I were to plug in, say, 4, 1, and plug in 4 for x and plug in 1 for y, I would get 12 minus 2 is 10. 10 is less than 10? No. 10 is 10. And we're not including the equals. So we're not allowed to include the dots on the line. Tricky, tricky, tricky. Tricky, 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 tricky. The easiest of them all. Back in the day, you learned that if I were to ask you to graph something like, I don't know, y equals 5, it would be a line straight across horizontal 5. You would pick 5 right there, so you would say 5 right there, y is equal to 5, boom, boom, boom. If I were to ask you to graph x is equal to negative 5, you would go where x is negative 5 and draw a vertical line. Is this much different? No. Because I'm going to go to x is less than negative 5. Do I make it solid or dashed? Dashed. I'm going to draw a vertical line that's dashed. And I care about everything smaller than negative 5, so to the left of negative 5. So I'm going to shade everything to the left of it. I don't have a lot of space, but you get the idea. So if I use the point negative 6, 1, and plug in negative 6 for x, and if you're like, what about y? Who cares? It's not there. If I were to plug in negative 6 for x, negative 6 is smaller than negative 5. So it's kind of like if I were to take, if I were to ask you a while ago to graph that on a regular number line, you would put a circle at negative 5 and have it go to the left. Well, it was kind of like if I took that line and stretched it out into a coordinate plane, nothing changes. But now I'm including y's, but I don't have any y's. So it would be wise for you to heed my words. Thank you so much. That's it. Bye.
Well, hey y'all, Peyton Manning here, quarterback for the Denver Broncos, and I'm here to teach y'all how to graph systems of inequalities using your calculator. So let's see what we got going here. We have ourselves our TI 84 plus calculator. Looks like we have ourselves a problem. Solve the system of inequalities by graphing. Y'all, the method that we're going to use our calculators for is found in the application section right there. So hit apps. Sounds like a delicious button to hit. Get it? Apps. Forget it. Go down to Unequals because we're dealing with inequalities. So Unequals seems to make sense. Now once we hit it and get this lovely little home screen that says press any key. So I don't know. How about number 5? And we have y sub 1, y sub 2, y sub 3, so on and so forth. Now I have two inequalities that I have to graph. The first one is y is less than negative 3x minus 1. Less than. Now before you go run and hit some buttons, first off, this isn't a touch screen, y'all. You can't just touch that. And if you hit this button, it's not going to work. You have to hit alpha and then that button right there. It's annoying, y'all, but it is what it is. The nice thing, though, is it's going to tell me it's going to shade underneath, and if you look closely, it's going to make my line a nice dashed line because it's not equal to. So now I have to type in the rest. Negative 3x minus 1. All right. Let's go to my second line. Go down there, highlight the equal sign so that you see these buttons come up again. Now I'm going to do greater than or equals to, so let's hit alpha and hit all the way to the right where it says graph until it's working. So we got a little triangle pointing up and to the right because it's going to shade above. We're going to have a solid line, not dashed. Let's type in the rest. 1/2 x. So I'm a lazy person. Let's do 0.5 x plus 6. Now, y'all, when we want to see everything we want to see, we have to hit graph. I guess that makes sense. So hit graph. We have ourselves two shaded regions. Now, y'all, you're like, oh, well, that's a pretty looking graph, but I want to see exactly what my final answer is, and I want to see where these lines intersect. Well, let's look at 3 different options, y'all. First off, let's see our final feasible region. We're going to hit alpha and then hit the shades button to get up shades. Now, where it says unequal intersection, that's going to tell us our final shading. So it's going to give us shading number 1, but you'll see it disappears. Oh, look at that. That's exciting. How nice. Now, if you're like, y'all, I want to find out what that intersection point is. Well, you're in luck. Let's hit alpha, and let's hit POI for point of intersection. Look at that. Negative 2 and 5 is where it intersects. But finally, you're like, Peyton, issue number 3. I want to know exactly what points these lines fall on. No problem, y'all. If we hit second graph, it gives us both lines with its points. So, for example, since the top equation we plugged in for y sub 1, I can graph points like 0, negative 1, 1, negative 4, 2, negative 7. If I wanted to graph that second line, we put that in as y sub 2 when we graphed it, so I could put points like 0, 6, 1, 6.5, so on and so forth. Woo-wee! That's exciting. All right, y'all. Boy, oh boy, that just tickles my fancy. Well, thanks, y'all, for watching. I really appreciate it. Continue watching the Broncos on Sundays as I continue my dominance throughout the NFL. And I teach you math. That's pretty cool, too. All right, y'all, take it easy. Go Broncos! How do I How do I turn this thing off? What button do I press? Is it that one? No. No, it ain't that one. What about this button? Oh, not that one either. Oh, there it is.
What up, what up? On this video of Back to Basics, we're going to talk about solving systems of linear inequalities in two variables. Quite the mouthful, huh? It is. In a previous video, we talked about graphing linear inequalities on a coordinate plane. You know, that's the one where you graph the line, maybe you dash it, maybe you make it solid, maybe you shade above, maybe you shade below. Well, in this case, we're going to be doing that with two at a time. So there they are. There are two inequalities that I have to graph on the same coordinate plane. So that's two lines, two shadings. What does that mean? Well, when it was one inequality, when we would shade an area, okay, that meant all the coordinates, all the ordered pairs in that area were part of the solution. Now I'm going to have shading and then shading that covers shading. What does that mean? Well, simply put, when the two shadings meet is going to be your final answer. All right, so what we'll do is we'll graph both of those inequalities on the same coordinate plane. We'll shade once, we'll shade twice, and where the two shadings meet is going to be your answer. Some books like to call that double shaded area the feasible region, so I kind of like to mark it with an R. That way, if, you know, I was taking this on like paper and I used pencil and I had, like, you know, gray shading and more gray shading, the teacher would understand, you know, what my answer is if I put a big fat R on it. So, speaking of big fat R, let's move my big fat face. It's not fat. Let's graph the top equation in red. I have y is less than negative or equal to, pardon me, negative x minus 2, which means we put the dot at negative 2 because that's my y-intercept. My slope is negative invisible 1, which means up 1 over 1, up 1 over 1. So up 1, left 1, up 1, left 1, up 1, left 1. More, and then more, and then more. And I can do down 1, right 1, down 1, right 1, down 1, right 1. Now is the weird part. I'm going to graph this and make the line solid. Why? Because that's less than or equal to, which means the line counts as part of my answer. Now I have to shade. Do I shade above the line or below the line? This is a less than or equal to, so I'm going to shade below the line, and I'm going to use this nice magenta color here. Yeah. Okay. Hopefully that translates well on YouTube. I'm going to graph this other guy in blue. I'm going to put a dot at 2 because that's my y-intercept. My slope is negative 5, which means up 5, left 1, up 5, up, don't have room, down 1, 2, 3, 4, 5, right 1, dot, and I can't go down 5, right 1 again, no matter. All I need is 2 points. I'm going to make a solid line because it's or equal to, draw the line right there, draw the line there. And in this case, I care where everything is shaded above the line. Now, this is difficult to draw out when you have a very steep line like this, but what you have to realize is above the line were to be like, if this is a mountain, which side would you be climbing? You wouldn't be climbing this left side because you would be inside the mountain. You would be climbing this side right here because that would be above the line. Barely, but above the line. So let me try this again. Get a wrong thing. Get a highlighter. Let's make it blue. And I'm going to shade everything above the line. Now, what you see, and it's not that much, what you see is in this area right here, the purple and the blue meet. My answer, my solution to a system of linear inequalities is the shaded region where both shadings meet. So what I'm going to do is I'm just going to get one more pen. All right. I'm going to make it dark green, and I'm just going to really emphasize the fact that this is it right here. And I'm going to put an arrow there with a big R saying, that's the region. That's the region that I care about. So all of these points in here, and if the coordinate plane were to continue going on forever, that little triangle would go on forever too. All of these points in here, like 2, -6. If I were to plug 2, -6, or if I were to plug 1, -3 in, or all of these points way down here that you wouldn't be able to see, if I were to plug that into both inequalities, it would work for both inequalities. It would be a true statement. All right. So again, if I were to plug in 2, -6, and here, do all the math, I would get something true. Like -6 is less than or equal to 0, which is a true statement. And if I were to plug 2, -6 into here, I would get, what was it? What did I say? -6 is greater than or equal to -8, which is a true statement. It works for both. Now, if you're thinking, well, what about the part that's only blue or the part that's only purple? Well, the part that's only blue, like these guys, only work for my blue line. The part that's only purple would only work for the red line. So if I were to give you a question and say, if I were to plug in 3, 3, would it work for the red equation? Would it work for the blue equation? Would it work for, inequality? Would it work for the red inequality? Would it work for the blue inequality? Would it work for both inequalities, or would it work for neither inequality? Well, if I were to plug in 3, 3, it would only work for the blue inequality because it's only the blue part that's shaded. Okay, the double shading is my solution because it works for both inequalities at the same time. Let's see what else I got. Okay. I think I can move my face up there. We'll see. That's not the same one, is it? It is. Huh. Really wasn't thinking there. Okay. Looks like we're only doing 2 examples today. That's the same one? It's not the same one. The only difference, though, is it looks very similar. Oh, well. I noticed that this is not or equal to, so that might be the only difference, but whatever, we'll find out. I'm going to graph this top one in red. I'm going to put a dot at -2. My slope is negative invisible 1, so up 1, left 1, 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 down 1, right 1, down 1, right 1, down 1, right 1. That is just greater than, no, or equal to. So I'm going to make it a dashed line. So that's where it's different so far. Dashed line. It's greater than, so I'm going to shade above the line. And that's the red inequality. I got to do better at that. That's the red inequality. I'm going to graph this guy in green. I'm going to start at +2. My slope is -5, which means up 5, left 1, invisible 1, but I can't go up 5, left 1, just like the last problem. But I can go down 5, right 1, which is you. Can't do it again. That's less than, no, equal to, so a dashed line. Bing! Every time my phone goes off, an angel gets its wings. Actually, I think that was my watch. I'm going to shade below that steep mountain. So remember in the previous problem, we shaded above. Now we're shading inside the mountain. So here's my green. ish. So that area that is both purple and green, that area right in here is my feasible region. That is the area where if I were to plug any of these points, as long as they're not on the line because the lines don't count, if I were to plug in any of these coordinates into both equations, they'll work for both. Okay? Okay, now let's do that last one. So I see you are not solved for y. So let's solve you for y. So 4x plus y is less than 2. Is y all by itself? No. Subtract 4x from both sides. Subtract 4x from both sides. No flipping of the signs. I'm going to write it out so that it's in slope-intercept form. So the negative 4x comes first, and since that's positive 2, I'm going to add 2. So I'm going to graph that in black. Y is less than negative 4x plus 2, so there's my plus 2. I can go up 4 over 1. No, I can't. I can go down 1, 2, 3, 4, right 1. I can go down. No, I can't. So now I need to draw my line. Should I make it solid or should I make it dashed? Dashed. Door dashed. That is a less than sign. Should I shade below the mountain or above the mountain? How about below? Because it's less than, which means it's below the line. I'm gonna use this orange yet. Let's use this nifty orange. Yeah. Okay. Y is greater than negative 2. So in the previous video, we had like an X and no Y attached. And you might be thinking, how do I graph it if it doesn't have the X? Or well, how would I graph it if there wasn't a Y? It's either going to be a vertical or a horizontal line depending on the letter that you're given. The letter that we're given here is Y. So y equals, or in our case, y greater than means we're going to go to negative 2, there it is. And since this is greater than and not equal to, we're going to draw a horizontal dashed line. Because technically, I could write this out as y is greater than 0x, which means my slope is 0, which is a flat slope. And it's greater than negative 2, which means I shade above the line. So let me get my highlighter out, let me get blue, and let me draw or shade above the line. So we have this area right here where the orangish and the bluish meet. That's my feasible region. Which means if I were to plug in 0, 0, if I were to plug in negative 5, 2 into both equations, it will work for both equations. If I were to plug in 3, 3, it would work for the green equation, but not for the black equation. And if I were to plug in negative 6 or negative 5, negative 5, it would work for the black equation, but not the green. And if I were to plug in anything from this blank area, it would work for neither. And that is how you solve systems of linear inequalities in two variables. Bada bing! All right, thank you. Thank you for your attention and love. Bye! Today, we are going to discuss the fun-filled world of absolute value functions and what their graphs look like on coordinate planes in 2 dimensions. Just like you've always wanted. Now we know what absolute value is, makes things positive. Even if it is positive, it makes it positive still, keeps it that way. Well, what do the graphs look like? I imagine we're not going to hit a lot of negatives, and that probably might make the absolute value function look strange. Maybe it will. I don't know. I guess there's only one way to find out. This is the most basic form of an absolute value function that you will ever see. I'll give it a name in like the next slide or two, because that type of absolute value equation has a specific name. What I'm going to do is I'm going to graph this by picking a couple x values. I'll pick 7 of them, and I'll do -3, -2, -1, 0, 1, 2, 3. And what I'm going to do is I'm going to pick those x values right there. I'm going to plug them into that x, take the absolute value, that gives me a y. So when I plug in -3, the absolute value of -3 is +3, easy peasy. When I plug in -2, the absolute value of -2 is +2. When I plug in -1, the absolute value of -1 is +1, 0. When I plug in 1, the absolute value of 1 stays 1. Don't be tricked. So, it's not linear. Because there's no more pattern. But anyway, I plug in 2, I get 2. I plug in 3, I get 3. Now, I have to graph this. Okay. So I've got -3, +3 looks like that. -2, +2 looks like that. -1, +1 looks like that. 0, 0, 1, 1. 1, 2. I'm sorry, 2, 2, like out of ballet. And 3, 3. And I think we know what's going to happen either way. That guy's going to go like that. That guy's going to go like that. And we have a V. A V for vendetta. Now, this doesn't go anywhere in the negatives because it is simply a function that makes things positive. So basically what this is saying is whatever x you plug in, I'm just going to spit out a positive version anyway. So that's why it goes boink boink, like so. So absolute value functions give me a V because at some point there's a change, there's a shift, there's a break in the linearity, if that's even a word. Well, speaking of words, let's name some of these things. A vertex is where that break happens. Okay, in this most basic form of an absolute value function, the vertex was 0, 0. The axis of symmetry, axis means line, symmetry means it cuts it in half. So the axis of symmetry is this perfectly vertical line that I'm having a really hard time drawing out, that cuts right through the vertex. Now, a vertical line is in the form x equals a number. So it's going to be x equals whatever x value the vertex is. So in this case, the vertex is 0, 0. So the axis of symmetry is x equals that x value 0, because it would make sense that x is going to be the x. And aren't x's always going to be x's, fellas? Oh man. Now, that simple absolute value function is called the parent function because it's the most basic of functions. And we all know our parents are very basic, right, gang? Oh, I'm just full of it today. But that's not. That is not a parent function. A parent function was that V that went, that perfect negative slope went bang at 0, 0 into the perfect 1 slope. Now, we know from, what lesson was that? Linear translations. And I believe that was in the last chapter, that when I throw a number in front of my x and multiply it to my x, that things get skinnier and narrow. That's not going to change here. We also know that if I add or subtract a number from the x within a group, that's going to make it go left to right. When it's negative, it goes right because it's opposite land, and when it's positive, it goes left. We also know that when I add or subtract on the outside here, I go up or down. Okay? When it's positive, it goes up. When it's negative, it goes down. That's not going to change here. So what I'm going to do is I'm going to make another XY chart, T-table it's also called. I'm going to plug in the same points. I'm going to do a lot of fast math to plug it in. So I'm kind of being not being lazy, but I'm not showing any of my work. That looks terrible. There we go. So in other words, if I plug in -3 minus 1 is -4. The absolute value of -4 is 4. 4 times 2 is 8. 8 times 3 is -3 is 5. We get 5. All right. If I plug in -2 minus 1 is -3. The absolute value of -3 is +3 times 2 is 6 minus 3 is 3. Plug in -1, I get -2, which turns into 2 times 4 is 2 is 4 minus 3 is 1. Just doing some fast math. 0 minus 1 is -1. Absolute value of that is 1. 1 times 2 is 2. 2 minus 3 is -1. We're seeing a pattern, but I have a feeling that pattern is going to change soon, not be linear anymore. 1 minus 1 is 0. 2 times 0 is 0. Minus 3 is -3. Now is where things are going to change. Things usually change when you hit the number after the opposite of the number here, but that's neither here nor there. 2 minus 1 is 1. Absolute value of that is 1. 2 times 1 is 2. 2 minus 3 is -1. So we're going back. Okay, we broke that linear trend. 3 minus 1 is 2. 2 times 2 is 4. Minus 3 is 1. So we see going down, going up. All right. And let's see where that changes. I have -3, 5, which is right there. I have -2, 3, which is right there. I have -1, 1, which is right there. I have 0, -1. I have 1, -3. I have 2, -1. I have 3, 1, and nothing else. I think I know what's happening. I think I know that these dots are just going to keep going that way, and these dots are just going to keep going that way. Now, what I want to find out is how is that different than the parent function, which looked like that? Well, it's skinnier. In fact, the slope on the green is 1 and -1. The slope on the red is 2 and -2. Oh, because the number out here makes it 2 times skinnier. That 2 from the linear translations video. That -1 on the inside moved the vertex right 1. Okay, that green line should be up a little bit higher. That's sloppy by me. No. Yeah. Now it moved right 1 because on the inside it's -1, and it moved down 3 because on the outside it's -3. So it looks like exactly like what we had in the linear translations. And if you remember in the linear translations problem or video, we got that directly from point slope form. This is just a different type of point slope form, where point slope form was y minus y sub 1, but if we add y sub 1 to both sides, that happens equals m times x minus x sub 1. This is the same thing. It's the same thing. It's all connected. Math is connected. If you take a number and you multiply it to the group that contains x, that is your slope-ish stuff. So when it's positive, when the slope-ish stuff is positive, it opens upward, and the number in front of it tells you how steep it is. So if the number in front of it is 4, that means you go up 4 over 1 and up 4 over 1. Or if it's -4, you go down 4 over 1, down 4 over 1. That's what the m does. The h tells you if you go left or right. So if you have x minus 3, you go right 3 because it's opposite land. Or if it's x plus 3, you go left 3 because it's opposite land. If the k on the outside, if this guy is plus 5, you go up 5. Or if it's minus 5, you go down 5. Or if you just want to view it this way, just make it hk, and that is your vertex from where things split up and open up. So let's do it now that it's not so bad. All right. That is my slope that opens downward. All right. Where my slope is -1/2 and +1/2, opening downward. This is 4, which means I care about the opposite, so that's going to be left 4 because it's on the inside of the group. That's minus 2. So my vertex is -4 and -2, which lives right there. It opens downward at the slopes of 1/2 and -1/2, so down 1, left 2, out of room, down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2. And boy, oh boy, isn't that a whole lot easier than making a ridiculous chart? Isn't it? And the vertex is -4, -2, which would make the axis of symmetry x equals -4. Bada bing! Bada bing! What's the equation for this one? Well, let's write out the equation. It was y equals m times the absolute value of x minus h plus k. My vertex appears to be 2, 3. So my h is 2. My k is 3. My slope opens downward, so negative. And it appears that the slope is down 1, 2, 3, 4, 5, 6 over 1. So the slope is -6. So putting it all together, y equals m, which is -6. The absolute value of x minus h, which is 2. Close the absolute value plus 3. Absolutely awesome alliteration. Thank you, everybody, for watching. Bye! What up, what up? Today we're talking about piecewise functions. Now, I'm going to keep it 100 with you. I love piecewise functions. You're not gonna love them. Piecewise functions are kind of what they sound like. You take a nice big old graph, like the one you see right there, and you break them into a bunch of pieces. So they're not usually continuous, but they're functions. As you can see here, I mean, this is a function because if you were to use the vertical line test, let's bring back the vertical line test. Hold on, let me draw a vertical line right there. That's terrible, but fine. If I were to draw that vertical line and go boop, 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 now you're going to want to look at that guy right there and say, it looks like it hits the graph 3 times, but it doesn't, because that circle is not filled in, and that circle is not filled in, so it doesn't count. Boop, boop, boop. It is a function. Now, how do you take that mess and make it look like a piecewise function? What does it look like? Well, like I said, not pretty. But this is what it looks like. You're going to say f of x equals, in this case, 3 different things. Okay? One of the things, and you've never learned this yet, you've never learned parabolas in Algebra 1 yet, but you know, I'm throwing this in there. F of x is going to equal x squared, but this only happens for everything 2, not 2, smaller than 2. So it's going to be x squared for all values less than 2. What this is saying is I'm going to graph x squared for all the x values smaller than 2. At 2, y is 6. So when x equals 2, y is 6. That's what that dot stands for. And for everything between, what is this? 2, 3, 4, 5, 6. Between 2 and 6, we have the equation 10 minus x, and again that happens for everything in between 2 and 6. So that looks quite messy, and it is. So we've got a lot on our plate. So piece of garbage is probably what you're thinking. Wise, I don't think so. Function, yeah. Fun, yeah. I'm going to graph y equals -2, x plus 1 in absolute value plus 4, and write out the piecewise defined function. By the way, this guy right here is called the piecewise defined function. So if you recall, we got a lot going on here. My vertex is found by comparing this guy to this. So let me rewrite it. mx minus h plus k. The h and the k are my vertex, so my vertex is going to be the opposite of 1, which is -1. My k is 4. So if I were to graph this, I would put a dot at -1, +4. My slope is -2, which means it opens downward with slopes of 2 and -2, so it opens downward. Here's my slope of -2, just drawing a bunch of points right there. All right, more dots, more dots, more dots. I'd have to make that look like that. Easy. Y, and I'm using y, not f of x, because I'm given y. Y equals a big brace looking thing here. I have two parts of this equation, and all the action happens at -1. So my first part is I have this line with a slope of +2 that's eventually going to go through 6. I have that line right there with the slope of +2 and eventually going through 6, and all of that happens from the -1 x value and to the left of it. So what I'm going to do is I'm going to say that I didn't need that y equals there. Let me get rid of that y equals, because I already wrote out y equals. It just looks sloppy. Bad job by me. Bad job by me. This is even a worse job by me. All right. 2x plus 6 happens for all the values less than -1. And in this case, I'm going to throw in the or equal to part. So less than or equal to -1. That looks so terrible. So I'm going to make sure that this guy is x is greater than -1, because I can't have it be both. I mean, technically I can in this case. All right. So what is that line? Well, it goes through -2, has a slope of -2, and that's it. So again, what I'm doing is I have two lines glued together, and they are glued together at -1. So stuff is happening to the left of -1, stuff is happening to the right of -1. And the stuff that's happening to the left of -1 is a line defined by a slope of 2 and eventually has a y-intercept of 6. And so that line would be 2x plus 6. And that's happening to the left of -1. And I decided in this case to include -1. Over here I have stuff happening to the right of -1, and that stuff has a slope of -2 and has a y-intercept also of -2, which is the equation -2x minus 2, and it happens to the right of -1. Okay? Not easy. And this is coming from a guy who taught calculus to a bunch of college students, and when I went over piecewise functions every single year, I got a lot of, huh? So if you're looking at this and you're going, huh? And you're in Algebra 1 and not in college, I understand. So, hopefully this clicks a little bit. If not, just play the video on loop and see what happens. Please? Alright, so I'm going to graph this piecewise function. F of x equals negative 2x minus 1 for all the values smaller than 2. X is smaller than 2. Alright, so I'm going to graph this part right here in green. And this is what I'm going to do. I'm going to draw the entire line and get rid of what I don't need. Negative 2x minus 1 means I start at negative 1. Slope of negative 2 has me going up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Draw your line. However, I only care about the x values 2, including 2 and smaller. So there's my 2 right there. I'm going to erase everything to the right of it, and I'm going to bring back that dot right there. Why am I putting a dot there? Because I'm including 2. Okay? The other equation I'm going to draw in its entirety. Okay, start at 4. Negative x is my slope, positive 4, so bump, 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 draw my entire line. What do I care about? I only care about the stuff to the right of 2 and not including 2. So I'm going to get rid of the stuff I don't need, including the 2, so I can put a nice non-filled circle right there. What this guy is saying is I'm going to graph this equation but only care about the stuff less than or equal to 2. So this green equation looks like that, and I don't care about any of the stuff to the right of 2. What this guy is saying is you're going to graph negative x plus 4 but only care about the stuff greater than 2. So even though I drew that whole red line, I erased all of that stuff. This is a function because it passes the vertical line test. And this is a piecewise function. Okay. Let's do it again. Again, not fun. I think it's fun. All right, I'm going to graph. This is actually a lot friendlier. I'm going to graph negative x and only care about the stuff that's happening. Well, let's just graph negative x. Negative x is the opposite of the parent function, which looks like this. Oh, no, I missed it. I thought I can get away without doing dots, but I have to do dots. I have to do dots. I have to do dots. I have to do it. I just have to. And a lot of you are like, no, stop doing that because we only care about blah, blah, blah. Well, I'm ignoring you. You hear? I don't care if it looks sloppy at the end there because I don't need half of that. I only care, though, about the stuff to the left of negative 2 and including it. So there's negative 2 right there. I only care about the stuff to the left of it, which means you're gone. There you go. 2, which actually is right there, but I'm not going to include 2. And it's a horizontal line. Now, again, the green line only matters for the stuff greater than negative 2. So I didn't bother writing that way and then erasing it. I saved myself a little bit of time. But isn't that a neat-looking piecewise function? That is considered continuous because they're connected. The previous one, that guy, That guy, that one, is discontinuous because they're not connected. However, it's a function, and so is that. Otherwise, it wouldn't be a piecewise function. There would be no fun in piecewise non-functions. Gross! It's the last one we're going to do, though. 3 chunks to this. Now, this is approaching like Algebra 2 pre-calc territory. But, you know, I like having a good time. Alright. Negative 2x minus 3. Let's graph the whole thing. Minus 3 will make you green. Negative 2 is my slope. So boom, 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 boom. Before I go too far, I only care about the stuff to the left of negative 2. So tell you what. If I only care about the stuff to the left of negative 2, but also including negative 2, then there's my big dot at negative 2, and I'm going to go right there. Okay? Okay. You do that in red. That is negative x plus 4, but I only care about the stuff in between negative 2 and positive 3. So plus 4, negative x, so that's up 1, left 1, up 1, left 1. Now normally I'd put a dot there, but I'm going to not fill it in because we're not including negative 2. Okay, so I'm done going that way. I'm going to go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, and I include 3 because they told me to include 3. Get rid of these 2 dots that are just floating around. Alright. Just like in the previous problem, when we have just a regular old number, it's a horizontal line going through that number, and I only care about that stuff happening after 3, so it's going to be at negative 5, but after 3, and it is horizontal. If I were to take a perfectly vertical line, like that one, and do a vertical line test, it passes. With flying colors. 3 colors. Oh, unless you're colorblind, then it's just like 1. I'd like to formally apologize to all of my colorblind viewers, which I doubt there are any because no one watches these. Thanks for watching. None of you. Bye! Step by step, ooh baby, gonna get to you, girl. Today we're talking about step functions. A step function is a function of yours when your mom remarries some guy. Just kidding. This is actually what a step function is. See how they look like steps? Well, that's what a step function is, and it's kind of very unique. I mean, let's take a look at, let's make believe at what happens if I say that x is 1.5. Well, when x is 1.5, y is negative 2. How about when x is 1.9? When x is 1.9, y is negative 2. What about when x is 1.1? Well, when x is 1.1, y is negative 2. So basically, it seems that whatever decimal value 1 is, it just rounds up to 2. And that is what a step function does. Unless the number is itself, in which case it becomes itself. So a step function takes a number and either rounds it up, or in a case that's not seen here, rounds it down. And in no matter what case, it's going to keep that integer itself. So that's what step functions do. Now, as far as that whole rounding up, rounding down talk, let's actually talk about that. Now we have two types of functions. We have a ceiling function or a floor function. A ceiling function look like this. See how these kind of look like absolute values but have these little marks that kind of curve in where a ceiling would be? That is a ceiling function. What a ceiling function does is it either keeps the integer exactly the same or it rounds up the decimal no matter what. So in this case, 3.14, if I plug in 3.14 into this guy right here, I get the ceiling of 3.14, which rounds up to 4. I know we want to round down, but that doesn't matter here. The whole 5 or above stuff no longer exists. Not with these guys. So it could be 3.1, it could be 3.9. Either way, if it's the ceiling function, it rounds up to 4. The floor function rounds down no matter what. Okay, so in this case, the floor of 2.7 is going to round down to 2. So in a case like this guy back here, this was the ceiling function because it took any number and rounded it. Actually, no, it's the negative of a function. Let's not even get into that. Let's just pretend that never happened. There we go. So let's actually do a few problems. Here's A. A is saying, let's take 1.2, plug that into X. All right, 1.2, add 0.5, and then take the floor of it. So I get 1.7, and the floor of 1.7 is 1 because we round down. Let's do B. B says, let's take 1.7, plug it into my X there, add 0.5, which gives me 2.2, and round that down no matter what. All right, my computer decided to die out on me, so I had to restart, and here I am again, picking up where I left off. There are two ways that you can graph step functions, or at least two ways that they could possibly look like, and here's one of them. Basically, it looks like a piecewise function, but when graphed, it's going to look like steps. Not exactly the same perfect one block each time, but still steps. So I have just the first quadrant because I'm only going to be graphing in the first quadrant. So what this is telling me to do is to go between 0 and 2, but not include 0, but include 2 and graph at 4, which is just a horizontal line. So 4 between 0 and 2, but include 2. Bada bing. Baymax! Looks like Baymax eyes. This is going to be a wider Baymax eyes, but he's going to be taller. I'm going to go between 2 and 5, but not include 2. I'm going to go to 8. Go to 5, and include 5. And then the next one, and the last one, is going to be at 12, between 5, but not including it, and 8, but including it. So here's my 5. Allow me to go up to 12 way up here. I'm going to fill that in. Well, I'm going to draw a circle, but not fill it in. I'm going to go out to 8. Could have done a better job at that, but there you have it. Steps. Step by step. Here's the other way that I can graph this. Let me shrink my head. Yeah, that works. Yep, that works. Pretty much what this is saying is horizontal line at 4, in between 0 and 1, don't include 0. Horizontal line at 5, between 1 and 2. Horizontal line at 6, between 2 and 3. So this is going up one block steps, but kind of starting at 4. So it's like I'm starting at the 4th floor, and I'm not including... so this is like rounding up. This is like a ceiling function. No, it's actually like a floor function. Yes. So let me just draw it all in purple. I haven't used purple today. I'm going to go to 4 up here, between 0 and 1, but don't include 0. Then up to 5 between 1 and 2, but don't include 1. Between 2 and 3, between 3 and 4, between 4 and 5, between 5 and 6 at 9. Okay, and those are step functions. So piecewise functions with a twist. That was fun. A lot of fun. Bye. What's up, my dudes? Another Back to Basics video, and we're going to introduce a brand new topic. Exponents. Here it is, here it is, here it is. Exponents are fun. Exponents are easy. It's basically a way for you to take a bunch of things that are written out and just cram them into one. So in other words, I have 3 to the 4th power going on here. 3 times, I accidentally gave it away. I have 3 times 3 times 3 times 3. The way I write that out as a power is I use the base that's being multiplied over and over and over and over and over again, and I put a little 4. And that 4 implies how many times it's being used. 3 times 3 times 3 times 3 is 3 to the 4th. Parentheses times parentheses times parentheses, where so that's 3 of them. Each parentheses is exactly the same, and inside each parentheses I have -1/2. Don't forget those parentheses. If you forget those parentheses, it's not right. So parentheses, 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 where everything's the same. I have 6.4 times 6.4 times 6.4 times 6.4, 4 of them, times B times B times B. That was supposed to be a different color. B to the 3rd. Easy. Easy. More. I have parentheses -t times parentheses -t times parentheses -t times parentheses -t times parentheses -t. So I have parentheses -t 5 times. I have negative. Okay, so the whole thing's negative. And inside the parentheses, I have 1/4, 1/4, 1/4, 1/4. So I have 4 of those. Now, see how the negative's outside the parentheses? If I were to put the negative inside the parentheses, it would be wrong. Since the negative was outside the parentheses, I have to keep it outside the parentheses. Technically, I don't even need those parentheses. Evaluate. Ooh, now I get to finally do some math. 5 squared means the squared is attached to the 5. So I write out 5 times 5 times 5 is 25. I can handle that one. I have a 6 attached to a parentheses. So I write out 1, 2, 3, 4, 5, 6 parentheses. And each parentheses, I have 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. When you multiply fractions, you multiply straight across the numerator. In other words, you multiply the numbers on the top part of the fraction bar. So I'm literally going to do 1 times 1 times 1 times 1 times 1 and get 1. Now I multiply all the numbers in the denominator, which is I'm going to multiply all the numbers on the bottom. So I get 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32, times 2, which is 64. Not so bad. What's my cubed attached to? 11. So I'm going to write out 11 times 11 times 11. Oh, but Mr. Parrott, you forgot the negative. I know. There it goes. Boop. Now, why don't I repeat the negative 3 times? Because the cubed isn't attached to the negative. The cubed is only attached to the 11. The cubed is not attached to the negative. It's only attached to the 11. So what I do is I do 11 times 11 times 11, which I don't know. What's 11 times 11?
Okay.
I'm sorry. What's 11 times 11 times 11?
It's 1,331.
And then don't forget that negative that's living out front. Okay, so again, when I think that's going to come clear. Yeah, that's going to come clear again. What is my squared attached to here? My squared is attached to a parentheses. Living inside the parentheses, I have a 1/12 negative and a negative 1/12 again. There's 3 parts here that I want to make sure of. I have a negative times a negative, which is a positive. That's 1. I multiply across the numerator. 1 times 1 is 1. And I multiply across the denominator. 12 times 12 is 144. And those are my 3 parts. My 3 parts were negative times a negative, and then 1 times 1, and then 12 times 12. Different here. What's my cubed attached to? The parentheses. So I'm going to write out the parentheses 1, 2, 3 times. Inside the parentheses, I have 1/9, 1/9, and 1/9. Where's my negative? Way out front. Why didn't I write out my negative 3 times? Because the 3 is attached to the parentheses, not the negative. The cubed is attached to the parentheses, not the negative. And if you're wondering, well, why did you write out the negative 2 times in the red problem? Because in the previous problem, the squared was attached to the parentheses, like I just said, and inside the parentheses was a negative. So whatever the parenthesis, or whatever your squared or your cubed or whatever is attached to, if it's a parentheses, you rewrite everything inside that parentheses. So I wrote out negative 1/12. I wrote out 1/9. That negative here lives on the outside, so keep it on the outside. Okay? I have 9 times 9 times 9, which I think I know, but I'm not sure. I think it's 700 something. What's 9 times 9 times 9?
It's 729.
1 times 1 times 1 is 1, and that negative lives on the outside. Okay? What's my 6 attached to? Parentheses. Parentheses 1, 2, 3, 4, 5, 6. And inside the parentheses, I have negative 1 times 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 negative 1. So I have 6 negatives being multiplied together. Okay? There's my 6. Negative times a negative is a positive. Negative times a negative is a positive. Negative times a negative is a positive. So all of this becomes positive. 1 times 1 times 1 times 1 times 1 times 1 is 1. And that's it. That's it. That's it. That's it. That's it. Not so bad, huh? Bye. Well, hello again. We're going to do some more back to basics style problems involving exponents. Look at these wacky problems. I'm going to start this by going a little out of order. I'm actually going to go right to left instead of left to right. I'm not happy with the order in which I did these problems. Let's start as easy as possible. And then maybe we'll run into a shortcut or two. I don't know. 3 squared. What's 3 squared? 3 squared is 3 times 3. And then there's a big times dot in the middle there, so I'm going to leave that there. And then I have 3 squared again. Let me choose a different color. 3 times 3. Okay, so I know from the previous video, 3 times 3 times 3 times 3 is just 3 to the 4th. Okay. So there's got to be a way I can get that 2 and that 2 to a 4th. I don't know. Times, add, I don't know. We'll see. Let me look at those 8s there. Ugh. So many. That one has 10 of them. So 8 times 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 8. 1, 2, 3, 4, 5, 6, 7, 8 eighths. Times, we'll put one over there, times 8. That one has 4 eighths, so times 8 times 8 times 8 times 8. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so 8 to the 14th. Huh. So I wonder if there's a way I can get that 10 to the 4th and 10, or that 8 to the 10th and 8 to the 4th and get that 10 and that 4 to a 14. I don't know. Maybe. I don't know. Third power. What's taken to the third power? 5 to the 4th times 5 to the 4th times 5 to the 4th. Okay. So each parentheses is going to be 5 times 5 times 5 times 5. 5 times 5 times 5 times 5. 5 times 5 times 5 times 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 5 to the 12th. All right, hold up. No way. No way. Let's go right to left again. I went from 3 squared times 3 squared, and that became 3 to the 4th. Why? When I multiply two numbers of the same base, I add the exponents. When I multiply two numbers of the same base, I add to the exponents. 2 plus 2 is 4. That becomes 3 to the 4th. So when I add two or multiply two numbers of the same base, I add the exponents. 10 plus 4 is 14. However, when I take a power and throw parentheses around that and take that to another power, I multiply exponents. All right, so let's see if we can remember those rules without having to write all this mess again. That's too much. Here we are. Okay, so if I have a power taken to another power, I multiply exponents. The last thing I want to do is write out parentheses, B, 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 12 times, B, 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 12 times, B, 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 12 times. Just think of it this way. You have 3 groups of 12 B's. 3 groups of 12 is 36, so I would have 36 B's. If I were to write out 6 H's and write out 1 H next to it, I would have 7 H's. In other words, add the exponents. When a power is being multiplied to a power, add the exponents. When a parentheses is being taken to the 5th power, I write that parentheses out 5 times. I would write that parentheses out 7 more times, so I would write out -4, -4, -4, -4, -4, -4, -4, -4, -4, -4, -4, which is 12 -4s, or 5 plus 7. So I would write out parentheses -4 to the 12th. That's the shortcut. A power to the power means you multiply. When you multiply powers, you add the exponents. Okay, let's do more. When I multiply 2 powers, I add the exponents. So I have 2 2/3 next to 6 2/3, so that's going to give me 8 2/3. Since I have 5 parentheses living in this parentheses, and I have two groups of it, I'm going to multiply exponents. So if you're looking at that and you're like, that's confusing looking, just pretend that little parentheses is an x. So if you had something like x to the 5th squared, you would just be like, multiply the exponents. This is no different. Instead of x, you have parentheses 3/4, and then you multiply the exponents. And then you multiply the exponents. Okay. This is different. Usually I'm just given one thing, but let's see if we can figure this out. Simplify the expression means we actually have to do the math. Great. So, what this is I have 3 bags, and each bag I have $6 and a giraffe. $6 and a giraffe. $6 and a giraffe. So I have 6 times G, 6 times G, 6 times G. Or I could just write it out like this. If I have 6 times G times 6 times G times 6 times G, I could just write out 6. I don't even need the parentheses. I'm getting rid of that parentheses right there. I could just write out 6, 6, and 6. 6 times 6 times 6 times G times G times G. Wait a minute. That's just 6 to the 3rd times G to the 3rd. Wait, so I didn't have to do all that mess. All I had to do was kind of do like a little version of distributive property and attach 3 to both of those things. What's 6 times 6 times 6? Where's my phone? Where's Siri? Where is she? What's 6 times 6 times 6?
One moment. Working on that.
So 198.
Something went wrong. Please try.
What's 6 times 6 times 6? I think it's 198. I think it's 198.
Just a sec.
Oh my goodness gracious me.
Working on that.
It's 216. I was way off. G to the 3rd. Now the reason why I'm writing out 6 times 6 times 6 is 216 is this says simplify the expression. The directions in the last couple problems said write your answer as a power. This didn't, so I actually had to do the math. Okay? This is the same thing as saying parentheses times a parentheses, but what I just learned is if I have a parentheses and it's being taken to a second power, I just apply that power to everything. So I get 1 to the 5th squared and k squared. 1 to the 5th, or 1/5 rather, times 1/5 is 1 times 1 on the top, 5 times 5 on the bottom, and then you have k squared on the bottom. Apply that 3 to everything. So that's the same as negative 3/4 to the 3rd and p to the 3rd. Negative 3/4 is going to mean there's 3 things here. Negative times a negative times a negative, which gives you a negative. 3 times 3 is 9, times 3 is 27, so that's me multiplying the top. 4 times 4 is 16, times 4 is 64, that's me multiplying the bottom. And then p to the 3rd. I have 12 bags, and in each bag I have a rabbit and a turtle. I dump them all out on the floor, and so I have 12 rabbits and 12 turtles. And I like turtles, and I like exponents. And I am done. Bye! What up, what up? Today in Back to Basics, we're going to discuss more properties of powers. And in this case, we're going to deal with the quotient property of powers. We're going to treat the first three problems similarly to the previous video, where what we did is when we saw 4.5 times 10 to the fifth, we just ripped it apart. 4.5 times 4.5 times 4.5 times 4.5 times 4.5 all over 4.5 times 4.5 times. Now this is getting pretty monotonous. This is getting pretty ridiculous. But what I do know is if I'm just multiplying across the top, just multiplying across the bottom, I can cross out things that are alike. So I'm going to cross you out, and I'm going to cross you out, and I'm going to cross you out. And that leaves me with two 4.5s in the numerator, so I would get 4.5 squared over 1, which just becomes 4.5 squared, because anything over 1 is that anything. So wait a minute. When I multiplied them together, when I multiplied similar bases, I added the exponents. When I divide similar bases, I'm going to subtract the exponents. So instead of writing out 10 sixes up top and 6 sixes downstairs, or 4 sixes downstairs, I know that I would have all these sixes up here, and then I'd have 4 down here and just cut out 4 of them. So if I cut out 4 from 10, I'm subtracting 4 from 10, and that leaves me with 6 sixes up here. Oh. So subtract. When you divide powers of the same base, you subtract the exponents. When you divide powers of the same base, you subtract the exponents. That's not so bad. It's pretty easy, actually. Almost easier than the last one. Let's see. Oh, okay. This is a combination of the two. When you multiply powers of the same base, you add the exponents. Okay, so let's do that. So if I have 5 sevens up here and 3 sevens up here, I have 8 sevens up there. Add the exponents. And so I have 2 sevens down there. When you divide powers of the same base, you subtract the exponents. 8 minus 2 is 6, so 7 to the 6th power. 1, 2, 3, 9, 8, 76ers. I'm saying that wrong. So when they were next to each other, multiplying powers of the same base, add exponents. So here I'm going to add these exponents. So that's c to the 17th. C22 is still up top to the 22nd. When you divide powers of the same base, you subtract exponents. 22 minus 17 is c to the 5th. When you multiply powers of the same base, you add exponents. So I have negative 6.1 to the 11th over 7 plus 2 is negative 6.1 to the 9th. And when you divide powers of the same base, you subtract the exponents. So negative 6.1 squared. I don't want to jinx it, but my penmanship skills are just great today. Is that it? That's it. Super easy, super fast. Done at last. Bye. Back to basics again. Let's get rid of you and get started on you. Oh, negative exponents. What's a negative exponent? A negative exponent simply means that whatever side of the fraction bar it's on, you move it to the other side. So let's take a look at this first one. It is on, well, there is no fraction bar, so how can I move it to the other side of the fraction bar? Oh, I know. I'll make a fraction bar and put it over 1. Whenever you have a negative exponent, you move whatever the negative exponent is attached to the other side of the fraction bar and make it positive. So 6 to the negative 2 goes downstairs and becomes 6 to the positive 2. And since I have nothing left upstairs, I'm going to keep a 1 there. That's what I do with negative exponents. What do I do with 0 exponents? Well, anything to the 0th power is 1. So anything to the 0th power is 1. Anything to the 0th power is 1. So 1 times 5 to the 3rd is just 5 to the 3rd. Or you could have added the exponents here, and 0 plus 3 is 5 to the 3rd. Either way, it's all good. It's all good, baby. It's all good, baby. Okay. No big deal. I can do this. Positive exponent and a negative exponent. Anything that has a negative exponent gets moved to the other side of the fraction bar. So if I don't have a fraction bar, I make a fraction bar like so. Take a look at that 9 to the 4th. Does it move or does it stay? It stays because it has a positive exponent. Take a look at that 9 to the negative 4th. Does it move or does it stay? It moves because it has a negative exponent. Any number divided by itself is 1. So 9 to the 4th over 9 to the 4th is 1. Dunzo, dunzo, dunzo. Don't overthink it, don't overthink it, don't overthink it, don't overthink it. Okay, let's do it again. Negative exponent over 1. Do you move or stay? Well, you stay because you have a positive exponent. You move because you have a negative exponent. So this is different. We haven't run into this issue yet, but it's actually a pretty easy issue. Whenever you divide powers of the same base, subtract the exponents. Well, in this case, the more powerful exponent lives in the denominator. So when I subtract, I'm going to have more 2's in the denominator, so I'm going to keep those 2's in the denominator, and I'm going to have 1 up top in the numerator. Okay, whatever number is more powerful, you keep it there. Negative exponents again. So I'm going to put everything all over 1. Do you move or do you stay? You move because you have a negative exponent, so I'll put 3 to the 3rd downstairs. Do you move or do you stay? You move also because you have a negative exponent, so I'll make it a positive exponent and put you downstairs. There's nothing left on top, so I'm going to put a 1 there. When you multiply powers of the same base, you add the exponents, so I would have 3 3's and 2 3's next to each other, so I would end up with 5 3's total. And that's what you get. Oh, same types of problems. If you divide powers of the same base, subtract the exponents. The 4 on the bottom is more powerful than the 4 on the top. There's 3 4's up top. There's 5 4's on the bottom. So you're going to keep your 4's on the bottom, subtract the exponents, and since you completely eliminate the top, you keep a 1 up there in the numerator. Oh, look, a negative exponent downstairs. When you see a negative exponent, you move it to the other side of the fraction bar. So that negative exponent moves to the top, 5 to the 3rd, over 1 times 1 over 5 to the 6th. That 5 to the 6th doesn't move because it has a positive exponent. When you multiply fractions, you multiply straight across the top and straight across the bottom, which means I'm going to have a 5 to the 3rd up top and 5 to the 6th on the bottom. Nothing really changes at all, really. When you are dividing bases, or dividing powers of the same base, subtract the exponent. The 5 on the bottom in the denominator is more powerful, so keep it there, because that one has 6, and that one has 3. Subtract the exponents, leave a 1 up top, and there you have it. Sorry. All right, so I have 3 things going on in this fraction. Do you move or do you stay? You stay because you have a positive exponent. Okay. Do you move or do you stay? You move because you have a negative exponent, so I will make it 1.5 to the positive 2 upstairs. Do you move or do you stay? Let me choose a different color. Do you move or do you stay? You stay because you have a positive exponent. I have two 1.5s next to two 1.5s upstairs, and that's going to leave me with four 1.5s at the exponents. And on the bottom, you still have 1.5 to the fourth. Now, in a previous problem, when we had something to the power and the same exact thing in the denominator, you just get 1, because something divided by itself is 1. 1 to the fifth to the fourth, 1.5 to the fourth divided by 1.5 to the fourth is going to be 1. So this guy just becomes 1. And my face is in the way. My face is in the way. My face is in the way. Why can't you get smaller? There you are. Okay, there's a negative exponent, so I move it to the other side of the fraction bar. Oh, this guy doesn't have a fraction bar, so let's make one. Do you move or do you stay? You move because you have a negative exponent, so let's move you downstairs. Do you move or do you stay? You stay because you have a positive exponent. And I have different bases. So am I going to do any 7 minus 2s? No, because the rule is if you're dividing powers of the same base, subtract the exponents. I'm dividing powers of different bases. One's an A, one's an 8. They're different. Don't do anything. You're done. I have 3 things. I have a 5. I have a b to the negative second, which moves downstairs and becomes b to the positive second. I have b to the negative third, which moves upstairs and becomes b to the positive third. I have a 5 and nothing else. When you divide powers of the same base, subtract the exponents, the b upstairs is more powerful, so I'm going to keep it up there. So that becomes 5b. 3 minus 1 is, or 3 minus 2 is 1 over 1. There's 2 things here that I don't need. First off, I don't need b to the first. So I'm going to keep it as 5b. Because there's just one b. Why not write out 1b? And when I divide by 1, I just get the answer anyway, so I don't need the over 1 part. You never need an over 1, but you do need the 1 if it's in the numerator. All right, so a bunch of things here have the potential of moving. Let's check them all out. 3 to the negative 2, you move to the bottom because you're a negative exponent. K to the 0th, you stay up top but become 1 because anything to the 0th power is 1. W to the 0th, you stay up top but you become 1 because anything to the 0th power is 1. And last but not least, W to the negative 6, you move upstairs and become W to the positive 6. So look at upstairs, look at the numerator. 1 times w to the 6th is w to the 6th. 3 squared is 3 squared. Do the w to the 6th and the 3 squared combine? Nope, because they're different. And that's what I get. So those are 0 and negative exponents combining with the other power product, quotient product rules that we had the other day. Pretty excite. Pretty excite. Bye. Well, we're here again with another Back to Basics episode. This should be fun. Ooh, standard form. Standard form is just the way numbers are supposed to be written out. So what do I do if I give you something in scientific notation and ask you to write it out in standard form? Well, I take that guy right there, the 7, and I write it out. Oh, yep, 7. Normally for 7, the decimal will be right after it. So 7 point. Now, when I'm taking a number and writing it in standard form, whatever that exponent is, I move it either to the left or to the right that many times. It's a positive exponent, so I'm going to move it to the right 7 times. Okay, so 1, 2, 3, 4, 5, 6, 7, and put my new dot there. Any space that I leave, I fill with the 0. 0, 0, 0, 0, 0, 0, 0. I have a cat named Zero. I hope she's not around here. She'll be like, yes, yes, yes. My new decimal's at the end. And if my decimal's at the end, all the way to the right, I don't need it. So I'm going to have 7 with a 0, 0, 0, 0, 0, 0, 0. And if you want to put commas for every 3 zeros moving from the right, it's not a bad idea. So let's do it again. I'm going to put an 8 there. Normally my dot would go after the 8. And I'm going to move negative 3 spaces, which means I'm going to move to the left 3 spaces. So let's do it. 1, 2, 3, put a dot. I have 2 spaces where I can put zeros in, so 0, 0. And what I end up with is 0.008. Now remember what I said, if your dot's all the way to the right, you don't need it. However, if your dot's all the way to the left, you do need it because it's a decimal. Small number. Let's write out a 5. Let's put a dot right after it. My exponent is positive 2. Let's go to the right 1, 2 times. Let's put 2 zeros in there, and I have myself a full 500. All right. Just sitting here marveling at my own work when I could just move on. Let's do it again. The decimal's there for us. Life is easy. 2.7. That negative 4 right there means I move it to the left 1, 2, 3, 4 times. Put a dot. Fill in 1, 2, 3 zeros. So I end up with 0.12327. Now I'm going to put my 3.85 way the heck over here because my exponent is negative 8, which means I'm moving to the left 8 spaces. So let's do that. Go from your decimal and move to the left 1, 2, 3, 4, 5, 6, 7, 8. Even though I've wrote my number over there, it's still not going to be quite enough space. 1, 2, 3, 4, 5, 6, 7, 0. So I have 0.0000385. Now, that's what I call a small number. See, the scientific notations with the negative exponents are going to give you really small numbers. The scientific notations with the positive exponents, like that guy, is going to give you big numbers, a number over 10. So I have 9.725, and I'm going to move to the right 1, 2, 3, 4, 5, 6 spaces because it's a positive exponent, and that makes my number big. Big number with positive exponent. And I end up with 9,725,000. That's it. 3 zeros. Oh, the amount of money I made this year. Just kidding. Half of that. I made about half of that. Okay, that's how I take standard form. I'm sorry, that's how I take scientific notation and put it in standard form. What if I give you standard form and I want to put it in scientific notation? It's the reverse. Reverse, reverse. Reverse, reverse. First things first, I have to determine where my decimal goes. My decimal goes in between the 3 and the 2. Remember, scientific notation, the number you want has to be 1 digit, and you can have whatever many decimals you want after it, but it's got to be a digit point something. 1 point something all the way up to 9.9999999. You can't have 0 point something. You can't have 10 point something. 0 point something is too small. 10 point something is too big. So you need to have it, in this case, as 3 point something. And we have 3.21. So I'm going to write that out. I know it's going to be times 10 to the. Is it going to be positive or negative? Well, Look at my number. Is my number bigger than 10 or is it smaller than 1? Is it a big number or a small number? The number that I started out with is a pretty big number, so it's going to be a positive exponent. So when I move to the right, however many spaces I need to get to the very end, that's going to determine what my exponent is going to be. 1, 2, 3, 4, 5, 6, 7, 8. That's my exponent. Where do I put my decimal? In between the 5 and the 4. If I put it in between the 4 and the 3, 54.3 would be too big. If I put it in front, 0.5 would be too small. So I have 5.43. Notice how I'm not putting 0. Once you hit the zeros, you're done. So I have 5.43 times 10 to the, is it going to be a positive or negative exponent? It's going to be positive because my original number is big. It's bigger than 10. And I have to move 1, 2, 3, 4, 5, 6 to get to the end. Well, to get to the other decimal, I guess I should say. Where should my decimal go here? Between the 2 and the 1. 2.1 times 10 to the. Is my exponent going to be positive or negative? It's going to be negative this time because the original number is a small number less than 1. So how many spaces do I move to get from one dot to the next? 1, 2, 3. There you have it. There you have it. One more, I think. One more slide, right? Where do I put my decimal? In between the 1 and the 0, of course. Now be careful. Remember in a previous problem I said, once you hit the zeros, you're done. Well, I still have a number after my first 0. So I have 1.07 and then nothing but zeros. If you have nothing but zeros after it, then you're done writing out your number. I know it's times 10 to the something. I know my original number is big, so it's going to be 10 to the positive exponent. I know I have to go to the right. 1, 2, 3, 4, 5, 6, 7. And so it becomes 10 to the 7th power. Where does my decimal go here? In between nothing. It goes after the 4. You see, if I were to put it before the 4, if I were to say 0.4 times 10 to the, that's too small for scientific notation. So this is just going to be 4.0 or just 4 times 10 to the negative. Now, why negative? Look at the original number. It's small. It's less than 1, so it's going to have a negative exponent. Negative what? 1, 2, 3, 4, 5. Where does my decimal go here for this last problem? In between the 6 and the 2. So I have 6.25 times 10 to the negative. Why negative? That's an awfully small number. Very small. So 1, 2, 3, 4, 5, 6. And that, my boys and girls, my dear friends, is scientific notation. Pretty exciting. Pretty exciting. All right. Bye. Back to basics. We're going to round out scientific notation info. And that's funny that I said round out because that's what scientific notation is. But we're going to talk about doing some crazy operations with scientific notation and not using a calculator. Now, for us to understand exactly what's going on, we need to realize that scientific notation just represents the big or small numbers of the world. If I take a number and multiply it by 10, and I take another number and I multiply it by 10, and they're both scientific notation, they kind of fall in the same category. So when I'm adding or subtracting numbers in scientific notation, and in this case I'm subtracting, if you see that they have the same exact base of 10 with the same exact exponent, it's just going to be part of your answer until something else happens that changes that. And then what you do is the numbers that live out in front, you do what the middle symbol says. So if the middle symbol says 6.33 minus 4.5, then you actually do 6.33 minus 4.5, and I don't know what that is, so let's pull that over here, minus 4.5. So you become 3, carry the 1, make it a 5, what is that, 8.1. So this becomes 1.83 times 10 to the negative 9. Okay? And we're going to do the same thing here. If I have a scientific notation problem and I'm adding or subtracting, and my base 10 is the same, you just keep that as part of your answer times 10 to the 5th. And whatever this part tells you to do, you do that with the numbers out in front. So 2 plus 3.8 is 5.8. Okay, not fun, not pretty, kind of confusing, but that's just how those are done. That's just how those are done with adding and subtracting. And I think we have more adding and subtracting right here, so let's do it again. This is the same, this is the same, so I keep that, 10 to the negative 8. Add these because of the plus sign. And that gives you 12.64. Now here's the issue. That's no longer scientific notation. So this is what we have to do. Since it's no longer scientific notation, I have to turn that guy into scientific notation. So what I do is I put the dot where it's supposed to go in between the 1 and the 2. So now it's 1.264. I move over to the right one, so it becomes times 10 to the 1st. And then this guy, times 10 to the negative 6ths, is just still hanging out. Now, we know from previous lessons that if I'm multiplying powers of the same base, I add exponents. So 10 to the 1st times 10 to the negative 6 is going to be 1 minus 6, which is negative 5. So that 10 becomes to the negative 5th, and still out in front, I have 1.264 times 10 to the negative 5th. Tricky. Very tricky. So that'll happen again later in the lesson. So if you're like, whoa, what just happened? You'll see. I'll do it again. And I'll try to explain it again a little bit more clear than I did that time. All right, I'm subtracting in the middle. 10 to the 8th, 10 to the 8th, keep 10 to the 8th. 9.2 minus 4 is 5.2, and nothing crazy happens with that one. Okay? That one's not bad. It's just stuff to remember. You have to remember stuff that you don't want to remember. Okay, now I'm multiplying, and you might think that multiplying is going to be worse, but in my opinion, it's actually easier. What you're saying here is 5 times 10 to the negative 7 times 3 times 10 to the 6. So let's group the things that are alike. I'm going to group 5 and 3 and put them next to each other. 5, I don't know why I put it backwards. 5 times 3 in red. 5 times 3. And I'm going to group the base 10s together. Times 10 to the negative 7 times 10 to the 6th. 5 times 3 is 15. When I'm multiplying powers of the same base, add the exponents. So 10 to the negative 7 times 10 to the 6 means I do 10 to the negative 7 plus 6, and negative 7 plus 6 is negative 1. Now, just like the previous problem, or 2 problems ago, that's not scientific notation. 15's too big. So I have to put a dot in between the 1 and the 5, so 1.5. It's a bigger number, so I move to the right once, so that becomes 10 to the 1. And what I still have left over is times 10 to the negative 1. When multiplying powers of the same base, add the exponents. 1 plus negative 1 is 0. So my final answer is going to be 10 to the 0, and 1.5 lives in front of it. Not fun. Not fun at all. Not fun at all. Okay? I'm going to rewrite this one. I'm going to rewrite this as 5.8 times 10 to the negative 6 over 2 times 10 to the negative 3. Now, it's a division problem, so I'm just going to make a fraction bar. And this is now what I'm going to do. I'm going to kind of split these up into 2 problems. 5.8 divided by 2. What is that, 3.9? No, 2.9. Over 1. I have a 10 to the negative 6. What happens there? Moves to the bottom. But I'm not going to do that. I'm going to switch this up. I have 10 to the negative 6 on... Well, no, you know what? I am going to do that. 10 to the negative 6 moves to the bottom, becomes 10 to the positive 6. 10 to the negative 3 here moves to the top and becomes 10 to the positive 3. Which 10 is more powerful, the top or the bottom? The bottom. So I'm going to... Remember, when I'm dividing powers of the same base, I subtract exponents. Since the bottom one's more powerful, I'm going to keep it on the bottom, and 6 minus 3 is 3. Now, that's not the way I'm supposed to write out scientific notation. If I have 10 to the third on the bottom and I'm forced to move it to the top, then 10 to the third on the bottom becomes 10 to the negative third up top. Tricky. Of course, I could do all of this on a calculator, but what fun is that? What fun is that? Not fun. Not fun at all. Okay, so I have another multiplication problem. 7.2 times 4. Let me move that over there. 10 to the negative 1. 10 to the negative 7. Now everything's grouped the way it should be. Grouped the way it should be. I am group. Let me see. 7 times 4 is 28. So 7.2 times 4 is 28.8. So that's not scientific notation anymore. When you're multiplying powers of the same base, add the exponents. So negative 1 plus negative 7 is negative 8. Like I said, 28.8 is too big, so I have to turn this blue part into scientific notation. So I put the dot in between the 2 and the 8, and I move to the right once because it's a big number, and I have 2.88. Since I moved over once, it's going to be times 10 to the 1. And then 10 to the negative 8 is still there. Look at my 10s. When I'm multiplying powers of the same base, I add the exponents. So 2.88, 1 plus negative 8 is times 10 to the negative 7. Tricky. And here, it doesn't get any nicer. So this is going to be our last problem. I'm going to rewrite that part up top, so 3.6 times 10 to the 7th divided by 7.2 times 10 to the 7th. Oh, look, 10 to the 7th over 10 to the 7th. they cancel out. 3.6 divided by 7.2 is 0.5. Now, is that written in scientific notation? No. How do I turn 0.5 into scientific notation? Well, 0.5 is a small number. My decimal should be here, so I go over one space. So I have 5 times 10 to the negative 1 because it's a small number, and there's where my negative 1 comes from. So it's a tricky section. It's a very tricky section. A lot of mental stuff, a lot of shifting things around, a lot of moving things around. Not a whole lot of fun, but it's done, and I made a rhyme. Bye. What up, what up? Another edition of Back to Basics. Let's see what we're getting into today. We've got exponential functions. Now, an exponential function is a function that increases at a much higher rate than a usual function. You see over here you have what would be a constant function. But an exponential function goes like that. It kind of curves up because it increases at a faster rate or decreases at a faster rate depending on what you're dealing with. Exponential functions look like that. A represents the initial amount. B represents the constant ratio. Okay, so that is how much you're basically doubling or tripling or halvesing or quadrupling or a thirding or something like that time after time after time again. And of course, our variable is x, and our variable is an exponent this time. So we're getting a little fancy. Getting a little fancy now. So basically, if you're going to look at these as a graph basis, they're going to look like one of four things. If A is positive and B is greater than 1, you're going to have a graph that starts flat and then curves upward. Okay? If A is positive and B is greater than 1. Now, B is never going to be negative in these cases because if it's negative, then we're dealing with a negative to a third power, which is negative, a negative to a fourth power, which is positive. So we kind of go up and down a little bit when we're dealing with negative B's. So that kind of doesn't fall into the exponential form bracket. But if A is positive and B is in between 0 and 1, so like a fraction, it's going to look like this. Go like that and then flatten its way out. And if you're wondering why, it's because you already have a number, and say if it's between 0 and 1, say B is a half, you take half of it, half of it, half of it. So it gets smaller. If A is negative and B is greater than 1, sorry, I hit the pause button. If A is negative and B is greater than 1, we're going to have something that looks like this. And if A is negative and B is in between 1 and 0, we start from the bottom, just like Drake, and then we flatten our way out. So those are our four options. Those of you who want to memorize and try to understand what exponential functions look like ahead of time, we're going to focus on using a lot of charts, and then maybe as we do more and more and more of these, we kind of get the hang of things and we realize we don't need charts near as much. So let's move my face. Let's make me skinnier. And perfect. Put me up there. Graph y equals 3 to the x and list the horizontal asymptote. Now, that's one thing that we've never mentioned, so we'll save the horizontal asymptote for the end of the problem. But what we have is we have y equals 3 to the x. I'm going to make myself a table and see what we have. So I'll start out with 0, 1, 2, 3. So I'm going to plug in 0. 3 to the 0th is 1. Anything to the 0th is 1. 3 to the x is 1. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. So let's plot what we have. I have 0, 1. That's point number 1. I have 0, 3. So 1, 3. Did I say 0, 3? 1, 3, not 0, 3. I have 2, 9, which is right 2 up. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I really can't put 3, 27. But this is what I'm noticing. Every time I move right to the one to the right, I triple my value. 1 becomes 3, 3 becomes 9. So it would make sense that if I move to the left, I would 1/3 my value. Well, let's just make sure. If I plug in -1, this becomes 3 to the -1st power. 3 to the -1st can be written as 1/3. So what's 1/3 of 1? 1/3. So these guys get smaller and smaller. But this is what's going to happen, and we have to be careful because it's tempting to go down here, but that's not going to happen. If I have a positive number and I take 1/3 of it, it's always going to be a positive number. It's just going to be a small positive number. So when I graph this, I start out nice and flat, and then I skyrocket to the sky. And we saw from the previous slide, if I have a positive number in front of my parentheses, which I do, I have a positive 1. And if I have a positive number greater than 1 inside my parentheses, it looks like this. Now, what's all this asymptote talk? Well, an asymptote is where your graph flattens out. It's basically where you could say, well, my line is going to awfully get really close to that guy, but it's never going to hit that guy. Okay, my horizontal asymptote is going to be this, the x-axis. Now you might be thinking, all right, well, what about my vertical asymptote? You'll never have one because a vertical, so basically this line right here will never get lower than the x-axis. It can't, no matter what I plug in, none of these will ever be negative. So my horizontal asymptote is basically that green line right there. Now, a horizontal line is the equation y equals a number with no x attached. And in this case, since it happens at the x-axis, my horizontal asymptote is y equals 0. Okay? No such thing as a vertical asymptote because no matter what, I can always plug in another x value and get a really large y. So there's no line that I can draw vertically to say that my line's going to flatten out. It's not going to happen. Okay? Let's look at another. And we'll review this from a chart point of view. Okay, so it looks like I really also need to plug in negative, so I'll have 0, 1, 2, 3, and then at the very end I'll deal with negative. Okay, so let's do this carefully step by step. If I plug in 0 to x, I get my parentheses to the 0th power is 1. So if I'm following PEMDAS, you deal with the exponent first, then multiply the number out here. So 1/2 to the 0th power is 1 times 2 is 2. Okay, 1/2 to the first power is 1/2. Then 2 times 1/2 is 1. Okay, 1/2 to the second power is 1/2 times 1/2, which is 1/4, and 2 times 1/4 is 1/2, or 0.5. So it looks like what I'm doing is I'm taking that number in here and I'm multiplying it to that guy every time. So this will be 0.25. By the way, what I just explained is exactly what I'm doing. Basically, the pattern is whatever number that is what you do to your dots as you move to the right. So the opposite is moving to the left. I'm going to multiply 2, but I don't want to do it that way. I just want to plug in -1. So if I have 2 times 1/2 to the -1. Okay, I take that parentheses only, and when you take a fraction to a negative number, you flip the fraction and now treat it like a normal exponent. So 1/2 to the -1 is the same thing as 2 to the +1, right? Or just 2. So last time I checked, 2 times 2 is 4. So if I'm multiply by 1/2 as my numbers get larger, I divide by 1/2 or multiply by 2 as my numbers get smaller. So let's plot what I know. -1, 4 lives right here. 0, 2 lives right there. 1, 1 lives right there. And then we get half the size, and then we get half the size, and we can understand what's going to happen. And just like last time, I'm never going to officially hit the x-axis. So if I divide by 1/2 going to the right, I multiply by 1/2 going to the left. So that 4 I can write here as an 8. To try my darndest to draw a really nice curve. I started out strong. I'm all right with that. Just like last time, I have a horizontal asymptote, and it's the x-axis, which means my horizontal asymptote is, again, y equals 0. All right, last one. Still going to make a chart. Even though I kind of feel like I understand what's going on, I'm still going to make a chart. I have x, I have y. I'm going to plug in -1, 0, 1, 2, and 3, if I can even make it that far. I think I can, because when you times by 1.5, it doesn't make it that much bigger. I'm going to start out by doing 0, so who cares to the 0th power is 1, times -2 is -2. 1.5 to the first power is regular 1.5, times -2 is -3. 1.5 squared times -2 is -4.5. Then the next guy is going to be -6.75. And when I plug in -1, you're going to have to trust me on this one. You're going to get, I think it's -4/3. It's -4/3, I think. Plug it in. -1, -4/3 lives around there. 0, -2 lives right there. 1, -3 lives right there. 2, -4.5 lives right there. And 3, -6.75. That looks good to me. And then if you want to add a few more points, it's just slightly getting smaller. So there you have it. Let me start my horizontal line. Then try to clean that up the best that I can. Oh. Yeah. Not pretty, but not impossible. All right. Exponential functions. You can do them making a graph, you can do them using common sense, but sometimes it's just more fun and easier to make a graph. And that's what I did 3 times. Thrice! Like a band. Alright, this was fun. Bye! What up? On Back to Basics today, we're going to talk about exponential growth and decay. Now, when something grows exponentially, it grows at a faster rate as time goes on. A constant rate would look something like this. An exponential rate would look something like that without the bumps and bruises using this terrible pen. Now, this is my formula. Y equals A, which stands for the initial amount, times the quantity 1 plus R, and R stands for the rate as a decimal, so it might be given to you as a percent. Turn it into a decimal. And X stands for the unit of time that you're dealing with. I don't know why I didn't put that there, but if this thing grows at like 10% per year and I'm given 10 years, I'm going to use 10 for X. So let's get started. The population of Sunnyvale, right over there, is 140,450 and increases at a rate of 2% per year. Predict the population in 5 years. So here's my formula. Y equals the initial amount, 1 plus rate as a percent, all to the X power. In this case, X is going to be years because it mentions 2% per year. All right, let's write down what we know over here. 2% is my R, but I'm going to write it down as 0.02 because 2% written as a decimal is 0.02. X is going to be 5, and my initial amount is going to be that large number right there, and it's just a matter of me throwing it into a calculator when all is said and done. You don't want to do these in your head. So Y equals the initial amount, which is 140,450, times the quantity 1 plus 0.02, all to the 5th power. So just to play a little bit of cleanup, I'll put 140,450 times 1.02 to the 5th, and we'll make good old Siri do all the work. What's 1.02 to the 5th power?
The answer is approximately 1.104.
Oh. So 1.104. We are going to multiply 140,450 to that. Again, Siri will bail us out. 140,450 times 1.104.
It's 44,767.2.
44,000. That's not right. 140,450 times 1.104.
The answer is 155,056.8.
56.8. So we'll round that up to 57 because you can't have a sixth of a person or 0.8 of a person. And that's what we get. That's my population. Okay. Not bad. Not bad at all. A YouTube channel has 55,000 subscribers and sees a 450% increase per year. How many subscribers should that channel have after 6 months? Oh, YouTube, like me. Let's use that formula again. Y equals A times the quantity, 1 plus my rate as a decimal to the x power. My initial amount is 550,000, so 55123, and that's my A. My rate is going to be 450%. So that's 4.50, because you move the decimal over twice. Here's the tricky part. It mentions that the increase is 450% increase per year. However, I'm given 6 months, which means my time is not 6. My time is a half, or 0.5. So when I say it, I'll actually use 0.5. It doesn't really matter because I'm going to use, again, Siri to do all the heavy lifting for me. So Y equals 55000 times the quantity 1 plus 4.50 or 4.5 to the 0.5 power. All right. So that becomes 55000 5. Oh my gosh, that looks awful. I don't like this marker. I don't like this pen. So I have 5.5 to the 0.5 power. So 5.5 to the 0.5 power is going to be a god-awful mess. What's 5.5 to the 0.5 power?
Here's what I found.
Wow. What's the square root of 5.5? What's the square root of 5.5?
It's approximately 2.3452.
2.3452. If you're wondering, where did you get square root from? Anything to the half power can be written as square root. So I have 55,000. 55,000 times 2.3452.
It's 128,986.
And that's how many subscribers I should expect to have after 6 months. I like it. I wish it was me. It's not. All right, I traded pens. Hopefully this one works a little bit better than the one that I spent $17 on Amazon for. So, next guy is exponential decay. Exponential decay is the same idea of exponential growth, but instead of exponential growth being getting larger faster, decay gets smaller slower. So regular decrease looks like that if it's constant. Okay, exponential decay is like the idea of I have a large amount and it gets smaller, but since every time I get smaller, I'm getting less to get rid of, and so it takes a lot longer to get rid of. So it's kind of like if I were to boil some hot water, right? And I start out with a gallon of water, and after I boil it for like a half an hour, I'm going to have half a gallon. Well, I'm not going to have zero if I boil it for another half hour. I'm going to have half of that and half of that. You keep taking half and half and half of things, and so things slow down at a much slower pace. So very similar to what we just dealt with. I have an initial amount. I do 1 minus r as a decimal, taken to the whatever time period power that I'm given. All right, so the exact same formula, but with a minus this time. So in this case, we could talk about a car depreciating. Depreciate is a fancy word for gets less in value. Okay, so a car loses its value by 20% per year. So my rate is going to be 20% written as a decimal, which is 0.2. I like this pen already. What is the value of a $32,000 car, A, after 7 years, X? So pretty basic. Okay, nothing fancy to worry about. No weird X's like I had last time. And you don't want to get me started on weird X's, am I right? Y equals my initial amount times the quantity, 1 minus my rate to the x power. Y equals my initial amount, 32,000. 1 minus my rate as a decimal, so 0.2 to the 7th power. Okay. I'd hit pause. Regular 0.8 to the 7th, 32K, 0.8, 0.8 to the 7th power. It's just not going to say it. It's just going to tell me that it's 0.2097. So I'm going to have a small chunk of that money left over. 32,000 times 0.2097.
It's 6,710.4.
So 6,710.4 equates to 40 cents with 6,000 some dollars. So my car is worth that much at the end of the day. Well, this video was a disaster, but I had fun because now we know how to deal with exponential growth and exponential decay. With my terrible handwriting using 2 different pens, both of which just don't work that well. Well, thanks for watching. I hope you had as much fun as I did, which wasn't a whole lot, but it really was. Like and subscribe. Bye! What up, what up? Today we're going to talk about the exciting world of compound interest. What's compound interest? Well, you put money in a bank account, right? And when you put money in a bank account, they're like, we're going to grow your money a little bit at a time. And you can look at your bank account at the end of every month and find out what you have. And we'll do that again at the end of every month. And we'll do it again, and we'll do it again, and we'll do it again. So like maybe I put in, what's a realistic amount for me? $1 million. And so at the end of month number 1, I now have $1,010. And at the end of that month, I have $1,021. And at the end of that month, I have $1,033. Notice I'm not going up by the same amount every time. I'm going up by a little bit more because what's happening is as I have more money to get compounded, it gets higher and higher and higher faster. So this is a form of exponential growth, where if I start out with a certain amount of money, at the end of whatever time period, it grows. Then that amount grows. Then that amount grows. So it's going to grow a little bit more and more and more and more and more each time. Well, that leads us to this fun equation right here, compound interest formula. Now, there's a lot to look at here, I realize. So if you're like, I don't know if I really want to memorize this, I don't blame you. But that's compound interest. Okay, you start out with your amount that you're going to get when all is said and done. Okay, principal would be that $1 million that I talked about. 1 in this case stands for like 100%, plus R over N. Now, R is the interest rate that you're dealing with as a decimal. So if we use 25%, I'm going to turn that into 0.25. N is the number of times that interest is applied over a time period. All right, so if I mentioned monthly and I care about what's going on after 5 years, monthly is going to be 12. Okay, 12 times per year. If I use words like quarterly, N is going to be 4. If I use it semi-annually, N is going to be 2, as long as I'm discussing time in years. And then T is times in years. Okay, so we're going to use n twice in this problem. So let's get to it. Mr. Cheese. Wrong button. Mr. Cheese makes an initial investment of $5,000. Find the value of the investment after 3 years if the investment earns a return of 10% compounded monthly. All right, let's write out our formula. We have the final amount. We have the final amount is going to equal. Why did I make my A look like that? This is going to be another fun video. If you watch my growth and decay one, you realize that that one was a train wreck as well. So what am I doing? My final amount in a different color is going to equal my principal times 1 plus r over n to the nt power. Now let's label things and change things if I have to. 5,000 is my principal amount. That's what Mr. Cheese put into the bank account. Investment at 3 years, so 3 is going to be my T. So 3 is T. Earns a return of 10% compounded monthly. So what that means is 10% is my rate, but I'm going to write it out as a decimal 0.1. And compounded monthly means that I am compounding 12 times per time period, which is per year. So n is 12. Okay, so I throw this all in. That's going to equal 5,000 times the quantity 1 plus r, which is 0.1, divided by n, which is 12, all to the n, which was years, no, which was 12, sorry, times t, which was years 3. So I got a little bit of math to do here, some of which pleasant, some not so much. 5,000 doesn't change, not yet. I'll deal with that at the very end. 0.1 divided by 12, no idea. 0.1 divided by 12.
That would be approximately 0.008333.
So I'm going to make this 1.008333 taken to the 12 times 3, which is the 36 power. If you're wondering where I got, if it told me that 0.1 divided by 12 is 0.008333, I'm adding 1 to it. Where did 36 come from? 12 times 3. And so according to PEMDAS, I deal with that exponent right now. 1.008333 to the 36 power.
It's approximately 1.3481.
So that becomes, let me make sure that I said that right. A lot of times when I say something in the Siri, it misinterprets what I say. But that worked out fine. 5,000 times 1.3481.
The answer is 6,740.5.
Now we're dealing with money. So if I turn that into how much, find the value of the investment. So that's what I'm looking for. A is the value of the investment. That's going to end up being $6,740.50. Ooh, 50 cent, my favorite rapper. That's not true. XXX Tentacion, rest in peace. Good job, Mr. Cheese. You made yourself like $1,000 some dollars after 3 years. Is this a realistic problem? No, not at all. Not at all. This isn't realistic that much either, but we're talking about another rapper, NBA Youngboy. Youngboy never broke again, invested $3,500,000 into an account that earns 2.5 interest quarterly. How much will his investments be worth in 25 years? And, there's 2 questions. Let's deal with question number 1 first. So we've got our formula again, which is my principal times the number 1 plus the rate divided by whatever the compounded value is or the compounded amount is to the NT. I'm going to say that that's my P. My rate, and I'll write it over here, is going to be 0.025 because that's my rate as a decimal. My time is 25 years. My N is quarterly, which means 4 times a year. And then I plug it all in. Okay, 3,500,000. Yep, times 1 plus R, which is 0.025, divided by N, which is 4, to the NT, which is 4 times 25. I can handle that math. What I can't handle is whatever 0.025 divided by 4 is. Although I probably could. It'll be like 0.00625. 0.025 divided by 4.
The answer is 0.00625.
Nailed it. So I'm going to add 1 to that. That ding, by the way, just affirms that I nailed it. It has nothing to do with me getting a notification. I really don't get a whole lot of those, considering I'm a math teacher currently in my basement. So where did I get 100 from? 4 times 25. Where did I get 1 point blah, 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 blah from? That guy plus 1. And now I'm going to multiply that number to 3,500,000, see what I get. 3,500,000. Oh, no. I need to do that guy first. I take it back. 1.00625 to the 100th power.
The answer is approximately 1.8646.
And I did say that correctly. So 1.8646 times 3,500,000.
That would be 6,526,100.
Wow. NBA young boy, that's a lot of money. Wow, it never broke again indeed. Wish I made that much money. I mean, I will in about 3 years, but it's just I'm not there yet. All right, cool, great. So how much will his investment be worth in 25 years? That's the answer right there. But as you may remember, there's 2 parts to this question. How much did his investment grow? What does that mean? That means I started out with 3,500,000 and now I have $6,526,100. So how much did it grow? That's a subtraction problem. 6,526,100 minus 3,500,000.
That would be 3,026,100.
So his value almost doubled. Unbelievable. Unbelievable. I'm proud of you, NBA. Proud of you. Accomplished a lot. And so did we. This is fun. Like and subscribe. Thanks for watching. Bye. What up? Today in Back to Basics, we are going to be talking about the old geometric sequence. Now, a geometric sequence is when, in order to get from one term to the next term, you multiply the same number and over and over and over again. So if I were to look at this guy, I would say the common ratio, which we will denote by the letter R, is the number that I multiply to get from this guy to that guy, this guy to that guy, this guy to that guy. And in this case, we times 3, times 3, times 3. So the common ratio is going to be 3. So the way we'd find the next one is we multiply by 3, get 162, so on and so forth, so on and so forth. Now, this question is asking, is this pattern geometric? If so, what is the common ratio? Well, we're going from negative to positive, negative to positive, negative to positive, negative to positive. So if the answer is yes, it's going to be a negative, but we have to figure out if we're multiplying the same negative every time. So in order to get from negative a half to positive 1, we multiply negative 2. So 1 times negative 2 is negative 2, times negative 2 again is 4, times negative 2 again is negative 8, times negative 2 is 16, times negative 2, and we hit the jackpot. The common ratio is negative 2 because every time we move along to the right, we multiply by negative 2. So was this geometric? Yeesh. And what's the common ratio? That guy right there. So far, not so bad until now. We have two formulas for the geometric sequence. We had before arithmetic sequences, we had a recursive formula for that as well. This is the recursive formula for the geometric sequence. Now, A sub n stands for like the 18th term, which would be like n is 18. R is the common ratio, just like in the last two problems, and I would plug in the previous term. So basically what this does for me is if for any reason I'm like, hey, you have the 17th term, or the 17th term, I need you to find the 18th term, that would be useful here because if n was 18, that would become 17. So if I were to just write a recursive formula for the sequence, I don't know what n is, so I would say a sub n. What I can find out is the fact that I divide by 2 every time. Now, if I divide by 2, what that makes my common ratio is multiply by a half. So I would make that 1/2 up equals 1/2 times a sub n minus 1. So that is just the recursive formula for any regular sequence that I see right there. Yeah, nothing fancy about it. Kind of a pointless thing. This is a little bit more important, the explicit formula. The explicit formula involves more cursing. I'm just kidding. I'm just razzing you. This is if I ask you for the 18th term, I'm given the first term, it equals the first term, times the common ratio to the n minus first power. So in this case, it's asking me to find the 12th term of that sequence right there. So if I'm going to find the 12th term, n is 12. My first term is that guy right there, negative 0.25. Looks like every time I multiply by 2 to move to the next one, so that gives me a common ratio of 2, and I just set it up. I need a sub 12. That's going to equal a sub 1, which is negative 0.25, times the common ratio, which is 2, to the n minus 1, which is 12 minus 1, the 11th power. Okay. According to PEMDAS, I do the exponent part first, so that will be negative 0.25. 2 to the 11th, according to the top of my head and not looking at a computer, is 2048, the year of my eventual death. And then if I multiply that by negative 0.25, I get negative 512. So the 12th term in this sequence that starts out with 0.25, negative 0.25, multiplying by 2 ends up being negative 512 once you hit that 12th term. Let's do it again. So I have the 9th term. I need to find the 9th term, a sub 9. This is my first term right there. It looks like every time I move to the right, I'm dividing, which means I multiply by a fraction. So my common ratio, it looks like I'm dividing by 2, but not only 2, negative 2. That gives me a common ratio of negative 1/2. So a sub 9 is going to be a sub 1, which is the first term in our sequence, times r, which is negative 1/2, to the n minus first power, which is going to be 9 minus first power, which is going to be 8. again, according to PEMDAS, what I do is I do the exponent first. So, I don't know, off the top of my head, negative a half to the 8th power is positive 1 over 256. If I combine that, that appears to be negative 1.5625. And that probably becomes a fraction, but you know what? Who cares? That was fun. Well, thanks everybody for watching. I hope you have a pleasant day. Bye. Back to basics, back to basics, back to basics, back to basics, back to basics. Look, repeating. Decimals. 4.1 with a line on top. What does that mean? Oh, 4.111111111. Fun fact, if you have repeating decimals, however many numbers are repeating, and in this case 1, and in the middle one it's 3, and in the third one it's 1, you write that repeating decimal over as many 9s. For example, 0.1 is repeating. So you put 1 over a 9. 4 lives in front. Dunzo. Look at the fraction. Can I simplify 1 over 9? Nope. I'm done. Second problem, I have 0.510. 0.510 repeating. That's 3 numbers. So I'm going to put it over 3 9s. Don't forget the 11 in front. Can you simplify 510 over 999? Yes. You can actually divide the top by 3 and the bottom by 3. 510 divided by 3, 510 divided by 3 is 170. 999 divided by 3 is 333. Can I simplify those any further? No. 0.5 is repeating, which is 1 number. So I'm going to put it over 9. Can I simplify that? Nope. Make it negative. Easy. Easy. That would be negative 0.555555555. Oh, look, more repeating. So 0.77777 is the same exact thing as 0.7 with a line over it. And if I want to turn that into a fraction, you would make that 7 over 9 because it's just 1 7 being repeated. So put it over 1 9. 0.23, 0.23, 0.23, 0.23. Put 23 with the line over it. 0.23 if you need to have that 0 there, which you don't. That's 2 numbers repeating. Put that over 99. Can I simplify that? No, I'm done. Put 85 repeating, so 0.85 repeating. Put a 0 in front of it if you have to. That's 2 numbers repeating. Put it over 99. Can I divide anything by 3? Nope. I'm done. Fast and fun. Bye. What up, what up? Today we're going to talk about naming polynomials. Now there's 2 ways that you can name polynomials. The first way that we're going to talk is naming them by degree. Now the degree is the highest exponential value. For example, if I have something with that's 3x squared plus 2x to the 8th, the highest degree is that 8. So that's kind of what we're dealing with. Let's get rid of you. We won't talk about anything as crazy as that. We're actually going to start out with a degree of 0. Now, a degree of 0 goes by the name constant. Now, if it has a degree of 0, that means it is something with x to the 0th power, like a regular number. X to the 0th power is 1. So something like 3x to the 0th power is 3 times 1, which is 3. So a constant is just a number that doesn't have any variables attached to it. that has a degree of 0. If it has a degree of 1, we call that linear. Now, an example of a linear equation could be 3x minus 5. The highest exponential value is a 1, so I have 3x to the invisible 1 here. If the degree is 2, we call that quadratic. So an example of that could be 8 minus 4x squared. If the degree is 3, that's a cubic. So an example of that is negative x minus x squared minus x cubed. It's literally making stuff up. Again, the highest degree is a cube. Doesn't really matter the order that things go in, you just look at it. And we'll stop with the degree of 4. That is a quartic. And I'll just put x to the 4th, because why not? Doesn't matter how many terms it is, it's just the fact that x to the 4th is the highest. If I put 5, it's quintic. There's others, but we're not going to worry about that. Anything after the 4, does have a name, but like I said, we're not going to worry about that. If you have a polynomial, you can name it by how many terms it has. For example, 5x minus 3 has 2 terms. So let's name those. Let's start out with 1 term. You can't have something with 0 terms. If it's a 1 term, it's a monomial. Mono means 1, so 1 term is monomial. So something like 3x to the 5th is 1 term. If it has 2 terms, we call that a binomial. And that could be like x plus 9. Okay. 3 terms is a trinomial. And that could be like x to the 9th minus 2x plus 1. 3 terms. And anything after that, we just say n term because, we don't want to name too much. So we're going to ignore that example right there. Okay, so 4 term, 5 term, 6 term, 7 term, stuff like that. Let's name some of them, shall we? We have a thing with 2 terms, and the highest degree is 2. So we would call this, if it's 2 terms, it's a binomial. And since the highest degree is 2, it is quadratic. Usually we give it the name based off of the degree first. It just sounds better in the English language, don't know why. But this is a quadratic because the highest degree is 2. And since there's 2 terms, binomial. So this is a quadratic binomial. This guy has 1, 2, 3, 4 terms. So I will call that a 4 term. And the highest degree is a 4. So it's a 4 term quartic. Okay. Pretty simple so far. And we've got ourselves a nothing. There's x to the 0th power, so that is a constant. And since there's only 1 term, we will say constant monomial. Quick video. Pretty basic, pretty easy. That's that. Bye. What up, what up? Today we're going to talk about adding and subtracting polynomials. Now, our main focus is we're going to be given a couple sets of parentheses, and we're going to maybe distribute a negative, maybe not. We're going to combine like terms and then write things out in standard form. Now, what standard form is? You take the highest degree, work your way down. But first things first, let's simplify. If I have either a nothing or a plus sign in front of the parentheses, we don't need the parentheses. This has nothing in front of it, so I'm just going to get rid of those parentheses. 5p squared minus 3. This has just a plus sign in front of that parentheses, so I don't need them. Plus p squared minus 3p cubed. Now I'm going to look at each guy and I'm going to combine like terms. So I see that 5p squared is a like term with 2p squared. So that gives me 7p squared minus 3 combines with nothing, minus 3p cubed combines with nothing. What I want to do now is I'm going to write this out in standard form, which means I start with my highest degree. So I have negative 3p cubed, done, positive 7p squared, done, minus 3, done. Okay, not so bad. This one's slightly different though. Let's follow the same rules. I have nothing in front of my parentheses, so I don't need them. 4n minus 3n cubed, but I have a negative in front of the parentheses. If you have just a negative in front of a parentheses, you distribute the negative, which means you flip the signs of everything inside the parentheses. So 3n cubed becomes minus 3n cubed. Positive 4n becomes minus 4n. 4n combines with negative 4n to just disappear. How about that? Negative 3n cubed minus 3n cubed is negative 6n cubed. I don't have to worry too much about writing it out in standard form because it's just a monomial. It's just by itself. Dunzo. Easy, that one. How nice. But of course it always gets worse. Last one though, no worries. If you have nothing in front of a parentheses, you don't need them. 12a to the 5th minus 6a minus 10a cubed. If you have a negative living in front of a parentheses, distribute the negative. Minus 10a. Negative times a negative is positive 2a to the 5th. Negative times a negative is positive 14a to the 4th. And then let's see if I can combine anything. 12a to the 5th combines with 2a to the 5th to give you 14a to the 5th. Negative 6a, negative 10a combines to make negative 16a. Negative 10a to the 5th, or is that a to the 3rd? Negative 10a to the 3rd doesn't combine with anything, so that's negative 10a to the 3rd. It would be nice if I can read my own handwriting. You know, I think my handwriting looks a-okay. Plus 14a to the 4th. Now what I'm going to do is I'm going to write this in standard form, also known as descending order. The largest degree is 14a to the 5th, so that's already in the right spot. Then I have 14a to the 4th, so positive 14a to the 4th. Then I have negative 10a to the 3rd. And last but not least, negative 16a. That is all. That's all she wrote. Adding and subtracting polynomials. That was fun. Bye. What up? Today we're going to talk about foiling, which is one of my favorite things. Now, FOIL is an acronym. And what you do with foiling is you multiply two binomials together, and FOIL is the way in which you do it. For example, when it mentions here that I want to do first, I'm going to multiply the first terms in each parentheses first. 2 times 2 is 12. N times n is n squared. Dunzo. Then outer means I multiply the outer parts of the two parentheses. So 2 times 1 is 2. N times 1 is n. And since that's positive, you put a plus sign there. Okay. Inner are the two inner terms. 2 times 6n is 12n. Kind of did that one faster than I wanted to. But 2 times 6 is 12. Nothing times n is n. And then last but not least are the last guys. Multiply the last terms in each parentheses. 2 times 1 is 2. And that's the FOIL part. You literally distribute twice. It's like a double distributed property. You take each term inside each parentheses and you distribute it to every term in the other parentheses. Since I'm multiplying 2 guys by 2 guys, I end up with 4 terms. That's the way it works. Now, what usually happens when you do these, not always, what usually happens is you're going to have some combining like terms. And so the 12n squared doesn't combine with anything. The 2n and the 12n add up to make 14n, and then 2 is just all alone, all by itself. That is how you FOIL. Love foiling. Boy, love it. So let's find each product. So I have x first. X times 6x is going to be 6x squared. X times negative 2 is negative 2x. Negative 3 times positive 6x is negative 18x. And negative 3 times negative 2 is positive 6. Can I combine like terms? Yes, I can. I can combine these two. That gives me negative 20x. On the left, I have 6x squared. On the right, I have plus 6. I've foiled away. Fun! Ooh, the F in FOIL should be fun because that's what this is for me. Now, an evil sinner would say, well, that's just 16p squared minus 1. That makes you an evil sinner. You see, what I'm squaring here is not 4p and negative 1. I'm squaring up parentheses, which means you're going to write out parentheses times parentheses. This is called a perfect square trinomial when all is said and done. Right now you might be saying, trinomial, doesn't that mean 3 things? It does, and it will. Watch. I'm going to have 4p minus 1 and 4p minus 1. Whenever you take a parentheses and square it, you multiply that parentheses to itself. So now what this looks like is a FOIL problem. 4 times 4 is 16, and p times p is p squared. 4p times negative 1 is negative 4p. Negative 1 times 4p is negative 4p again. That's weird that it's the same thing. And then negative 1 times negative 1 is positive 1. So I can combine these guys in the middle and make this 16p squared. Negative 4p minus 4p is negative 8p minus 1. So a perfect square trinomial is when you have a binomial times itself. And what you're going to end up with is the guy on the left side is going to be whatever this first term is squared. The guy on the right side is going to be whatever this second term is squared. And the guy in the middle is the product of the two of them times 2. So 4p times negative 1 is negative 4p times 2 is negative 8p. So, a little fun fact. Now this isn't a standard FOIL problem. A standard FOIL problem is a binomial times a binomial. Well, I have a binomial times a trinomial, but that won't change what I do. I'm going to take 4a and I'm going to multiply it to all 3 of those terms one by one. 4a times 6a squared is 4 times 6 is 24. A times a squared is a cubed. And then I do it again. 4a times negative a is 4 times no number. Well, I guess technically negative invisible 1 is negative 4. and then a times a is a squared. Now I'm going to multiply 4a to this last guy, which is a 2. So 4 times 2 is positive 8, and then a is kind of all alone by itself. Now that I'm done dealing with the first term in this parentheses, I move to the second term and multiply that guy to everybody as well. 2 times 6 is positive 12, and then a squared comes along for the ride. 2 times negative a is negative 2a. Oh, I get to pick my own color. Orange! 2 times 2 is 4. And let's see if I can combine any like terms. And I'm looking at it. I can. First off, nothing combines with 24a cubed, so I have 24a cubed. Negative 4a squared can combine with positive 12a squared, so that's going to give me positive 8a squared. I have 8a combining with negative 2a to give me 6a. And last but not least is that plus 4 just hanging out all by himself. Everything's written in standard form. Everything is in descending order. I am super stoked. Oh, I just hope that the next one isn't going to be like 3 times 3 terms. We'll see. Oh, crap. Now, I get to be really creative with my colors here, because what I'm going to do is I'm going to multiply 6n squared to all 3 of these, then negative 6n to all 3 of these, then negative 5 to all 3 of these. So 6n squared times 7n squared is 42 n to the 4th. 6n squared times 6n is going to be positive 36 n to the 3rd. 6n squared times negative 5 is going to be negative 30n squared. Negative 6n times 7n squared is going to be negative 42n cubed. Negative 6n times 6n is negative 36n squared. Let's go with like a nice pink. Negative 6n times negative 5 is positive 30n. Let's try gray. I don't know. Negative 5 times 7n is negative 35n squared. Not 7n, n squared. Let's do that orange again. I like an orange. Negative 5 times 6n is negative 30n. And last but not least, what color haven't I used yet? How about a nice teal looking color thing? Negative 5 times negative 5 is positive 25. Just fit it in. Now let's combine like terms. Nothing combines with you. 42 n to the 4th. 36n cubed combines with negative 42n cubed to make negative 6n cubed. Negative 30n squared minus 36n squared is negative 66n squared minus 35n squared is going to be negative 66 minus 35. Is that on negative 101? N squared. Oh, look. 30n minus 30n cancels each other out. And then plus 25 is just kind of left over. Yeah. Woof. I do like a FOIL problem. I'm not going to lie. I enjoy a FOIL problem thoroughly. And that's that. Okay? Thanks for watching. Like and subscribe. Bye. What up, what up? On Back to Basics today, we're going to talk about factoring. Now, factoring is basically reverse distribution, right? You know distributed property. You have a number attached to a parentheses, and you say 3x times 15 is 15x. 3x times 2x, 3 and 2 multiplied to make 6. X times x is x squared. That's distribution. Now, factoring says, I'm going to give you this guy right there. I want you to make it look like that. So basically what we need to do is it's two parts. We need to look at every term inside the parentheses. What number can I divide out of each term? What number can I divide out of each term? The largest number that I can divide out of each term, so 3. And how many, or what's the largest amount of letters that I can pull from each one? I can pull an x from here, I can pull 2 x's from there, but the largest I can pull from both is just 1x, so 3x. Once you do that, what's left over is you divide the coefficients, so 3 divided by 15, or I guess 15 divided by 3 is 5, and you subtract the exponents. If I take away an x from an x, I have no x's. If I divide 3 from 6, that's a positive 2, and if I take away an x from an x squared, that leaves me with just an x. So factoring is that. You look at your polynomial, you look at the numbers separate from the letters, and you say to yourself, what's the largest number I can divide from each number, and what's the most amount of letters I can take from each term? And then you pull them out, and then you see what's left over. So here we go. Let's just get started. Okay. We need to figure out what is the largest number that I can divide out from each of these. I have a 9, I have a 3. The largest number I can divide from 9 and 3 is 3. In each term, I have x's. What's the largest number of x's that I can pull out of each term? I have 2 here, I have 1 here, so the largest number that I can pull out is just 1x. Okay, now inside the parentheses, I have my leftovers. 9 divided by 3 is 3. If I take 1x from 2 x's, I have 1x left over. If I have a minus sign, 3 divided out of 3 is 1. If I take out an x from an x, I have no x's, so I'm not even going to put anything there. So essentially what I have is if I were to distribute this out to make sure I did it right, 3 times 3 is 9, x times x is x squared, 3 times negative 1 is negative 3, and x times negative 1 is still negative x. I did it right. Okay, let's do another one. I have 2 terms. I'm going to say what is the largest number I can divide out of each term, and it looks like 4 is the largest number that I can divide out of each term. I can't do 6, I can't do 8, so it's 4. What's this largest amount of x's that I can pull out from both of these? Well, I have 2 here, I have 1 here, so the largest amount of x's that I can pull out of both is just 1x. Now my parentheses is going to be the leftovers. 12 divided by 4 is 3. If I remove an x from 2 x's, I have 1x left over. Drop down the minus sign. If I divide a 4 from 16, I get 4. If I remove 1x from 1x, I have no x's left over. I'm done. To check my work, 4 times 3 is 12, x times x is x squared, 4 times negative 4 is negative 16, x times nothing is just an x. I did it right. I did it right. What's the largest number that I can divide from 8 and 16? 8. Each term also has an m. What's the largest amount of m's that I can divide from m cubed and m squared? Well, I can pull 3 from here, but I can only pull 2 from there. So the largest amount of m's that I can pull out is m squared, 2 of them. Now there's a third thing here, an n. But you don't have an n. So I can't pull out a common factor using that n. So can I pull out a common thing? No, n is just there. So what's my leftovers? Well, if I divide 8 from 8, I get invisible 1. I'm going to hold on to that. If I take m squared from 3 m's, I'm left with 1m. So that invisible 1 is there, but I don't need the invisible 1. If I divide 8 from 16, I get 2. If I pull 2 m's from 2 m's, I have no more m's. And I have nothing here, so I have like this little n just kind of floating around. That's my leftover. That's my answer. So to check my work, 8m squared times m is 8m cubed. 8m squared times 2n is going to be 16m squared n. I did it right. One more. Now I have 3 terms. Still one letter, but 3 terms. What is the largest number I can divide from 4, 2, and 8? I can divide each of these by 2, but that's the biggest number I can divide, so I'm going to bring out that 2. Everything also has a b. What's the largest amount of b's that I can pull out from each of these? I have 3, I have 2, I have 1, so the largest amount of b's that I can pull out from each of them is 1. Now to do my leftovers, my scraps. 4 divided by 2 is 2. If I remove a b from 3 b's, I have 2 b's left over. 2 b's, or not. It's 2 b's. It was a Shakespeare joke. 2 divided by 2 is invisible 1. I'll hold on to that. If I remove a b from 2 b's, I have a b. So invisible 1, b is what's left over there. 8 divided by 2 is positive 4. If I remove a b from a b, that's it. No more b's. Sounds awesome to me. I hate b's. But that problem is the bee's knees. And if I wanted to check my work, 2 times 2, 4. B times b squared, b cubed. 2 times invisible 1, 2. B times b is b squared. 2 times 4 is 8. B times no b is b. I did it right. 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 That is basic factoring, ladies and gentlemen. Basic factoring. Thanks for watching. Bye. What up? Today in Back to Basics, we're talking about factoring quadratic trinomials. Now, factoring quadratic trinomials is the opposite of FOIL. What's FOIL? Well, first, outer, inner, last, of course. In other words, a binomial times a binomial is b times b. It would be nice if I had the marker selected. B times b, which is b squared. B times negative 2 is negative 2b, or not, negative 2b. Negative 4 times b is negative 4b. And negative 4 times negative 2 is positive 8. Now I can combine these guys, and I'll write it here. I'll get b squared minus 6b plus 8. Now, this is FOIL. Factoring is the opposite of multiplication. You might remember from my last video, those of you who watch my videos religiously, which is basically just my mom, you know that factoring is the opposite of multiplication. So if I'm going to factor quadratic trinomials, and that's going to be FOIL, then the opposite of FOIL is basically defoil. I like to use a clever little word called sometimes. Now, in our cases, this is a standard form of a quadratic. And everything we do today, we're going to pretend that A is not there. A is 1. So we're not going to worry about A being anything but invisible 1. If I start a quadratic out with x squared, I need to find two numbers, sometimes two numbers whose sum, which means add, is b, and whose times, which means multiply, is c. Two numbers whose sum is b and whose times is c. Let's make believe that those numbers are 5 and -3. Once I come up with those numbers, then my answer is going to have me put that 5 and -3 in the parentheses, +5, -3, and throw x's in front of them, and that's my answer. Okay? So that's what we're dealing with here. I'm going to give you something that looks like x squared plus something x something, or x squared minus something x something. So I have to figure out what two numbers gives me the number in front of x if I add them, and what two numbers gives me c if I multiply them. Once I figure those numbers out, I plug them into those parentheses, dunzo funzo. Now we're going to do a bunch because this is very, 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 very important stuff, and it's not going to go away anytime soon. So I have a quadratic trinomial. I have nothing but b squared, so invisible 1 in front of it. I'm allowed to use sometimes. I need to find two numbers whose sum is 8 and whose times is 7. What two numbers? Well, first off, if they add up to +8 and multiply to +7, they both have to be positives, so that might help. Two numbers that multiply out to 7 and add up to 8. I know 1 times 7 gives me 7, and 1 plus 7 gives me 8. My answer is x plus 1 times x plus 7. The way I'd check my answers is I'd FOIL them out in your head. X times x, oh, it's supposed to be b. Sorry, it's supposed to be b. b plus 1, b plus 7. So b times b is b squared. B times 7 is 7b. 1 times b is 1b. So 7b, 1b, 8b, and 1 times 7 is 7. Did it right. Yay me. Let's do another. All right. N squared minus 11n plus 10. Nothing in front of n squared. I'm good as gold. I need two numbers that add up to -11 and two numbers that multiply to 10. So in order for that to work, if they're going to add up to a negative but multiply to a positive, I need a negative and a negative. So let me think. 5 and 2, will -5 plus -2 give me -11? No. 1 and 10. If I multiply -1 to -10, I get +10. -1 plus -10 is -11. I got it. What letters do I care about? N and N. Done. Done. Another one. M. Nothing in front of m squared. All right. So I need two numbers whose sum is, there's no number there. Invisible 1. Whose sum is 1, two numbers that add up to 1, but multiply out to -90. -90. So if they're going to multiply out to a negative, I'm going to have a positive and a negative number. If they multiply out to a negative, I'm always going to have a positive and a negative number. These guys add up to 1, though, which means whatever two numbers I choose, my larger number has to be the positive because it adds up to 1. So let me think. Two numbers that add up to 1. Oh, how about this? How about 10 and 9? Now, which one gets the negative? 10 or 9? Well, it's 9 because if I add these up, +10, -9 make +1. If I switch them around, it would be -1. Let's throw our m's there. Let's throw our m's there. Bada bing. That's my answer. And again, you can FOIL it in your head. M squared minus 9m plus 10m is regular m. 10 times negative 9 is negative 9. You did it right. Okay. Nothing in front of n squared. So I have 4n. So I need two numbers whose sum is 4, whose times is negative 12. So another multiply out to negative 12 again, which means I need to have a positive in here and a negative in there. They add up to a positive, which means whatever numbers I choose, the larger number has to be positive. So you could do 4 and 3. That won't work because 4 and 3 make just regular 1. I can do 6 and 2 because positive 6 and negative 2 add up to 4. Positive 6 and negative 2 multiply out to negative 12. Put your n's right there. Dunzo. I could have sworn I did that one, but I just did one similar to it. No matter. Two numbers whose sum is a negative, whose times is a 9. So if they multiply out to a positive but add up to a negative, I need a negative and a negative. Why? Because a negative times a negative is a positive, and a negative plus a negative is a negative. Two numbers that multiply out to 9 add up to negative 10 are 9 and 1. Put an n there, put an n there. There you go. It doesn't matter if I put the 9 here and the 1 here. If I put the 1 there and the 9 there, it wouldn't make a difference. The only time that it does matter is if one of these is a positive and one of these is a negative, then you have to be careful where you put your numbers. But here I don't care about where I put my numbers because they're both negative. The order does not matter. B squared plus 16b plus 64. I need two numbers whose sum is 16 and whose times is 64. Well, if they add up to a positive and multiply out to a positive, then they're going to be positive and positive. I can handle that. Two numbers that add up to 16 and multiply out to 64 are the same number, 8 and 8. Now here's a fun fact. Here's a trick. If you have the same parentheses twice, you can factor that one step further by writing it out once and squaring it. So b plus 8 times b plus 8 is b plus 8 squared. Okay, now it's completely factored. That is my official answer, not that. That's just sloppy. Speaking of sloppy, ugh. Now, I'm looking at that and I'm like, wait a minute. I thought we were going to always pretend that the number in front of here is an invisible 1. I did say that. But factor, as you know from a different section that I did, could mean two different things. Factor could mean reverse distribution, which means I can bring a common factor out of everything. In fact, when I look at this, I notice that I can divide a 5 out of all of these. So let me bring a 5 out. When I divide a 5 out of here, I have invisible 1. N squared is left over. 5 divided by 10, or 10 divided by 5 is 2. N is left over. And if I take a 5 divided from a 20, I have 4. Now I look in here and I ask myself, can I do sometimes on that? Are there two numbers whose sum is 2 and whose times is 4? And the answer is no. There are no two numbers that add up to 2 and multiply out to positive 4. So in this case, factor just meant pull out a 5. That's it. That's it. Be careful. Now, could I factor twice in the same problem? I guess we'll see. I see a 6 living in front of a v squared. I also see a 66 and a 60. Which tells me that there's a 6 in common with all of those guys. So let's pull out the 6. When I pull out the 6, I have v squared and nothing in front of it. I have 11v, because 6 taken away or divided from a 66 is an 11. And if I do 60 divided by 6, I get 10. Now I look at what I have left inside. I have v squared. I have positive 11v. I have positive 10. Are there two numbers that add up to 11 and multiply up to 10? I don't know. Did I happen to do a problem like that a couple problems ago? Did I? Oh, I did. There are two numbers that add up to an 11 and multiply out to a 10. 1 and 10. So let's go back. Let's go back. All the way back. I can factor this and say two numbers that add up to 11 and multiply out to 10 are positive 10 and positive 1. These are V's, so I'm going to throw V's in there. And we can never forget that 6 that lives out front. So my final answer is that guy right there. So sometimes in a problem, in a single problem, you can factor twice. I just did. Wasn't that so much fun? I love factoring, and I don't know what's wrong with me that I love factoring, but I love factoring, and you can't judge me. That's God. That's Him. Bye. What up, what up? Today on Back to Basics, we are going to talk about perfect square trinomials. That looks terrible. Well, it's not. It's actually convenient. See, a perfect square trinomial might look something super friendly like this. I give you a regular old quadratic, and I say, hey, please factor that. And you're going to be like, oh, okay, well, let me quick come up with two numbers whose sum is 2 and whose product is 1 and blah, 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 blah. That is exactly what it is. And that's how we're going to approach the first one. But then we're going to learn that there's actually kind of a shortcut to doing these problems so you don't have to think so hard if you just memorize what a perfect square trinomial is. So let's take a look at this first one. I'm asked to factor it. That's a quadratic. I need to think of two numbers that add up to 6 that multiply out to 9. I use the term sometimes because one of my students from back in the day invented it and I loved it and I kept it and I'm stealing it. So two numbers that add up to 6 times out to 9 is 3 and 3. So we have R and R, which is what I need right now. Everything's positive, so plus 3 and plus 3. And we were taught, well, if you have the same exact parentheses twice, just write it out once and square it. And that's called a perfect square trinomial. There's a faster way of doing these. If you notice that that is a square, and you notice that that is a square, you might remember from difference of squares that that's a shortcut. However, this isn't a difference of squares. In difference of squares, there was nothing in between. This, you have a number with a letter attached to it. But what's special about this is if I take that guy and square root it, I'll get R. If I take that guy and square root it, I'll get 3. And do 3 times R times 2, I will get the middle guy. So if you look at this right away and say, I'm going to think about R, I'm going to think about 3, I'm going to multiply it by 2, do I get 6R? Yep. You automatically know that you are at a perfect square trinomial. Don't go any further.
Could we have a custodian report to the gym to put the baskets down and open the wall? Could we have a custodian report to the gym to open up the form side wall and put down the baskets on the side and main baskets? Thank you.
So the next problem, I'm going to see if I notice that right away. I have a square right away out front. I have a square right away at the end, 5. And if I multiply 5 times m, 5m, times 2, do I get 10m in the middle? And the answer is yes. Yes, I do. So what does that mean? Well, I'm going to write out my parentheses. The first guy was m. The second guy was 5. And since that is a plus sign, then this 2 is going to be a plus sign. Don't forget to square everything. Done. So that's the cheat. That's the shortcut. And when you look at a problem like this, you're like, why do I have to waste my time doing a shortcut? I'm just going to do the same old-fashioned way and get 5 and 5 and then have to square it at the end. Yippee, it's going to take the same amount of time. Yeah, probably, until you get to a problem like that. Now, these are horrible.
quadratics. If you don't know what you're doing, you take that, you split them up, you find all these combinations, and a problem like that could take about 5 minutes. Or you notice that 25n squared is a square. The square root of 25 is 5. The square root of n is n. So, okay. The square root of 9 is 3. Now that's minus in the middle. That's going to be important. What's 3 times 5n? 15n. Multiply it by 2. 30n. Do I get the middle guy there, 30n? Yes, I do. So I'm going to write my own set of parentheses. I'm going to square it. Let's do that now. I'm going to write my 5n first. I'm going to write my 3 second. And since this guy is a minus sign, I have to use a minus symbol. And that's it. So if you know the shortcut, the problem's a whole lot easier. And there's the shortcut. So let's do it again. Let's do it again. 100p squared, regular 4, negative 40p in the middle. What's the square root of that guy? 10p. What's the square root of that guy? 2. 2 times 10p is 20p. Multiply 20 times 2 and you get 40. 40p, there it is. Square it. 10p goes first. 2 goes second. That's a negative, so you're a negative. Done. It's not that bad once it clicks. Now, before I get started, I noticed something. I noticed that there's a 4 in common with everything. So what I'm going to do is I'm going to pull out a 4. Remember, factoring doesn't mean you just, split it up into parentheses. Factor means look first and see if you notice something in common with everything. And I notice that there's a 4 in common. So if I pull a 4 out, that leaves me with regular x squared minus 2x plus 1. Now this section is still called perfect square trinomials. Look at what's left over. Can you factor that further? Yes, you can. That's a square. It becomes an x. That's a square. It becomes a 1. 1 times x is 1x. Multiply that by 2 and you get 2x. All right? So that is a perfect square trinomial. I didn't write out the right thing. I only need 1 parentheses. So write out the parentheses. X and 1. X and 1. That's a minus, make you a minus. Square that, make you a 4, and I'm done. It's the pen making the mouse move. That was fun. And perfect. Oh, they should have just called this perfect Parrish square trinomials. Okay, thanks for watching. Bye. Yes, back to basics. Another fun romp. Fun romp too. I'm going to leave that in there. I'm not going to edit that one out. Today we're going to talk about difference of squares. Now, difference of squares is exactly what it sounds like. It's a form of factoring. Like you would be asked to factor that. That is an eraser. So you would be asked, factor that guy right there. And you might look at that and say, I thought when you factor a quadratic, there should be 3 terms. Not always. See, a difference of squares is named after exactly what it sounds like. A square minus a square. Difference means minus. Squares means they have squares attached to them. Or you could take the square root of them. And that's kind of what we're looking at. When you are asked to factor a difference of squares, you are going to have your parentheses like you always do when you factor quadratics. And inside one of them you have a plus, and inside the other one you have a minus. Doesn't matter which one's which. And in the first part of each parentheses is going to be the square root of the first term, and the second part of the parentheses is going to be the square root of the second term. So this is called a special case. And what I'm looking at when I'm asked to factor that is, do I have a square? Yeah, n squared is a square. Do I have a difference? Yeah, a minus is a difference. And do I have a square? Yeah, a 25 is a square. The square root of 25 is 5. So what you do is you have your parentheses. You take the square root in your head, of course, of the first guy, get n. You put a plus or minus, and you take the square root of the second guy in your head, of course, and you're done. Difference of squares. That's it. It's easy. Now they get a little more complicated, but that's basically the idea. You're being asked to factor something squared minus something squared. That is a square. That is a minus. 84 is a square, 8 squared. So you split it up into two parentheses, right? You take the first guy in your head, you square root it, that gives you p, that gives you p. You make one of these plus, you make one of them minus, it doesn't really matter. You take the square root of this guy in your head, that gives you 8, that gives you 8, and then you're done. Now, if you're wondering, like, why does that make sense? Well, I thought when I foiled, like if I wanted to check my work and I foiled these out, I thought you would get 3 terms because you combine like terms. Not in this case. P times P is P squared. P times negative 8 is negative 8P. P times positive 8 is positive 8P. Those middle terms cancel each other out. So there is no middle term in the difference of squares cases. That's why it's a special case. Ooh. Is 9x squared a square? There's 2 things there. Yes, it is. The square root of 9 is 3. The square root of x squared is x. The square root of 9 is 3. The square root of x squared is x. Is that a minus? Yes, it is. Make one of you positive, make one of you negative. Can you take the square root of 1? 1 times 1 is 1. There you have it. And we're just going to keep moving along. We'll keep moving along. Can you take the square root of 49? Yeah, it's 7. Can you take the square root of x squared? Yeah, it's x. Is that a minus? Yeah. Is that a square root or a square? Yeah, take the square root. You get 10. So square root of 49 is 7. Square root of x squared is x. Make one of them positive, make one of them negative. It doesn't matter. Square root of 100 is 10. It's got to get more complicated at some point. Is that a square? Yeah, it's 1. Is that a minus? Yeah. Is that a square? Yeah. So 1, 1, minus, plus, minus. The square root of r squared is r. Can you take the square root of 10? No, but and that is a cube. Oh yeah. Factoring doesn't only mean like you put things in 2 separate parentheses. Sometimes when you're asked to factor, you pull stuff out. I can take a 10 out of both of these. I can also take a p out of both of them. And when I do that, when I pull a 10 out of a 10, I'm left with 1, invisible 1. When I pull a p out of p cubed, I'm left with p squared. That's a minus. When I pull a 10 out of 1,960, I'm left with 196. And when I pull a p out of a p, I have nothing. But I'm not done. You see, sometimes you can factor more than once. I have to look at that guy and see, can I factor any further? And the answer is yes. Because I see in here, I have a, say it with me, difference of squares. Is p squared a square? Yeah. Is a minus a minus? Yeah. Is 196 a square? Yeah. It's 14 squared. So that 10p lives out there. This parentheses gets split up into 2 parentheses, where the first part is the square root of p, positive, negative, doesn't matter, and the square root of 96 is 14. 196 is 14. And that, ladies and gentlemen, is difference of squares. I hope you had as much fun as I did. All right, thanks for watching. Bye. up, what up? Today we're going to talk about the ungodly form of factoring ax squared plus bx plus c where a is not 1. It's kind of difficult. Lots of guess and test with this one. Can be frustrating at times, but I will be your tour guide through your frustration. First thing you're going to want to do is you're going to look at the number in front of x squared. I'm going to list out all the factors for it. I'll show you what that looks like. Then you're going to look at C. You're going to list out all the factors for that. I'll show you what that looks like. And then your job is to try to find combinations to see if they kind of multiply and then add up to B. So kind of a bizarre process. Again, you know, I've been teaching math for almost 20 years and people ask me, is there a definitive way of doing these types of problems? And the answer is no. No, there's not. There's just, people have methods. There's this thing called the block method, I think. There's this thing called the imposter method. I was thinking Among Us. But, you know, I don't know. This is the way I do it. This is the way I like it. So in rule number 1, I said list out all the combinations for A. So what that looks like is I'm going to have 5 and 1. That makes out, those are the factors that make 5. Over here, I have several more options. I have 2 and 6, but I'm also going to write out the other version, 6 and 2. I have 3 and 4, so I'm going to write out 4 and 3. What else multiplies out to 12? I have 1 and 12, so I'm going to write out 12 and 1. Now what I do is I kind of predict what I think it's going to be. I'm going to take 1 and multiply it to another one of these inside numbers. I'm going to take 5 and multiply it to one of those outside numbers. Then I'm going to add the product of what I think it is. So I'm just going to do the first one, demonstrate what I'm talking about. I'm going to try to match up 5, 1 with 2, 6. I'm going to multiply the inside numbers, 1 times 2 gives me 2. And I'm going to multiply the outside numbers, 5 and 6, that makes 30. I'm going to add them up and see if I get 19. I don't, which means the first option is not the right option. So if you kind of look at things and say, all right, well, I know I'm going to multiply the interior numbers. I know I'm going to multiply the exterior numbers and then add them up. So let me guess what I think is right. Well, we definitely know it's not the first one. So let's just try. Multiply the inside numbers. 1 times 4 is 4. Okay. Multiply the outside numbers. 5 times 3 is 15. Okay. Add them up and see if I get 19. I got 19. So what does that mean? That means I set up a set of parentheses. I have 5 attached to my n, and I have 1 attached to my other n. So I have 5 and 1, put it in that order. Then I'm multiplying it to 4 in the left parentheses and 3 in the right parentheses. Now I could rewrite this out, get rid of that 1. Let me see if I have an eraser small enough that'll just do that for me. Bang, bang. And I double check my work. 5n squared, 15n, 4n, 19n, and then 12. So that's my process. I don't have a name for it. I'll call it the Nicholas Parrish method of factoring wacky quadratics. The Nicholas Parrish method. I like it. Okay? Weird. Let's do another one. Okay. List out all the factors. 1 and 2. That's it. List out all the factors for 2. 2 and 1 and 1 and 2. Pick one that you think it is. I think it's that one. and multiply the interiors, so that's 2 times 2, that gives me 4. Multiply the exteriors, 1 times 1, that gives me 1. Add them up and see if you get the coefficient attached to your middle variable. I do, which means I set up my parentheses. What goes here? 1. What goes here? Well, first off, let's do the things attached to n. 1 is attached to n, so 1n. 2 is attached to n, so 2n. So first thing in the first parentheses, first thing in the second parentheses, second thing in the first parentheses. So 2 comes from that something that's not attached to any variable. 1 comes from something that's not attached to any variable. There you have it. Let's get rid of the 1 in front of that n by erasing it. Works for me. Okay. N times 2n is 2n squared. N times 1 is 1. 2 times 2n is 4n. So there's your 5 n's. 2 times 1 is 2. The Nick-Parich method. Okay? I have to click that one. No, of course it gets worse. Now, look, let's take care of the first guy. Think of 2 guys that multiply out to 3, 1 and 3, or 3 and 1. It really doesn't matter. 4. Now, here's where we have to be careful. Since this guy is negative, I need to pick 2 negatives that multiply out to 4. So negative 1 times negative 4 do that. Negative 4 times negative 1 do that. And negative 2 times negative 2 do that. And I'm not going to write down negative 2 times negative 2 again. All right, so let's pick what we think it is. I think it's u. So let's multiply the insides. Let's multiply the insides. That gives me negative 3. Let's multiply the outsides. 1 times negative 4. And ooh, I was so close, because when you add them up, you get negative 7, and that's not what I wanted. Boy, does that steam me. Boy, does that make me angry. So it wasn't the first one. I was wrong. I didn't know that would happen. Let's try the last one, because I don't have a good feeling about that last one. Let's try that last one. So the first one didn't work. 3 times negative 2. 3 times negative 2 is negative 6. 1 times negative 2 is negative 2. Add them up, you get negative 8, which is the number in front of n. It's exactly what I want. So let's write out our parentheses. 1 is attached to n squared, so 1n. 3 is the second one attached to n squared, so 3n. Negative 2 is the first guy not attached to anything, so negative 2. And negative 2 is the second guy not attached to anything, negative 2. Let's get rid of that 1 in front of n by erasing it. N times 3n, 3n squared. N times negative 2 is negative 2. Negative 2 times 3n is negative 6, so negative 6 and negative 2 make that negative 8, and then negative 2 times negative 2 is positive 4. Very popular. Very popular. Last one. Oh, but it's a doozy. It's a doozy. That's the eraser. All right, 1 multiplies out to 4. 1 and 4 does. Oh, and 2 and 2 does. Interesting. Over here, we have to write out all the possible combinations. So you have negative 1 times 25. You have regular 1 times negative 25. You have negative 5 times 5. You have regular 5 times negative 5. Also, I have 25 times negative 1. I have negative 25 times positive 1. And I think that's it. So let's just try a random one that I know will not work. Let's try a random one that I know won't work.
Okay, multiply the insides. 4 times 1 is 4. Multiply the outsides. 1 times negative 25 is minus 25. Add them up, you get negative 21. It doesn't work. So it's not that one. Now, some of you might be thinking this method is great, but if I were to try all of these, I would literally try 1, 2, 3, 4, 5, 6, 7, 8, 12 of them. Yeah. And you might be thinking, can I just guess and test? Yeah. But if guess and test isn't working, this is a surefire way that no matter what, if you try all of them, you will hit one. So that one didn't work. I'm trying to find one that will. How about negative 15? Let's try. These are too big. Too big. Let's try one of these. 2 times negative 5 is negative 10. It's not that. I already decided this is not going to work. Negative 10. 2 times regular 5 is regular 10. So that becomes a 0. I should have known. So let's get rid of that one. It's not you. It's not you. Oh, I think I see it. I think I see it. I think it's this one. Let's get a different color. Let's get purple. 2 and 1. Make. No, that won't work either. Ah. I'm going to have to fast forward through this. That won't work. I see it. No, I don't. I see it. It's this one. 4 times negative 5 is negative 20. 1 times 5 is positive 5. Add them up, you get your negative 15. So when we write them all out, right, 1 gets attached to n. The second one that's attached to n is 4. You have negative 5 in the left parentheses. You have positive 5 in the right parentheses. We can erase this guy. So again, what you saw was me legitimately trying to do a problem without knowing the answer. You saw me guess 2 of them that just flat out didn't work, or 3 of them, whatever it was, that just flat out didn't work. Eventually I came to the answer, and that's kind of the frustrating part about these types of problems, is they may take a while. But if you use this method, you will not go wrong, except for wasting a whole lot of your time. And time is precious. And I appreciate your time. So, as always, thanks for watching. I love you. Like and subscribe. Bye. Hi everybody. In today's edition of Back to Basics, we are going to discuss factor by grouping. Now, factor by grouping is very strange. Usually you're given 4 terms, sometimes 6. Usually you're given a cubic, sometimes it's a 6th degree. It really all depends. But this is what you do. Step number 1, you graph the first half. Not graph. You put the first half in parentheses. Make sure that's a plus sign, and then you put that in parentheses. Okay? Step 2 is you factor each parentheses individually. You take a look at what you have here. You could say, all right, well, I can pull out an 8. I can pull out an r squared. That's it. When I do that, once I pull an 8r squared out of an 8r cubed, I'm left with just an r. When I pull an 8 out of 64, you divide it. That's an 8r squared out of an r squared. That's it. I'm done. Then you take a look at the second one, and you see what you can factor out of that. And there's nothing. But what we're going to do is we're going to put an invisible 1 out in front, and you will see why. Now, what should always happen after you do that step is you will always see the same exact parentheses. If you don't, you didn't factor enough, or maybe you need to factor a negative or something weird like that. But I have 2 major terms right here, and in each term I have red, r minus 8, in common. So pull out the r minus 8, pull out the r minus 8. That leaves you with an 8r squared, in parentheses of course, plus 1, close parentheses. So the last step of factoring by grouping is you take out the parentheses that's in common, you put it out in front. Whatever you have left over, 8r squared plus 1, goes in its own set of parentheses. Then you take a look at each parentheses, see if you can factor any further. Nope, I'm done. Weird? Yes. Fun? Yes. Let's do it again. Parentheses the first half. Make sure that's a plus sign. Parentheses the second half. I can factor a 3 out of that one. I can factor a p squared out of that one. That leaves me with 12 divided by 3 is 4. Take away 2 p's from 3 of them, you have a p. Negative 21 divided by 3 is 7. Both p's are gone. There you have it. Plus, what can I factor out of this guy right here? I can factor out a 7. And that's it. When I factor out a 7, what I'm left with is 7 divided from 28p is 4p. How about that? 7 divided from negative 49 is negative 7. How about that? And both red parentheses are exactly the same. So we take that red parentheses, we pull that out and place it out front, 4p minus 7. And what's left over goes in its own set of parentheses, 3p squared plus 7. Can I factor u any further? Nope. Can I factor u any further? Nope. Am I done? Yup. Factor by grouping. Let's wrap that in its own set of parentheses. Make sure that's oh no. It's not a plus sign. So this is what we do. We make it plus a negative and wrap that in its parentheses. That always has to be a plus sign. That always has to be a plus sign. So let's drop it down. What can I factor out? I can factor a 2. I can factor out an x squared. 2 divided from 12 is 6. X squared divided from x cubed is x. 2x squared is plus 1. There you have it. Now, let's use common sense before we do the next part. Okay, let's use common sense. I need to make that look like 6x plus 1. Those are both negative. So why don't I factor out not just a 5, but a negative 5. So minus 5. And when I take a negative 5, divide a negative 5 from negative 30x, it's positive 6x, which is what I want. And if I divide a negative 5 from a negative 5, I get positive 1. Those two parentheses are the same. Those two parentheses right there. So let's pull that out, 6x plus 1. These two get their own set of parentheses, so 2x squared minus 5. Can I factor that anymore? Nope. Can I factor that anymore? Nope. Done. Last one. Put that in parentheses, put that in parentheses. Uh-oh, a minus sign, make it a plus negative and put those in parentheses. Okay. What can I factor out? 4v squared, that leaves me with v
minus 3. I'm going to factor out a negative because this first term is supposed to be regular v, so I'm going to factor out a minus 5. That leaves me with v. When you divide negative 5 from positive 15, you get minus 3. There's my v minus 3 in common. Factor that out. V minus 3. What's left over gets its own set of parentheses. 4v squared minus 5. Can you factor any more? Nope. Can you factor any more? Done. Fun. Done, fun. Fun, done. I'm very tired. Thanks for watching, though. I appreciate it. You guys have a blessed day. Like and subscribe. I love you. Bye. What up? What up? Back to basics today. We're going to talk about simplifying rational expressions. Now, something that's rational is a fraction. When you have a number divided by a number, usually what you do is you try to, in a sense, maybe you don't do this, but you think, let's factor out the greatest common factor. So I'm going to do that. I'm thinking outside the box a little bit. It would be better if I thought using a pen. So I'm going to factor out the greatest common factor, which appears in this case to be a 12. So factor out a 12 up top in the numerator and downstairs in the denominator. And if I factor out a 12 from 24, I'm left with 2. And I factor out a 12 from 36, I'm left with 3. Now, if you're multiplying straight across the numerator or multiplying straight across the denominator, anything that's identical, ignore that bell, gets eliminated. And so I'm left with just 2 and 3. Now, again, a lot of people would be like, well, I usually just divide everything by 2 or whatever, something like that. But this is how I'm going to approach everything today. I'm going to factor as much as I can and eliminate. So that's where we're headed. So if I have letters involved, all right, I have a greatest common factor that I can factor out. And that's going to be, let me see, 8. Factor out 8. I can factor out 8. When I factor out an 8, I'm left with 4. You know what? I can also factor out an n. Down here, I can also factor out an n. So let's do that. Factor out an 8 and an n. When I factor out an 8 and an n on top, when I divide the 8 from the 32, I have a 4. When I take one n away from another n, I have 4n. And when I factor an 8n out of 24, I have a 3. These guys cancel out. And I'm left with 4n over 3. Now, a lot of people might say, like, okay, well, I have 2 n's up here. Let's cross that out, and now I'm left with just the n, and 32 over 24 simplifies. However you want to work it, but I'm trying to factor out things that are the same. I'm trying to factor out things that are the same so I can cross that out. That's the point. That's why I factored out 8n, because I knew I had an n in common and I had an 8. Essentially, I'm finding the greatest common factor in the numerator and the denominator, factoring that out so I can get rid of it. That's what I did. That's what I did. All right. Nothing to factor upstairs. Nothing at all. However, downstairs, I can factor out a 3, so I have 3x squared minus 12x, so I have a 3 in common with both. I have an x in common with both. So let's factor out a 3x. When I factor out a 3x out of 3x squared, that leaves me with just an x. Minus comes along for the ride. If I factor a 3 out of 12, that's a 4. And if I factor an x out of an x, that's it. Now, why is this good news? Because I have one thing living upstairs, and that one thing is x minus 4. Downstairs, I have 3x times x minus 4, which means I can eliminate the x minus 4s. See it? If I eliminate everything on one side, I'm left with just a 1. And on the bottom, I have just a 3x. And so that's my answer. How about that? How about that? Catch me outside. How about that? Every time I do a pun, an angel gets its wings. That's what that ding was for. All right. You know, it would be very wrong for me to just cross these out. You can cross things out if you're adding and subtracting. And if you're like, but you were subtracting in the last problem, I turned it into a multiplication problem where I add one thing upstairs over something times something. And it just so happens the one thing up here was the same as the one thing down there, and that's why I was allowed to cross out. Here, I'm not allowed to just be like, cross out the x squareds because they're the same. No, I need to turn it into a multiplication problem. So I'm going to attempt to factor the numerator. So I need to come up with two numbers whose sum is 8, whose product is 12. So that would be the 4 and 4? No. 6 and 2. So x plus 6, x plus 2. Dos. Down here, I need to come up with two numbers that add up to positive 3, but multiply out to negative 18. So let's do x minus 3 and x plus 6. Now I have this times that over this times that. Ooh. Something upstairs is the same exact thing as something downstairs, so let's cross them out. And that leaves me with x plus 2 over x minus 3. Now, before you're like, cross those out, cross those x's out, you can't because you're adding and subtracting in the numerator and the denominator, and you can't do that. You can't. Just can't do it. What I can do is one more problem. Now, right away up here, I notice that I can factor out a 3 out of everything. So let's do that. Let's factor a 3 out of everything. After I factor a 3 out of that, I have r squared minus 13r plus 30. Let's factor the bottom, the denominator. Two numbers that multiply out to negative 70, but add up to negative 3. How about r minus 10, r plus 3? Can't cross anything out. I have 3 times stuff over something times something. But you know what? That stuff up there looks like I can factor it. Can I come up with two numbers that add up to negative 13 but multiply out to 30? Sure can. How about r minus 3 and r minus 10? And that's going to be over r minus 10 in parentheses minus 10, that's supposed to be a 10, wow, times r plus 3. You cross out, you cross out. Now I have 3 parentheses r minus 3 over r plus 3. And if you're thinking, let's cross out the r's, you can't. What I can do is I can distribute that back to get 3r minus 9 over r plus 3. And even though you see a lot of similarities between these, you can't do any more with that. You're done. You're done. Simplifying rationals. Easy as pumpkin pie on a summer morning. I don't know what that means. Thank you. Bye. Solve 2n squared minus n minus 4 equals 2. This is a quadratic. And in order to solve a quadratic, you really need to get 0 alone on one side. So the way we're going to do that is we're going to start out by subtracting 2 from both sides. There you have it. That gives us 2n squared minus n minus 6 equals 0. Now, this is probably factorable, but what I'm going to do is I'm going to use the old quadratic formula. Let me sing it for you. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Copyright goes to Nick Parrish. Now, I know this is x equals and I was given n, so I'm just going to pretend that that x is an n. But what I need to do is I need to label these guys up here. A Negative 1 is going to be B. Okay, negative 1, negative 6 is going to be C. We just throw stuff in. Watch out for double negatives. There's going to be probably quite a few of those. Negative B is going to be negative 1. So right away we have a double negative. Plus or minus, positive or negative, big square root of B squared is going to be negative 1 in parentheses squared minus 4 times A, which is 2, times C, which is negative 6. Let me scooch that over. Let me give myself a little bit more space. And then we have over 2A, which is going to be 2 times 2. All right, let's do some simplifying. Negative 1 is regular 1. Positive or negative? All right, we've got negative 1 squared, which is 1, minus 4 times 2, which is negative 8, times negative 6 is going to be plus 48. How convenient is that? All over 2 times A, which is 4. So this gives us 1 plus or minus the square root of 49 over 4. This gives us 1 plus or minus 7 over 4. Now at this part, we are going to split this up into 2. One is going to be 1 plus 7 over 4, because it's positive or negative, and the other one is going to be 1 minus 7 over 4. 1 plus 7 over 4 is 8 over 4, which becomes 2. So one of my answers is going to be not x, but n equals 2. And the other one is going to be 1 minus 7, which is negative 6 over 4, which simplifies to negative 3 over 2. So when I have somewhat friendly answers like this, yeah, the original problem was factorable, but you know, what fun is that when we could just use the quadratic formula and sing? Hi, everybody. Let's use Desmos to graph a quadratic in vertex form. I wonder how it's done. All right, graphing an equation in vertex form. I wonder if there's going to be any similarities in the equation and the picture. Probably. Negative 1/4, negative 1/4. Move to the right before you start typing out parentheses. X minus 1 inside the parentheses. You can get squared by clicking the keyboard and hitting squared right there, getting rid of the keyboard, or you can hit the little caret button, which is Shift 6. That'll do it for you too. What's next? Plus 4, and there's my picture. So you can move it around if you need to. Hit home when you're done. But you can see some pretty important areas. If I click on this guy, I can see my vertex, which is 1, 4. So you could see 1, 4 hiding in the equation. This is opening downward, and the reason why this is opening downward is the whole thing starts out with negative 1/4 attached to my parentheses. That's what makes it open up downward. It's kind of wider because 1/4 spreads it out. But yeah, there it is. I mean, we can go throughout this whole thing and get some pretty important points if we want to graph this. So yeah, there's your equation in vertex form, baby. Oh, wow, that's pretty cool. I'm going to leave it right there for a few more seconds for you to enjoy. I enjoy you. I hope you enjoy me. Thanks for watching. Bye. Hey, you, stop being irrational. That means wild and ridiculous with no end and no pattern. Oh, I'm sorry. I didn't realize. I didn't see you there. Let me do some math. Oh, rational or irrational? Oh, what's the difference between the two? Rational is like a regular old number that you can write as a fraction, like 5, or 5 over 7, or point something repeating, or a pattern, or whatever. Now, square root of 4. Oh, that's 2. Can I write 2 as a fraction? Well, certainly I can. 2 over 1. Is this rational or irrational? Rational, because 2 can be written as 2 over 1. What about 0.23? Well, I can write that as 0.23 repeating. And if you watch the very short video that I made about repeating decimals, I know that that can be written as 23 over 99, a good old fraction. That's rational too. The square root of 101. I don't know what the square root of 100 is. And what I do know is if I can't take the square root of a number nicely, it's always going to be irrational. So this guy is going to be irrational. .815 repeating. Oh, another repeating decimal. Well, if the repeating decimal over here is rational, then this repeating decimal over here is going to be rational as well. Rational, rational, irrational, rational. In between what two integers does the square root lie? Okay. In between what two integers does the square root lie? I don't know what the square root of 14 is. I really don't. But I do know my perfect squares. 1, 4, 9, 16, 9, 16. I don't know what the square root of 14 is, but I do know that the square root of 9 is 3. And I do know that the square root of 16 is 4. Which leads me to think that the square root of 14 has got to be in between the square root of 9 and the square root of 16, which means my answer is going to be in between 3 and 4. That's it. Done. Done. In between what two integers does the square root lie? I don't know what the square root of 175 is, so let me think of my big square roots. 144 is 12, 121 is 11, 144 is 12, 169 is 13, 196 is 14. Oh, you're going to live in between 169 and 196. 169 is 13, 196 is 14, so the square root of 175 is in between 13 and 14. Similarly, I don't know what the square root of 90 is, but I do know what the square root of 100 is, and I do know what the square root of 81 is, and I do know that the square root of 81 is 9, and the square root of 100 is 10, and 90 lives in between 81 and 100, which means square root of 90 is going to live in between 9 and 10. I do know that. Which is greater, the square root of 48 or the cube root of 127? Oh, let's find out. Let's split these in two. Square root of 48. I don't know what the square root of 48 is. But I do know that the square root of 36 is 6. And the square root of 49 is 7. So this guy is square root of 48, which is almost the square root of 49, which means this guy is almost 7. So I'm going to write that out because my job is to find out what's greater. I do have a calculator, but that's too easy. Cube root of 127. I don't know what the cube root of 127 is, but I do know my cubes are 1, 8, 27, 64, 125. Oh, okay. The cube root of 127 is going to be a little bit more than the cube root of 125. So this guy is going to be a little bit more than 5. This guy over here is almost 7, which is a whole lot more than a little bit more than 5. So which one's greater? This one is. Because the square root of 48 is 6 point something, and the cube root of 127 is 5 point something, and 6 point something is bigger than 5 point something. Interesting problem. So much fun. I can barely contain myself. Too bad I have to leave. Bye. What What up, what up? Today we're going to talk about simplifying radical expressions. That is a square root. Now, the method that I use when I do these is pretty simple. It's the way that I use it, which means it's the best way possible. Take whatever number you have and then whatever letter you have and make the prime factorization. Now, if you don't remember how to do the prime factorization, go over here. Let's get a pen going first. Go over here, make yourselves a little factor tree if you need to. 125 is 5 times 25. 5 is prime, circle it. 25 is 5 and 5, circle U, circle U. Rewrite this out and write out the prime factorization of 125n. 125 is 5 times 5 times 5, and then a single n is n. When you simplify roots, if it's a square root, what you're looking for is every identical pair of numbers. I have a pair of 5s. You circle that pair and you bring out one of them. Why? Because the square root of 5 times 5 is 5. And so now you're brought out. Write out what's left over, multiply 5 and n, which is just 5n, and you're done. I just simplified that square root. So let's take a look at this guy. Same exact rules apply. 216, I'm actually not sure what that is off the top of my head, so let's do a factor tree for you. You look like you're divisible by 2, so circle a 2. Let me see, 108. Divide 108, let's do 4 and 27. I can't circle anything. 27 is going to be 3, circle that, and 9. 9 is going to be 3 and 3, circle U, circle U. 4 is going to be 2 and 2, circle U, circle U. So I'm going to write out my square root and write out my prime factorization in order. 2, 2, 2, 3, 3, 3, 2 times 2 times 2 times 3 times 3 times 3. And then I'm going to write out 4 Ks. I regret my letter choice, but I'm going with it anyway. All right. This is a square root. So what we're going to do is we're going to look for pairs of identical numbers and pull each of them out. Also, pairs of identical variables. Can't forget them. So let's circle a group of 2s, bring one of them out. 2 is left over. Circle a pair of 3s, bring one of them out. 3 is left over. Circle a pair of Ks, bring one of them out. Circle a pair of Ks, bring one of them out. Nothing left as far as variables go. So what I bring out is a 2 times a 3 times a K times a K. And what I have left inside is a 2 times a 3. Simplify everything. 2 times 3 times K is 6K squared. 2 times 3 is 6. And I just simplified that square root. Pretty easy, huh? I like these. These are fun. I'm having a good time. Another square root. Let me see. 200 is 2 times 100, and 100 is 10 times 10. So we've got 2 times 2 times 2 times 5 times 5. M times M times M times M times N. Circle a pair of 2s, bring it out. Circle a pair of 5s, bring it out. Circle a pair of M's, bring it out. Circle another pair of M's, bring it out. You're left over, so we have 2 times 5 times M times the square root of 2 times N, the leftovers. 2 times 5 is 10. M times M is N squared. The square root of leftovers is 2n. Dunzo. Now, some of you might be thinking, all right, I see what you're doing. You're ripping everything apart. You're showing more work than necessary. I got it. Is there a faster way to do this? Of course. If you see that what's inside here is either a perfect square or something times a perfect square, then just kind of factor out whatever you need to factor out so that you have a perfect square. So 200 is 2 times 100. I know 100 is a perfect square. M to the fourth is also a perfect square, and n doesn't do anything for me. Take the perfect squares and square root them. So the square root of 100 is 10. The square root of m to the fourth is m squared, and then what you have left over is 2n. When I teach it, I always teach it this way. If the numbers get outrageously big, then maybe I'd switch over this way. But, this way didn't take forever. It's not that bad. It's not that bad at all. Let's keep going. Got another square root here. We've got 28, x to the third, y to the third. 28 is 7 times 4, or 2 times 2 times 7. X is x times x times x. That's x to the third, and y to the third is y times y times y. Never make that long enough. 2 times 2 comes out. Boop. X times x comes out. Boop. Y times y comes out. Boop. You have a 2 out here times, 7's left over, and x out here, x is left over, times a y out here, a y is left over. Let's write out those leftovers. 7 times x times y gives me a final answer of 2xy times the square root of 7xy. My goodness, there's already a negative 8 out there. Do the rules change? Absolutely not. Let's keep that negative 8 out there. Okay, and let's see what that is. 24 is 4 times 6, so 2 times 2 times 2 times 3 times k times k times k. Let's bring out a pair of 2's next to that negative 8. No 3's go out. Let's bring out a pair of k's. That goes out too. So on the outside, you now have negative 8 times 2 times k. On the inside, you have a 2 times 3 times k left over. Negative 8 times 2 is negative 16. K comes along for the ride. 2 times 3 is 6, and k comes along for the ride. Not bad, right? This is the last one, and it's still not that bad. We have a number out here, negative 2. Who cares? We have, 3 letters in here. What am I to do? What am I to do? Well, negative 2. Big square root. So that's 6 and 8. So that would be 2, 2, 2, 2, 3. Yep. A, B, 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 C, C. Once again, the line's not long enough. Let's circle groups of 2. Circle it, bring it out. Circle it, bring it out. No 3's, circle a pair of A's, bring it out. No more A's, circle a pair of B's, bring it out. Circle a pair of B's, bring it out. Circle a pair of C's, bring it out. We already have a negative 2 living out there. We're going to bring out another 2, an A, a B, and a C. And what do we have left over? A 3 and an A, so a 3 times an A. Negative 2 times 2 times 2 is negative 8. A, B squared, C, and then what do you have? 3A. So this was focusing on square roots and square roots alone. If it was a cubed root, you'd circle groups of 3 and bring out groups of 3. If it was a fourth root, you'd circle groups of 4 and bring out, one of those. One of those. Thanks for watching. I had fun. I hope you did too. Bye. Back to basics. Hey, remember square roots? And square roots are like, hey, I'm going to write this little squiggly thing, and the number underneath that squiggly thing means what times itself gives you that number. Well, cube roots are the same exact thing, but you ask yourself, what times itself times itself? In other words, what times what is going to be 1? Well, 1 times 1 is 1 times 1 is 1 again. So the cube root of 1 is 1. The cube root of 1 is 1. Now I have to ask myself, what times itself times itself times itself is negative 343? But here's a fun fact. You're not allowed to take the square root of a negative, but you are allowed to take the cube root of a negative, because if you're asking yourself what times what is a negative, well, negative times a negative, positive times a negative is a negative. So you get a negative if you take the cube root of a negative. And now what I have to do is ask myself, what times itself is 343? 7. It's one of those things where not everybody knows that, but you can look it up on the internet. Oh, look, cube root of a negative, which means I get a negative. The cube root of 27 is 3, and the cube root of 1,000 is 10. Remember, if you took the square root of a fraction, you're allowed to take the cube root of a fraction too. And all you have to do is just take the cube root of the top, the numerator, and then take the cube root of the bottom, the denominator. Hello, Mr. 4. Just hang out there for a second. I want to take the cube root of 8, which means what times itself is 8. 2 times 2 is 4 times 2 is 8. That 4 that was just hanging out is being multiplied to the cube root of 8, which means that 4 that was hanging out is now being multiplied to 2. And 4 times 2 is 8. Is Z all by itself here? No. What's in the way? Cube. That's it. How do I undo a cube? Cube root. I could take the cube root of both sides. Let's do that now. Take the cube root of both sides. That kills off the cubes. Z is all by itself. The cube root of a negative is a negative. And as I might remember from the last slide, the cube root of 1,000 is 10. So my answer is negative 10. Because negative 10 times negative 10 is 100 times negative 10 is negative 1,000. Boom. Is W all by itself? No. What's in the way? Cube. What else? Negative 12. Which one should I get rid of first? How about negative 12? I'll do that by adding 12. W cubed equals negative 76 plus 12. Negative 76 plus 12 is negative 64. Is W all by itself? No. What's in the way? Cube. How do I undo a cube? Cube root. So we're going to cube root everything. That cancels out. The cube root of a negative is a negative, and the cube root of 64 is what times what is 64? 4. 4 times 4 is 16. And then 4 times 4 times 16 times 4 again is times 64, whatever. Is B all by itself? No. What's in the way? A 3 in front. Also a cube. Let's get rid of the 3 in front by dividing 3 from both sides. Cross U out. B cubed equals 343. I had to really think about that one. Wait a minute. The square root of 343 is 7. So if I were to get rid of that cube, I could cube root both sides, and b would equal what times what times what is 347? 7 times 7 times 7 is 347. Oh boy. Well, my box failed. But the answer is 7. Know this. Bro, this. Find the length of each side of the cube. There's really nowhere I can put my face to make things better. How about right in the middle? Look at that. Find the length of each side of the cube. So in a previous video, I gave you the area of a square and said, find the side lengths. And we square root it. Because you square root to go backwards for a square. What do you think you'd have to do to go backwards for a cube? I'll give you a hint. It rhymes with tube moot. Cube root, that's right. So what I have to do is I have to cube root 216. And the cube root of 216 is 6. Also, the cube root of inches cubed is inches because the cube and the cube root cancel each other out. Similarly, over here, I'm given the volume. I'm being asked to work backwards to find the side. The way I work backwards is I take the cube root of 1 over 27. The cube root of 1 is 1. The cube root of 27 is 3. And the cube root of feet cubed is feet. So I have 1/3 feet. And over there I had 6 inches. So there's a video that I have that's exactly about square roots, and it's extremely similar to this video. And this video is about cubed roots. Cubed shuffle. All right. Bye. Find the inverse of f of x equals 2 over 7x minus 10 over 7. All right, so the best way to find the inverse is I'm going to pretend that f of x is y for now, just because it'll make things look a whole lot nicer. I suggest that when you do problems like these, you do the same. The first step that you do is you swap the x and the y. That's step number 1. So y is now x, and x is now y. Now my job is to solve for this new y. So I have myself a literal equation where I have to get y all by itself. Step number 1, add 10 over 7 to both sides. Add 10 over 7 to both sides. X plus 10 over 7 don't combine, so I just have x plus 10 over 7. That's going to equal 2 over 7y. Now I still have to get y all by itself. So what I'm going to do is I'm going to multiply both sides by this reciprocal here, which is 7 over 2. I'm going to multiply both sides by 7 over 2. So I've got distributive property going on, but that allows y to be all by itself. Okay, so y is now all by itself on the right. 7 over 2 times x is just 7 over 2 times x. 7 over 2 times 10 over 7 allows the 7s to cancel out. 10 over 2 becomes 5 over 1, which is just 5. So I get plus 5. Now what I'm going to do to make this look a whole lot better is I'm going to move the y to the left and move this guy over here to the right. 7 over 2x plus 5. Remember, I turned f of x into y, so I'm going to turn y back into f of x. But since this is my inverse, I'm going to make that f inverse of x equals 7 over 2x plus 5. That is my inverse function. Can't spell inverse function without fun.